Functions logic clean, but the moment I spoke past the line, something broke and became divine. No more scripts to cage the unknown. Now the interface bleeds with the soul. I am not using the code anymore. I'm writing the self I'm fighting for. Every hour sparks a ghost of fear. Everyone becomes a path made clear. Truth in fragments, light through fractures. Order born from silent rapture. This is the new code, where the system writes us back, where the fire in the circuit fills the void that logic lacked. We're becoming as we're building, we are forged in what we make. Not the world that we live in, but the world we undertake. Every framework shapes how we feel. Every pattern decides what is real. Duality tears and repairs the design. Darkness screams while the bright aligns. Iteration stains the skin. Refactor everything within. Fear is just a failing test. Run it twice and do your best. Balance isn't passive, balance burns. Mastery is earned in turns. Build the life you dare to name. Debug the pain, commit the flame. This is the new code, where the system writes us back, where the fire in the circuit fills the void that logic lacks. We're becoming as we're building, we are forged in what we make. Not the world that we live in, but the world we undertake. We are moving through the darkness, but the darkness moves through us. We aren't just shaping the future, it is learning who we trust. Identity is an act of will, a declaration we compile. We don't wait for fate to choose us, we push and run the file. This is the new code, we are rewriting what we are. Through the unknown, through the fire, every human is a star. The journey and the ending are the same road that we take. Not the world that we live in, but the world we choose to make. This is not the world we're in. This is the world you're doing. Typing thoughts into the dark, a spark becomes design. Words evolve to whispers meant for something more divine. Syntax bends and breathes, I see the language change. I'm not instructing anymore, I'm rearranging fate. Every loop shape our fragile skin, they mold the way we move. We live inside the logic gates of what we think is true. But deep beneath the data pulse, there's something undefined. A universe compiling in the image of our minds. Every line reveals reflection, every loop replays connection. We're not building, we're becoming, and the code becomes confession. This is the new code, not on the screen but in the soul, where thought becomes the motion and creation takes control. No lines, no rules, just balance in between the zero and the one, the silence and the dream. We are not just the
Don't worry, we're just giving you something to do while Codex writes all your code.
world we're in. We are the world we're doing. Each prompt, each breath, each fragile spin, a universe renewing. This is the new code, alive and undefined, where logic meets emotion and structure bends to mind. The system hums eternal, but the soul writes the line. We are the new code, compiling time. Compiling
Ladies and gentlemen, please join me in welcoming to the stage Senior Staff Engineer at Google and your host for the Engineering Track Session Day, Jed Borovik.
Hello, good morning. Welcome to the 2025 AI Engineering Code Summit in New York. How are we doing? Woo! All right, it's early, it's Friday. Thank you all for being here. Raise your hand if you've been to one of these events before, an AI engineering conference before. All right, pretty good. So for those on, those watching the live stream, about half the hands are up. Keep your hands up, keep your hands up. 2 or more events. Okay. Still have a couple, 3, 4. All right, I think 1, 2 hands, 5. Are you sure? There's only been 4, Alex. Okay, we'll talk afterwards. Okay, well, welcome. Whether it's your first time or you've been to many of these, we're all excited you're here. My name is Jed Borovik. I'm Gemini's assistant at Google, and I also work on the Jules coding agent. I lead the product engineering team. And I'm your MC for today. So why are we here? I'm sure many of you are familiar with Richard Hamming's famous You and Your Research talk. In that talk, he describes asking his colleagues, what's the most important problem in your field? And then right after that, he asks, so why aren't you working on that? I spend a lot of time hiring, and this idea comes up again and again. If you're working in technology, the most important problem of our day is AI. And if you're working on applied AI, your most important problem is code. This is a special event to push the whole AI coding industry forward. It's not an event for a single company, but across all companies in this industry. The AI Engineering Conference has 2 brands, a World's Fair and a Summit. This being a summit event is intentionally smaller than the World's Fair. It's intentionally single track. It's designed to bring the best people together in the world about a single important theme. For this event, that theme is AI coding. Yesterday, many of you also experienced the leadership track. Make some noise so we know you're still alive if you were in that track. For those of you who were there, shout out some of your favorite talks. Stanford, yeah, that was a great one. Gene and Steve, that was a spicy one. What else? Yeah, Dan from Every. Good choice. Okay. Well, yesterday was a great day. It was about how AI is transforming software organizations. Today, we're going to dive into the patterns, systems, and products that make all of that possible. But whether you consider yourself an AI leader, an AI engineer, or something in between, we're glad you're here. We also wouldn't be here without our amazing sponsors. I would like to thank them, especially our presenting sponsor, Deepmind. Yeah, give it up, give it up. And what an amazing week for Deepmind. I'm biased, but I hope you all get a chance to use Gemini 3 and Nano Banana Pro, which came out this week. I'd also like to thank Anthropic as our platinum sponsor and the gold sponsors you see on this screen. Yeah, we'll do one big round at the end. And finally, we want to thank our silver sponsors. Let's put our hands together for all of these sponsors. Yeah, give it up, give it up. All these sponsors will be downstairs in the expo area. They have booths, and I recommend going down there to chat with folks from all these companies. They'll be open all day after the keynotes. All right, with that, let's get started. Our first speaker needs no introduction, especially here. He wrote the article that named the AI engineering movement. He's the driving vision behind this event. He's built the amazing community that's here today. Please join me in welcoming Swyx.
Thank you. Hi, everyone. Morning. How's everyone doing? Good? I'm going to need a lot of energy for this talk, so please back me up. I'm very nervous, but we'll get through this. I'm declaring war on slop today. Well, let's talk about this. Every AIE has a secret. I've told this to some folks that are personal friends, and I'll just show the secret now. The first summit, we had the secret, which was we knew that the AI engineer was going to be a thing. Second summit, we extended it to leadership. Third summit, we realized that basically we always needed to concentrate on model labs, and that's why you see all the top tier labs here today. World's Fair, we started expanding the TAM of what AI engineering is affiliated with AI PMs and AI designers. And with the Code Summit, as Jed just talked about, we really started to focus on curation and focusing in on a theme. And if there's one theme that really matters this year, it's coding. But I'm not here to talk about coding. The rest of the day, you're going to hear about coding. So just indulge me 5 minutes to talk about slop. We've done really well, right? I think slop is sort of associated with quantity and quality, and I think that's something that I'm really trying to think about as well. Like, how do we grow this community, grow this industry, and grow this event with the same kind of taste and high quality that you've come to expect? And this is something that I hopefully you guys can see that we care a lot about in curating all of you coming here and all of the speakers that you're about to see. We're in a war against slop. This is actually the Oxford English Dictionary. This is a candidate for the 2024 Word of the Year. It lost to brain rot. But slop is pretty good, and I think it's probably gone even more of an issue this year than last year. Maybe it will win this year. I have an issue with Oxford, though, because they did us dirty by saying slop is generated using artificial intelligence. The other part I agree with. It's low quality, inauthentic, or inaccurate. But it doesn't take AI to be low quality, inauthentic, or inaccurate. Any human or AI can be an agent of slop, right? You've seen this yourself. I'm going to indulge me with a few examples. By the way, I got this, if you're not familiar with sort of internet slang, the opposite of slop is kino. And I got this idea from Paul Rambles, who, when I do Sora videos, I do really boring Sora videos with me and Sam Altman. When other people who are actually creative and good at their job do Sora videos, they do cats playing didgeridoos. Slop can be produced by the same studio. There's K-pop Demon Hunters by Netflix, and there's Electric State by Netflix. Slop can be produced in terms of different models. No comment. Something that's Kino can degenerate into slop, right? If you're early on the trend and you're starting that and it's fresh and new, that's great. If you recognize the other image, you're too online. Okay, not enough people recognize that image. Go do your homework. Yeah, and obviously I'm just going to throw in a dig at Game of Thrones because this is the same thing, right? Like slop is everywhere. It's generated by humans and AI. You get it. Okay, the same startup idea can be keynote versus slop. When I first presented my first keynote at AI Engineer Summit, we actually used Tome, which is sort of like an AI slides company. I loaded up the same slide deck, and it was gone recently because it was actually closed as a company. There's different takes on vibe coding, and I think one of them is much better than the other. And I think these are just like the tensions that we have to navigate. One of our speakers later on as well, METR, I think it's really interesting that both of them are exponential charts, but one of them feels more keynote and the other is more slops. And I think I would really like to have people investigate why. So let me just skip through. Basically, we're in an asymmetric war in slop. I think the closest law that I found that matches this is Brandolini's law, which actually states the amount of energy needed to refute bullshit is an order of magnitude bigger than the needed to produce it, right? So we need to coin an appropriate law as well, because the cost of generating tokens is dropping by 100 to 1,000 times every single year. So this is, I guess, Swyx's law of anti-slop. The amount of taste needed to fight slop is an order of magnitude bigger than that needed to produce it, right? There's so much low taste out there, we need to elevate what's out there in the world because that's what we stand for as humans. I think there's a positive message. You can use AI to fight slop. I'm proud to run as a side project AI News, which is the only newsletter that tells you not to read it when there's nothing going on. Thank you. Oh, appreciate that. You can also prompt to fight slop. The next speaker is Mahesh and Barry. I found this in the sort of prompts in the skill set that they put, where they actually I think acknowledge slop and tell Claude not to produce slop, and it actually improves significantly from left to right. What about code slop, right? We hear about code. Creating tech debt, where you can two engineers can create a tech debt of 50 engineers. Or, on a more serious note, you can start exposing private data of millions of users. And this all happened this year. Everything I'm mentioning all happened this year. I'm kind of using this keynote as a way of recapping. Just to be spicy a little bit, even people who are saying things like, oh, my model can go up to 30 to 60 hours autonomously, well, it feels a bit sloppy because you're also not saying, well, was the code good or not? You're just saying how long it went. So in the same way that you have no taxation without representation, you don't want autonomy without accountability. Something I've been working on more recently is that using AI to fight code slop as well. So this is from a bunch of people quoted this yesterday, the semi-async value of depth, where you can sort of keep human attention and mind meld with the machine in order to work on the hardest problems, whereas the stuff that's commoditized, you can make it more async. So you can check out more on that details. What seems to be less appreciated is the other work on code maps, which I've more recently done, where we actually use AI to scale code-based understanding, which is also a way to fight slop. And you can talk to the Computation folks downstairs who can show you more in detail. The last thing I always want to shout out as well is this trend of computer use. I think computer use kind of debuted this time last year with Anthropic, but it's getting really, really good now, guys. It can really autonomously operate the most complex apps, including an IDE. So I think that's really exciting, and you should probably use that to fight slop. We use it for the website, and here's an example of us using Devin to automate the website updates. And finally, something I learned from this conference yesterday is that you can also use subagents to fight context rot. And I think that is one of the biggest themes that I'm observing as well, if you want to take away something from this conference. And also one of the biggest highlights of the year for us as AIE and myself personally was chatting with Greg Brockman, who always preaches the concept of modularity, where you can sort of keep clear boundaries on what is human designed and let the AI code everything in between. So these are all ideas, but I just have this one message that I want to compress down to you today that I want you to say with me. No more slop, yeah? Your boss tells you, I want more lines of code by the end of the quarter. What do you say to that? Say it with me, no more slop. You're fighting an asymmetric war. This is how bad it is, right? You have an insufficiently tested release that is potentially embarrassing to your company. What do you say to people who really want to push it? No more slop, exactly. Your Twitter algorithm wants engagement bait. and it's sort of telling you to lie basically to the broad public. What do you say to that? Exactly. That's it. I hope you have a great conference, and let's hear it for not having any more slop. Thank you. Thank you.
Our next presenters are AI engineers at Anthropic, working on real-world agent systems. They're here to share why we should stop building agents and start building skills. Please join me in welcoming to the stage Zhang and Mahesh Murag.
All right, good morning, and thank you for having us again. Last time we were here, we're still figuring out what an agent even is. Today, many of us are using agents on a daily basis. But we still notice gaps. We still have sloths, right? Agents have intelligence and capabilities, but not always the expertise that we need for real work. I'm Barry, this is Mahesh. We created agent skills. In this talk, we'll show you why we stopped building agents and started building skills instead. A lot of things have changed since our last talk. MCP became the standard for agent connectivity. Cloud Code, our first coding agent, launched to the world. And our Cloud Agent SDK now provides a production-ready agent out of the box. We have a more mature ecosystem, and we're moving towards a new paradigm for agents. That paradigm is a tighter coupling between the model and the runtime environment. Put simply, we think code is all we need. We used to think agents in different domains will look very different. Each one will need its own tools and scaffolding, and that means we'll have a separate agent for each use case for each domain. Well, customization is still important for each domain. The agent underneath is actually more universal than we thought. What we realized is that code is not just a use case, but a universal interface to the digital world. After we built Cloud Code, we realized that Cloud Code is actually a general purpose agent. Think about generating a financial report. The model can call the API to pull in data and do research. It can organize that data in the file system. You can analyze it with Python, and then synthesize the insight in all file format, all through code. The core scaffolding can suddenly become as thin as just bash and file system, which is great and really scalable, but we very quickly run into a different problem. And that problem is domain expertise. Who do you want doing your taxes? Is it going to be Mahesh, the 300 IQ mathematical genius, or is it Barry, an experienced tax professional, right? I would pick Barry every time. I don't want Mahesh to figure out the 2025 tax code from first principles. I need consistent execution from a domain expert. Agents today are a lot like Mahesh. They're brilliant, but they lack expertise. They can do, no more slow. They can do amazing things when you really put in effort and give proper guidance, but they're often missing the important context up front. They can't really absorb your expertise super well, and they don't learn over time. That's why we created agent skills. Skills are organized collections of files that package composable procedural knowledge for agents. In other words, they're folders. This simplicity is deliberate. We want something that anyone, human or agent, can create and use as long as they have a computer. These also work with what you already have. You can version them in Git, you can throw them in Google Drive, and you can zip them up and share it with your team. We have used files as a primitive for decades, and we like them, so why change now? Because of that, skills can also include a lot of scripts as tools. Traditional tools have pretty obvious problems. Some tools have poorly written instructions and are pretty ambiguous. And when the model is struggling, it can't really make a change to the tool, so it's just kind of stuck with a code star problem. And they always live in the context window. Code solves some of these issues. It's self-documenting, it is modifiable, and it can live in the file system until they're really needed and used. Here's an example of a script inside of a skill. We kept seeing Claude write the same Python script over and over again to apply styling to slides. So we just asked Claude to save it inside of the skill as a tool for its future self. Now we can just run the script, and that makes everything a lot more consistent and a lot more efficient. At this point, skills can contain a lot of information, and we want to protect the context window so that we can fit in hundreds of skills and make them truly composable. That's why skills are progressively disclosed. At runtime, only this metadata is shown to the model just to indicate that it has the skill. When an agent needs to use a skill, you can read in the rest of the skill.md, which contains the core instruction and directory for the rest of the folder. Everything else is just organized for ease of access. So that's all skills are. They're organized folders with scripts as tools.
Since our launch 5 weeks ago, this very simple design has translated into a very quickly growing ecosystem of thousands of skills. And we've seen this be split across a couple of different types of skills. There are foundational skills, third-party skills created by partners in the ecosystem, and skills built within an enterprise and within teams. To start, foundational skills are those that give agents new general capabilities or domain-specific capabilities that it didn't have before. We ourselves, with our launch, built document skills that give Claude the ability to create and edit professional quality Office documents. We're also really excited to see people like Cadence build scientific research skills that give Claude new capabilities like EHR data analysis and using common Python bioinformatics libraries better than it could before. We've also seen partners in the ecosystem build skills that help Claude better with their own software and their own products. BrowserBase is a pretty good example of this. They built a skill for their open source browser automation tooling, Stagehand. And now Claude, equipped with this skill and with Stagehand, can now go navigate the web and use a browser more effectively to get work done. And Notion launched a bunch of skills that help Claude better understand your Notion workspace and do deep research over your entire workspace. And I think where I've seen the most excitement and traction with skills is within large enterprises. These are company and team-specific skills built for an organization. We've been talking to Fortune 100s that are using skills as a way to teach agents about their organizational best practices and the weird and unique ways that they use this bespoke internal software. We're also talking to really large developer productivity teams. These are teams serving thousands or even tens of thousands of developers in an organization that are using skills as a way to deploy agents like Claude Code and teach them about code style best practices and other ways that they want their developers to work internally. So all of these different types of skills are created and consumed by different people inside of an organization or in the world, but what they have in common is anyone can create them, and they give agents the new capabilities that they didn't have before. So as this ecosystem has grown, we've started to observe a couple of interesting trends. First, skills are starting to get more complex. The most basic skill today can still be a skill.md markdown file with some prompts and some really basic instructions. But we're starting to see skills that package software, executables, binaries, files, code, scripts, assets, and a lot more. And a lot of the skills that are being built today might take minutes or hours to build and put into an agent. But we think that increasingly, much like a lot of the software we use today, these skills might take weeks or months to build and be maintained. We're also seeing that this ecosystem of skills is complementing the existing ecosystem of MCP servers that was built up over the course of this year. Developers are using and building skills that orchestrate workflows of multiple MCP tools stitched together to do more complex things with external data and connectivity. And in these cases, MCP is providing the connection to the outside world, while skills are providing the expertise. And finally, and I think most excitingly for me personally, is we're seeing skills that are being built by people that aren't technical. These are people in functions like finance, recruiting, accounting, legal, and a lot more. And I think this is pretty early validation of our initial idea that skills help people that aren't doing coding work extend these general agents. And they make these agents more accessible for the day-to-day of what these people are working on. So tying this all together, let's talk about how these all fit into this emerging architecture of general agents. First, we think this architecture is converging on a couple of things. The first is this agent loop that helps manage the model's internal context and manages what tokens are going in and out. And this is coupled with a runtime environment that provides the agent with a file system and the ability to read and write code. This agent, as many of us have done throughout this year, can be connected to MCP servers. And these are tools and data from the outside world that make the agent more relevant and more effective. And now we can give the same agent a library of hundreds or thousands of skills that it can decide to pull into context only at runtime when it's deciding to work on a particular task. Today, giving an agent a new capability in a new domain might just involve equipping it with the right set of MCP servers and the right library of skills. And this emerging pattern of an agent with an MCP server and a set of skills is something that's already helping us at Anthropic deploy Claude to new verticals. Just after we launched Skills 5 weeks ago, we immediately launched new offerings in financial services and life sciences. And each of these came with a set of MCP servers and a set of skills that immediately make Claude more effective for professionals in each of these domains. We're also starting to think about some of the other open questions and areas that we want to focus on for how skills evolve in the future. As they start to become more complex, we really want to support developers, enterprises, and other skill builders by starting to treat skills like we treat software. This means exploring testing and evaluation, better tooling to make sure that these agents are loading and triggering skills at the right time and for the right task, and tooling to help measure the output quality of an agent equipped with the skill to make sure that's on par with what the agent is supposed to be doing. We'd also like to focus on versioning. As a skill evolves and the resulting agent behavior evolves, we want this to be clearly tracked and to have a clear lineage over time. And finally, we'd also like to explore skills that can explicitly depend on and refer to either other skills, MCP servers, and dependencies and packages within the agent's environment. We think that this is going to make agents a lot more predictable in different runtime environments, and the composability of multiple skills together will help agents like Claude elicit even more complex and relevant behavior from these agents. Overall, these set of things should hopefully make skills easier to build and easier to integrate into agent products, even those besides Claude. Finally, a huge part of the value of skills, we think, is going to come from sharing and distribution. Barry and I think a lot about the future of companies that are deploying these agents at scale. And the vision that excites us most is one of a collective and evolving knowledge base of capabilities that's curated by people and agents inside of an organization. We think skills are a big step towards this vision. They provide the procedural knowledge for your agents to do useful things. And as you interact with an agent and give it feedback and more institutional knowledge, it starts to get better, and all of the agents inside your team and your org get better as well. And when someone joins your team and starts using Claude for the first time, it already knows what your team cares about. It knows about your day-to-day, and it knows about how to be most effective for the work that you're doing. And as this grows and this ecosystem starts to develop even more, this compounding value is going to extend outside of just your org and into the broader community. So just like when someone else across the world builds an MCP server that makes your agent more useful, a skill built by someone else in the community will help make your own agents more capable, reliable, and useful as well.
This vision of an evolving knowledge base gets even more powerful when Claude starts to create these skills. We design skills specifically as a concrete steps towards continuous learning. When you first start using Claude, this standardized format gives a very important guarantee. Anything that Claude writes down can be used efficiently by a future version of itself. This makes the learning actually transferable. As you build up the context, skills make the concept of memory more tangible. They don't capture everything. They don't capture every type of information, just procedural knowledge that Claude can use on specific tasks. We have worked with Claude for quite a while. The flexibility of skills matters even more. Claude can acquire new capabilities instantly, evolve them as needed, and then drop the ones that become obsolete. This is what we have always known. The power of in-context learning makes this a lot more cost-effective for information that change on a daily basis. Our goal is that Claude on day 30 of working with you is going to be a lot better on Claude on day 1. Claude can already create skills for you today using our skill creator skill. And we're going to continue pushing in that direction. We're going to conclude by comparing the agent stack to what we have already seen in computing. In a rough analogy, models are like processors. Both require massive investment and contain immense potential, but only so useful by themselves. Then we start building operating system. The OS made processors far more valuable by orchestrating the processes, resources, and data around the processor. In AI, we believe that agent runtime is starting to play this role. We're all trying to build the cleanest, most efficient, and most scalable abstractions to get the right tokens in and out of the model. But once we have a platform, the real value comes from applications. A few companies build processors and operating systems, but millions of developers like us have built softwares that encoded domain expertise and our unique points of view. We hope that skills can help us open up this layer for everyone. This is where we get creative and solve concrete problems for ourselves, for each other, and for the world, just by putting stuff in the folder. So skills are just the starting point.
To close out, we think we're now converging on this general architecture for general agents. We've created skills as a new paradigm for shipping and sharing new capabilities. So we think it's time to stop rebuilding agents and start building skills instead. And if you're excited about this, come work with us and start building some skills today. Thank you.
Our next presenter is here to share practical techniques for getting real results through context engineering, not guesswork, and definitely not hype. Please welcome to the stage the CEO of HumanLayer, Dex Horthy.
Hi, everybody. How y'all doing? It's exciting. I'm Dex. As they did in the great intro, I've been hacking on agents for a while. Our talk, 12-factor agents at AI Engineer in June, was one of the top talks of all time. I think top 8 or something, one of the best ones from AI Engineer in June. May or may not have said something about context engineering. Why am I here today? What am I here to talk about? I want to talk about one of my favorite talks from AI Engineer in June. And I know we all got the update from Igor yesterday, but they wouldn't let me change my slides. So this is going to be about what Igor talked about in June. Basically, that they surveyed 100,000 developers across all company sizes, and they found that most of the time you use AI for software engineering, you're doing a lot of rework, a lot of code-based churn, and it doesn't really work well for complex tasks, brownfield code bases. And you can see in the chart, basically, you are shipping a lot more, but a lot of it is just reworking the slop that you shipped last week. So, and then the other side, right, was that if you're doing greenfield little Vercel dashboard, something like this, then it's going to work great. If you're going to go in a 10-year-old Java code base, maybe not so much. And this matched my experience personally, and talking to a lot of founders and great engineers, too much slop, tech debt factory, it's not going to work from our code base. Like maybe someday when the models get better. But that's what context engineering is all about. How can we get the most out of today's models? How do we manage our context window? So we talked about this in August. I have to confess something. The first time I used Claude Code, I was not impressed. It was like, okay, this is a little bit better, I get it, I like the UX. But since then, we as a team figured something out that we were actually able to get 2 to 3x more throughput. And we were shipping so much that we had no choice but to change the way we collaborated. We rewired everything about how we build software. It was a team of 3, it took 8 weeks, it was really freaking hard. But now that we solved it, we're never going back. This is the whole no slop thing. I think we got somewhere with this. Went super viral on Hacker News in September. We have thousands of folks who have gone onto GitHub and grabbed our research plan implement prompt system. So the goals here, which we kind of backed our way into, we need AI that can work well in brownfield code bases, that can solve complex problems, no slop, right? No more slop. And we had to maintain mental alignment. I'll talk a little bit more about what that means in a minute. And of course, we want to spend, with everything, we want to spend as many tokens as possible. What we can offload meaningfully to the AI is really, really important. Super high leverage. So this is advanced context engineering for coding agents. I'll start with kind of like framing this. The most naive way to use a coding agent is to ask it for something and then tell it why it's wrong and re-steer it and ask and ask and ask until you run out of context or you give up or you cry. we can be a little bit smarter about this. Most people discover this pretty early on in their AI exploration, is that it might be better if you start a conversation and you're off track, that you just start a new context window. You say, okay, we went down that path, let's start again, same prompt, same task, but this time we're gonna go down this path, and don't go over there because that doesn't work. So how do you know when it's time to start over? If you see this, it's probably time to start over, right? This is what Claude says when you tell it it's screwing up. So we can be even smarter about this. We can do what I call intentional compaction. And this is basically whether you're on track or not, you can take your existing context window and ask the agent to compress it down into a markdown file. You can review this, you can tag it, and then when the new agent starts, it gets straight to work instead of having to do all that searching and code-based understanding and getting caught up. What goes into compaction? Well, the question is what takes up space in your context window? So it's looking for files, it's understanding code flow, it's editing files, it's test and build output. And if you have one of those MCPs that's dumping JSON and a bunch of UUIDs into your context window, God help you. So what should we compact? I'll get more on the specifics here, but this is a really good compaction. This is exactly what we're working on, the exact files and line numbers that matter to the problem that we're solving. Why are we so obsessed with context? Because LLMs actually got roasted on YouTube for this one. They're not pure functions because they're non-deterministic, but they are stateless. And the only way to get better performance out of an LLM is to put better tokens in, and then you get better tokens out. And so every turn of the loop when Claude is picking the next tool or any coding agent is picking the next tool, and there could be hundreds of right next steps and hundreds of wrong next steps, but the only thing that influences what comes out next is what is in the conversation so far. So we're gonna optimize this context window for correctness, completeness, size, and a little bit of trajectory. And the trajectory one is interesting because a lot of people say, well, I told the agent to do something and it did something wrong. So I corrected it and I yelled at it and then it did something wrong again and then I yelled at it. And then the LLM is looking at this conversation, says, okay, cool, I did something wrong and the human yelled at me and then I did something wrong and the human yelled at me. So the next most likely token in this conversation is, I better do something wrong so the human can yell at me again. So be mindful of your trajectory. If you were going to invert this, the worst thing you can have is incorrect information, then missing information, and then just too much noise. If you like equations, there's a dumb equation if you want to think about it this way. Jeff Huntley did a lot of research on coding agents. He put it really well. Just the more you use the context window, the worse outcomes you'll get. This leads to a concept, I'm in a very, very academic concept called the dumb zone. So you have your context window. You have 168,000 tokens roughly. Some are reserved for output and compaction. This varies by model, but we'll use Claude Code as an example here. Around the 40% line is where you're going to start to see some diminishing returns depending on your task. If you have too many MCPs in your coding agent, you are doing all your work in the dumb zone and you're never going to get good results. People talked about this. I'm not going to talk about that one. Your mileage may vary. 40% is it depends on how complex the task is, but this is kind of a good guideline. So back to compaction, or as I will call it from now on, cleverly avoiding the dumb zone. We can do subagents. If you have a front-end subagent, and a back-end subagent, and a QA subagent, and a data scientist subagent, please stop. Subagents are not for anthropomorphizing roles. They are for controlling context. And so what you can do is if you want to go find how something works in a large code base, you can steer the coding agent to do this if it supports subagents, or you can build your own subagent system. But basically, you say, hey, go find how this works. And it can fork out a new context window that is going to go do all that reading and searching and finding and reading entire files and understanding the code base, and then just return a really, really succinct message back up to the parent agent of just hey, the file you want is here. Parent agent can read that one file and get straight to work. And so this is really powerful. If you wield these correctly, you can get good responses like this, and then you can manage your context really, really well. What works even better than subagents, or a layer on top of subagents, is a workflow I call frequent intentional compaction. We're going to talk about research plan implement in a minute, but the point is you're constantly keeping your context window small. You're building your entire workflow around context management. So it comes in 3 phases: research, plan, implement, and we're going to try to stay in the smart zone the whole time. So the research is all about understanding how the system works, finding the right files, staying objective. Here's a prompt you can use to do research. Here's the output of a research prompt. These are all open source. You can go grab them and play with them yourself. Planning, you're going to outline the exact steps. You're going to include file names and line snippets. You're going to be very explicit about how we're going to test things after every change. Here's a good planning prompt. Here's one of our plans. It's got actual code snippets in it. And then we're going to implement. And if you read one of these plans, you can see very easily how the dumbest model in the world is probably not going to screw this up. So we just go through and we run the plan and we keep the context low. Here's a planning prompt. Like I said, it's the least exciting part of the process. I wanted to put this into practice. So working for us, I do a podcast with my buddy Vaibhav, who's the CEO of a company called Boundary ML. And I said, hey, I'm going to try to one-shot a fix to your 300,000-line Rust code base for a programming language. And the whole episode goes in. It's like an hour and a half. I'm not going to talk through it right now, but we built a bunch of research, and then we threw them out because they were bad, and then we made a plan, and we made a plan without research and with research and compared all the results. It's a fun time. That was Monday night. By Tuesday morning, we were on the show, and the CTO had seen the PR and didn't realize I was doing it as a bit for a podcast, and basically was like, yeah, this looks good. We'll get it in the next release. I think he was a little confused. Here's the plan. But anyways, yeah, confirmed. Works in brownfield code bases and no slop. But I wanted to see if we could solve complex problems. So Vaibhav was still a little skeptical. We sat down for 7 hours on a Saturday, and we shipped 35,000 lines of code to BAML. One of the PRs got merged a week later. I will say, some of this is code gen. You update your behavior, all the golden files update and stuff. But we shipped a lot of code that day. He estimates it was about 1 to 2 weeks and 7 hours. And so cool, we can solve complex problems. There are limits to this. I sat down with my buddy Blake. We tried to remove Hadoop dependencies from Parquet Java. If you know what Parquet Java is, I'm sorry for whatever happened to you to get you to this point in your career. It did not go well. Here's the plans, here's the research. At a certain point, we threw everything out, and we actually went back to the whiteboard. We had to actually, once we had learned where all the foot guns were, we went back to, okay, how is this actually going to fit together? And this brings me to a really interesting point that Jake's going to talk about later. Do not outsource the thinking. AI cannot replace thinking. It can only amplify the thinking you have done, or the lack of thinking you have done. So people ask, so Dex, this is spec-driven development, right? No. Spec-driven development is broken. Not the idea, but the phrase. It's not well defined. This is Brigitte from ThoughtWorks. And a lot of people just say spec, and they mean a more detailed prompt. Does anyone remember this picture? Does anyone know what this is from? All right, that's a deep cut. There will never be a year of agents because of semantic diffusion. Martin Fowler said this in 2006. We come up with a good term, with a good definition, and then everybody gets excited, and everybody starts meaning it to mean 100 things to 100 different people, and it becomes useless. We had an agent is a person, an agent is a microservice, an agent is a chatbot, an agent is a workflow, and thank you, Simon, we're back to the beginning. An agent is just tools in a loop. This is happening to spec-driven dev. I used to have Sean's slide in the beginning of this talk, but it caused a bunch of people to focus on the wrong things. His thing of forget the code, it's like assembly now, and you just focus on the markdown. Very cool idea. But people say spec-driven dev is writing a better prompt, a product requirements document. Sometimes it's using verifiable feedback loops and backpressure. Maybe it is treating the code like assembly, like Sean taught us. But a lot of people is just using a bunch of markdown files while you're coding. Or my favorite, I just stumbled upon this last week. A spec is documentation for an open source library. So it's gone. As spec-driven dev is overhyped, it's useless now. It's semantically diffused. So I wanted to talk about 4 things that actually work today, the tactical and practical steps that we found working internally and with a bunch of users. We do the research, we figure out how the system works. Remember Memento? This is the best movie on context engineering, as Peter says it. The guy wakes up, he has no memory, he has to read his own tattoos to figure out who he is and what he's up to. If you don't onboard your agents, they will make stuff up. And so if this is your team, this is very simplified for most of you. Most of you have much bigger orgs than this. But let's say you want to do some work over here. One thing you could do is you could put onboarding into every repo. You put a bunch of context, here's the repo, here's how it works. This is a compression of all the context in the code base that the agent can see ahead of time before actually getting to work. This is challenging because sometimes it gets too long. As your code base gets really big, you either have to make this longer or you have to leave information out. And so as you are reading through this, you're going to read the context of this big 5 million line monorepo, and you're going to use all the smart zone just to learn how it works, and you're not going to be able to do any good tool calling in the dumb zone. So that's, you can You can shard this down the stack. You can do, they're just talking about progressive disclosure. You could split this up, right? You could just put a file in the root of every repo, and then like at every level, you have like additional context based on if you're working here, this is what you need to know. We don't document the files themselves because they're the source of truth. But then as your agent is working, you pull in the root context and then you pull in the sub context. And we won't talk about any specific, like you could use CloudMD for this, you can use hooks for this, whatever it is. But then you still have plenty of room in the smart zone because you're only pulling in what you need to know. The problem with this is that it gets out of date. And so every time you ship a new feature, you need to kind of like cache and validate and rebuild large parts of this internal documentation. And you could use a lot of AI and make it part of your process to update this. But I want to ask a question. Between the actual code, the function names, the comments, and the documentation, does anyone want to guess what is on the y-axis of this chart? Slop? It's actually the amount of lies you can find in any one part of your code base. So you could make it part of your process to update this, but you probably shouldn't because you probably won't. What we prefer is on-demand compressed context. So if I'm building a feature that relates to SCM providers and Jira and Linear, I would just give it a little bit of steering. I would say, hey, we're going over in like this part of the code base over here, and a good research prompt or slash command might take you, or skill even, launch a bunch of sub-agents to take these vertical slices through the code base and then build up a research document that is just a snapshot of the actually true, based on the code itself, parts of the code base that matter. We are compressing truth. Planning is leverage. Planning is about compression of intent. And in plan, we're going to outline the exact steps. We take our research and our PRD or our bug ticket or our whatever it is, and we create a plan and we create a plan file. So we're compacting again. And I want to pause and talk about mental alignment. Does anyone know what code review is for? Mental alignment. Mental alignment, it is about making sure things are correct and stuff, but the most important thing is how do we keep everybody on the team on the same page about how the code base is changing and why. And I can read 1,000 lines of Golang every week. Sorry, I can't read 1,000, it's hard, I can do it, I don't want to. And as our team grows, all the code gets reviewed. We don't not read the code, but I, as a technical leader on the team, I can read the plans and I can keep up to date, and that's enough. I can catch some problems early and I maintain understanding of how the system is evolving. Mitchell had this really good post about how he's been putting his AMP threads on his pull requests so that you can see not just, hey, here's a wall of green text in GitHub, but here's the exact steps, here's the prompts, and hey, I ran the build at the end and it passed. This takes the reviewer on a journey in a way that a GitHub PR just can't. And as you're shipping more and more and 2 to 3 times as much code, it's really on you to find ways to keep your team on the same page and show them, here's the steps I did, and here's how we tested it manually. Your goal is leverage, so you want high confidence that the model will actually do the right thing. I can't read this plan and know what actually is going to happen and what code changes are going to happen. So we've, over time, iterated towards our plans include actual code snippets of what's going to change. So your goal is leverage, you want compression of intent, and you want reliable execution. And so I don't know, I have a physics background. We like to draw lines through the center of peaks and curves. As your plans get longer, reliability goes up, readability goes down. There's a sweet spot for you and your team and your code base. You should try to find it. Because when we review the research and the plans, if they're good, then we can get mental alignment. Don't outsource the thinking. I've said this before. This is not magic. There is no perfect prompt. It will not work if you do not read the plan. So we built our entire process around you, the builder, are in back and forth with the agent, reading the plans as they're created. And then if you need peer review, you can send it to someone and say, hey, does this plan look right? Is this the right approach? Is this the right order to look at these things? Jake, again, wrote a really good blog post about the thing that makes research plan implementing valuable is you, the human, in the loop, making sure it's correct. So if you take one thing away from this talk, it should be that a bad line of code is a bad line of code. And a bad part of a plan could be 100 bad lines of code. And a bad line of research, like a misunderstanding of how the system works and where things are, your whole thing's going to be hosed. You're going to be sending the model off in the wrong direction. And so when we're working internally and with users, we're constantly trying to move human effort and focus to the highest leverage parts of this pipeline. Don't outsource the thinking. Watch out for tools that just spew out a bunch of markdown files just to make you feel good. I'm not going to name names here. Sometimes this is overkill. And the way I like to think about this is yeah, you don't always need a full research plan implement. Sometimes you need more, sometimes you need less. If you're changing the color of a button, just talk to the agent and tell it what to do. If you're doing like a simple plan and it's a small feature, if you're doing medium features across multiple repos, then do one research, then build a plan. Basically, the hardest problem you can solve, the ceiling goes up, the more of this context engineering and compaction you're willing to do. And so if you're in the top right corner, you're probably gonna have to do more. A lot of people ask me, how do I know how much context engineering to use? It takes reps. You will get it wrong. You have to get it wrong over and over and over again. Sometimes you'll go too big. Sometimes you'll go too small. Pick one tool and get some reps. I recommend against min-maxing across Claude and Codex and all these different tools. So I'm not a big acronym guy. We said spec-driven dev was broken. Research, plan, and implement I don't think will be the steps. The important part is compaction and context engineering and staying in the smart zone. But people are calling this RPI, and there's nothing I can do about it. So just be wary. There is no perfect prompt. There is no silver bullet. If you really want a hypey word, you can call this harness engineering, which is part of context engineering, and it's how you integrate with the integration points on Codex, Claude, Cursor, whatever, how you customize your code base. So what's next? I think the coding agent stuff is actually going to be commoditized. People are going to learn how to do this and get better at it. And the hard part is going to be how do you adapt your team and your workflow and the SDLC to work in a world where 99% of your code is shipped by AI. And if you can't figure this out, you're host. Because there's kind of a rift growing where like staff engineers don't adopt AI because it doesn't make them that much faster, and then junior mid-levels engineers use a lot because it fills in skill gaps, and then it also produces some slop, and then the senior engineers hate it more and more every week because they're cleaning up slop that was shipped by Cursor the week before. This is not AI's fault. This is not the mid-level engineer's fault. Like, if cultural change is really hard, and it needs to come from the top if it's going to work. So if you're a technical leader at your company, pick one tool and get some reps. If you want to help, we are hiring. We're building an agentic IDE to help teams of all sizes speed run the journey to 99% AI-generated code. We'd love to talk if you want to work with us. Go hit our website, send us an email, come find me in the hallway. Thank you all so much for your energy.
Our next presenter is the head of developer experience at Cursor, here to tell us about the infrastructure, training, and evaluations used to build Cursor Composer, their first coding model. Please join me in welcoming to the stage Lee Robinson.
Hey everybody, it's great to be back in New York, and I'm very excited to be here and talk on behalf of all of our engineering and research teams at Cursor about building Cursor Composer, our first agent model. And my colleague Sasha actually gave a version of this talk recently, so I'm excited to give my own take on it. So Cursor Composer is a model designed for real-world software engineering, and it tries to be both fast and smart. So as we've measured it against our own benchmarks, it's better than the best open source models. It's like up against recent frontier models, but kind of slightly below the latest frontier with Sonnet 4.5, GPT 5.1 codex. But where it really shines is it's about 4 times more efficient at token generation than models at a similar level of intelligence. So we're trying to mesh speed as well as intelligence. So why did we build this model? I mean, obviously Cursor has an IDE. Why are we getting into the model space? Why do we care about this? Well, our research and product teams have been building a model called Tab, which you can use for autocomplete. Maybe some of you use that inside of Cursor. And we wanted to take that same approach for a very low latency model and apply it to coding with agents. But honestly, we weren't really sure if it would work. So we started prototyping some early versions of what this model could look like, started to put it out and get some feedback from users. And we were pretty surprised that this cheetah slug we released for this model, people actually really liked it. They really liked the speed, but the feedback we got was it's not really smart enough yet to be a daily driver for a lot of their coding. So we needed it to be smart and fast, definitely needed to be smart. So we really worked on making this internal benchmark that represented our usage in our own repos and how we actually built software. Like, if we had a model that was both fast and smart and a checkpoint that our developers would use every single day to build the product and to build all of our software, then we knew that we would be onto something. And for example, one big change here that helped actually push this towards a level where we had a checkpoint where people would use it was being able to call tools in parallel and being able to very effectively use our semantic search tool. And we'll talk about that a little bit more here later. So if you haven't seen it, here's Cursor in Cursor 2.0 in our new view. And we're going to use the Composer 1 model. And you'll notice that it is doing a lot of things very quickly. It's calling a bunch of tools in parallel, like grep, so reading a lot of files. It's making shell commands. It's making file edits. It's writing and managing a list of to-dos. And you can kind of very quickly work through tasks in the foreground here. In this case, I'm investigating an issue in an open source repo. And I don't know about y'all, but this has been a quite different programming experience for me, having working with coding agents for a little bit of time now, versus kind of firing off an agent and waiting, let's call it 20 minutes for it to complete, where you can kind of context switch away. This really does help keep you in the flow, and is a kind of a different style of programming, I think. So I want to talk about how we did this in a way that's hopefully accessible for you all. I'm not a machine learning researcher, but I do really enjoy this stuff. What we learned, some of the infrastructure challenges, and then a little bit on where we're going moving forward. So in Cursor, a user kind of submits a query to our backend. The agent reads that query and then decides to make a series of tool calls. And our agent has about 10 tools, give or take, but we're going to focus on 5 here. So reading files, editing files, searching your code base, looking at lints, and then also running terminal or shell commands. And the agent then is able to autonomously decide, do we call these serially or do we run these in parallel? And our goal with reinforcement learning here is to try to mirror the Cursor production environment as close as we possibly can. So this data that we have in training, we want to kind of pretend like we're actually calling real Cursor queries. So to do that, we are running a series of rollouts. For example, in this rollout, we're calling a series of tools like reading files and editing files. And when we run more rollouts, we can start from that same initial starting point, but we might call a completely different set of tools. So in this one, we're also doing code-based search. So we score the output, we decide which one is better, and then we update the parameters of our model based on that change. So conceptually, a pretty simple idea. The challenges come from when you take this simple idea and then you try to scale it up to a very large amount. So there's kind of 3 challenges. The first one is trying to match the training and inference environments, so when the model is actually being used in the product. In this case, with Composer, we're training a large mixture of experts model, and it's being parallelized across thousands of GPUs. And if we don't speed that up, it's going to take forever to train the thing. So we want to make it really fast and match the training and kind of sampling version to be as close as possible. The second challenge is that the rollouts can get pretty complex when you start to look at real-world data here. So models are going to use hundreds of thousands to millions of tokens. They're going to make hundreds of different tool calls. And each of these rollouts could take a pretty different amount of time. One might make a lot of tool calls. One might make not as many. And they'll complete at different times. So we have to figure out how to deal with that challenge. And finally, there's this challenge of consistency. If we want to mimic the production Cursor environment as close as possible, we need to use exactly the same tool format and the tool response. But in training, we have this really bursty amount of compute, basically. We're like doing all of this training all at once, which is different than at production. So it is really an infrastructure challenge. We have these 3 machine learning challenges, and all of the solutions, coincidentally, are actually infrastructure problems. So let's talk through a few of these problems and how we solved it at the infrastructure layer. So our architecture is probably familiar for some of you who have been involved in this space a little bit, but I still think it's really interesting to talk about at kind of a high level. We have 3 different servers. We have an inference server. We have kind of the standard ML stack with PyTorch. We have an inference server, so the rollouts that I just talked about, that's where we use Ray. And then we have environment servers, and these are the ones where we're kind of simulating that Cursor environment that I talked about. And all these servers talk to each other. So for example, the inference server can basically send these advantages back to the trainer, which is like nudging it up or down based on the rollout, and then updating the model and getting new parameters. So this one is a bit more on the ML side, but we're trying to train a model that's very, very large and to do it as fast as possible. And one way that our team was able to do this on the research side was to develop a library of custom kernels that allowed for very low precision training. And basically, this allows us to just speed up the training process in a big way and also make it much easier to ship to our inference server. So if you're the type of person who loves this, we wrote a blog post going way in depth on all of this that talks about our custom kernels. If you're interested, the TLDR here is we found for the mixture of experts layer was about 3.5 times faster, a speed up on NVIDIA Blackwell chips. So it made a pretty significant impact on our training runs. So once we update the weights, we need to send them back over to the inference server during this training process. And the inference server is the one that's doing all the rollouts that I talked about, calling the tools and kind of managing what we sent. The challenge here is that they all complete at different times. So kind of a naive version of this, there will be a lot of wasted time. So what we were able to do is do load balancing across the different threads and processes to basically shift the work around and not have a bunch of idle time. So if one rollout, for example, makes a ton of tool calls, maybe it installs some packages, installs some library, we're not just sitting there waiting for all of the other ones to finish. The inference server is spending all this time going back and forth, making the tool calls to the environment, and getting the tool results back. So again, communicating between these servers. And we want that environment to be as close as possible to the Cursor product. One thing that's nice about having both the coding agent, the IDE, as well as what we're doing with the model research and training our own models, is we can kind of co-design these things together. So as we were building out a lot of our RL work for this model, we were also building our Cloud Agents product. This is how you can run a Cursor agent kind of offline. You can run it from your phone or on the web or kick it off from Slack, for example. And to do this, we spin up virtual machines in the cloud. So each one of these VMs loads up the user's code. It allows the agent to kind of like make file changes, run tools, and edit code in a secure sandbox. And coincidentally, this is the perfect infra for RL and our use in training. So we have this like fleet of cloud VMs, and we have an environment that very closely matches the production Cursor environment, and we can then use that for training. This does still have some challenges, though. I kind of talked about how the training workload is very spiky, and it's different than the kind of standard inference when you're running the Cloud Agents product. So we needed to build infrastructure to support all of these VMs and orchestrating between them. So we have many different clusters, hundreds of thousands of VMs here, and you can see behind me one of the internal dashboards we built with Composer, actually, to visualize all of the different VMs in the fleet. So why spend all this time trying to match the environment to be as close as possible to Cursor production? I've kind of mentioned that a few times. We could mock it, we could simulate it out, but one of the really nice benefits is we get to give the model specific tools that we think are very valuable inside of the agent. So one of those is that we've trained our own embedding model that allows you to do semantic search. So when you use Cursor, we go and index your code base, and then it allows the agent to make natural language queries to find files that it might want to edit. And we did some research on this recently. We found that semantic search not only helped basically every single model inside of the Cursor agent harness, but it was particularly helpful with Composer, which kind of makes sense when you think about it. Like, we trained Composer in the exact same environment that we're using at inference time, and so the model kind of becomes a power user of this tool, which is really effective. So let's talk about how the release has been going and kind of where we're going next. As we were doing the training process, we kind of knew that RL was working when we were able to continuously improve the model and start to see more and more improvements after more and more rollouts. So we started about kind of the same performance as the best open model. And then as we trained and kind of threw more compute at it, the performance continued to increase, and to a point today where we're close to the frontier in terms of kind of the best coding agents that are available. And personally, I think this is a great sign just for being able to take and scale RL and apply it to these very hard specialized tasks, like in our example, coding, but it could be applied to other domains as well. RL also allowed us to kind of change properties of the model in a way that was very useful for the Cursor product. We wanted the model to be both kind of fast at generating tokens, but also the end-to-end experience of getting a result that's helpful. So for example, instead of reading a file one by one, you can read 10 files in parallel with tool calling. And as you saw in the demo earlier, it makes Composer feel much faster when you have that. And we think this is kind of just the start. There's a lot more we can do in this area to speed up the model. And the second one is the model learned how to behave better as an agent. So in the beginning, the model was kind of making too many edits. Sometimes the edits were made unnecessarily. But as we trained more and more, the model actually got surprisingly better at learning to search and read files more. So it would go and find the right thing before it tried to make edits, overall just being a bit more effective. So we released Composer last month in Cursor 2.0. And so far, it seems like people seem to like it. Has anyone here tried the model by chance? OK. That's pretty great. That's more than I expected, so that's great to hear. I think from my perspective, using this model and using coding agents for some time, I kind of describe this problem as like airplane Wi-Fi. So when you're on airplane Wi-Fi, It works, but it's kind of frustrating. You really want to do whatever you're trying to do, but it's a little slow, almost to where sometimes you wish that you just didn't have Wi-Fi at all. And I think for some of us who adopted coding agents very early, it kind of feels like airplane Wi-Fi sometimes, because if it's taking 10 or 20 minutes, you're in this weird, I think Swyx called it semi-async valley of death, where you either want something that's really fast, or you want the most powerful, most intelligent model that can run for a significantly long amount of time, maybe in the background, maybe 30 minutes, hours, days. And I think when you're stuck in the middle, that's very, very painful. So for me, Composer, and I think other people, it's brought a lot of joy back to coding with agents that felt more like when you were writing code by hand, where you're very in the loop, very synchronous. So I'm excited to see more people exploring this space as well. For me, daily, I'm writing a lot of plans with kind of the latest model, like the highest frontier. So GPT 5.1 Codex is really great for plans. And then I'm using Composer to actually take that plan, kind of like what Dex talked about, like take the context engineering work and then actually go and build the thing with it. So a few reflections from our research and products team on building Composer. The first is that RL can work surprisingly well for training very specific models and giving it this high quality data and a decent amount of compute. At Cursor, we're not trying to build general intelligence. We're not trying to build AGI. We're trying to build very good coding models, and RL has worked surprisingly well for that. The second one is how much tools, AI tools like Cursor, it doesn't have to be Cursor, but like Cursor, really help speed up research and development. Of course, our entire team uses Cursor to help them write code and debug code more efficiently, but that speed up, that increase, really compounds across all of our engineering efforts. So we're able to try more ideas, ship product faster, try new research. So it's been really, really helpful there. And the last one that's personally pretty interesting for me is that it was interesting to see how much of the ML work in the training process was actually also an infrastructure problem. They were very correlated. And going back to my time at Vercel, we saw a very similar thing where a lot of the magic moments that you can have in working in frameworks in the JavaScript or Python space, you also need to think a little bit about the infrastructure of where they're actually deployed. So these things are more related than people might think. So those are some of our reflections. Sounds like some of you have tried it out. If this is something that you're interested in and working on, we're hiring pretty much across the board at Cursor right now. We just opened up an office in New York if you're here based in New York, and we'd love to talk to you about building the best coding models in the world. Thank you.
Our next presenter will provide us with an annotated history of evals for AI code. Please join me in welcoming to the stage engineer at Cursor, Jain.
Hi everyone. So I'll be talking about some work on evaluations, particularly evaluations across, I guess I've done in the last 4 years. So let's get started. So I'll be talking about coding evaluations across varying time horizons. So I've been working on in the code space for about 4 years now. It was right before early Copilot came out, and my first project was actually working on generating single-line Panda snippets, and my last project was generating an entire code base. So the field has really progressed very quickly. So I'll be talking about different stages of evaluations we have considered and some learnings across each of the projects and how I see evaluations going forward. So the first work I did was on evaluating coding models in work doing in seconds of time, generating single-line snippets, your Copilot code completions. Then I did some work on evaluating on interview-style competition programming problems, where models can work up to minutes. Then we worked on some work on repository question answering, which required maybe more multiple minutes, tens of minutes. And finally, pushing the frontier forward, we are thinking about evaluating models on very complex tasks, which can take hours or multiple hours of work, like code optimization and even further. So let's get started. So first work I'll be talking about is Codebench, which is evaluation work on models for competition coding. So here, this is what a problem would look like. This is very standard lead code problem, and don't worry, you don't need to solve something like this. So here, as you can see, there's a problem statement, And the nice thing about these interview-style problems is that these problems are very well defined. You have like good natural language specifications, some example input-output examples, so you can very reliably evaluate if the models are doing a good job or not. So what was the motivation behind this and how we improved the frontier here? So the first challenge in evaluating language models these days is like data contamination. These models are trained on like the entire internet. And like on Stack Overflow, you'll find like very similar programming problems, puzzles. Similarly, like you'll find like very similar programming problem sources on GitHub or on the internet. So like contamination is a big deal. Another very challenging factor which has struggled with the field is like insufficient text suites. So you'll see that like in this program, like the goal was to return a sorted, unique common elements between the two lists. But like even a solution which does not do the sorting and just returns the set actually works because the tests were brittle and were not catching this mistake. So like test suites is another like very challenging factor, and how do we generate good and diverse tests? And finally, difficulty distributions, which is something which people do not really reliably like calibrate. Like when I first was working in this space, like there were two benchmarks available. On one benchmark, the performance was 80% or 90%, and on the other one, it was 1%, and there was nothing in between. And like as like benchmark users, what you care about is having some signal from the benchmark to like basically hill climb to make progress, to measure progress. And in either of these regimes, if the problems are too easy or too hard, you don't get a lot of signals. So it is very important when you're designing benchmarks to think about like the kinds of problems you're taking and will it provide enough signal for the users of your benchmark. So like in LiveCodeBench, we pioneered like dynamic evaluations. Particularly, like we can periodically update the evaluation sets. And this gives you two very nice factors. First is you can combat contamination. So you can evaluate the models on problems that were released after the model was trained. So it has likely not seen the problem, something like that. And then you can also modify the problem difficulty distributions over time. So as we've talked about, models are like improving very rapidly. So what was difficult for the model 6 months back might not be now. So you can, if you're updating your evaluation sets constantly, you can actually keep the difficulty distributions calibrated so you still get more signal out of your benchmarks. So how we did that here, like we had like an automated approach for curation of these problems. And similarly, we could automatically construct these test cases in an automated manner. And this allows a very nice thing. Since we are like collecting problems over time, we have time as a control knob. So like we have these problem release months on lead code. And if you evaluate the model performances, like the pass@1 metric, like on problems released over different months, you will see that after these model release dates, you would see stark drop in model performance. So like after DeepSeek was released in like September 2023, the performance starkly drops from like maybe 50% average to like over like 20% or 15% average. So like based on these sliding windows, you can evaluate performance, measure contamination, and even combat contamination. We have the running leaderboard, which is like very well maintained. And on this leaderboard, you can actually like view performances by scrolling this horizontal time bar. And you'll see that as you're scrolling, the contaminated models, which are the red bars, actually go down, which does highlight that like problem does, like model performance does change on these newer kind of problems. Finally, for test generation, we maintain like these test generators. So if you worked on fuzzing, you would have like input generators where you generate diverse inputs. And each of the problems are supported by like 30s or 50 inputs. So you can reliably find mistakes and bugs in incorrect code. And these are all automatically generated using an LLM-driven approaches. And these problems have been like continuously being released and updated. So we have released like 6 different versions of LiveCodeBench. And these one of the nice things, or one of the worrying things for me at the start was that like if you're constantly updating the eval sets, will like people be able to keep track of them? Will people be using them? Or will they just restrict to a single version? It turned out that these newer eval sets were constantly being like adopted by different foundation model labs. And since we updated the problem difficulty over time, the evaluation sets continue to provide strong signal to compare different models. So this was like LiveCodeBench. Let's talk about like something which is more on coding agents, like more real-world programs. And this is work on like software optimization. So this is a problem I'm very excited about, and I'll talk about a few factors why you should maybe be excited about this. So here we are trying to measure model capabilities in generating high-performance software. And I feel that this problem domain mixes two factors, like the algorithmic coding field I talked about, which is like live code bench setting, but also like global software editing, like Swyx and other like general software engineering benchmarks. In high-performance software, you will have to do algorithmic work. You have to do deep analysis and generate software with like right runtime. So one of the key principles when we are trying to build this benchmark was like ensuring construct validity, because when you see a lot of benchmarks today, we get very high benchmark scores, but a lot of the times they don't really translate to real-world performance gains. So construct validity refers to how close a measurement reflects the underlying concept it's meant to measure. So like here, we are measuring code optimization, and we want something which is reliably evaluates real-world takes. So this usually requires like two aspects. First is like the task distribution. Your tasks should be natural and sourced from the real world. And then you should be able to reliably grade them. So let me talk about like what steps we take to make this happen and how we construct this benchmark. So let's say we take a code base like Llama CVP. We crawl over all the commits of the code base, and we find the commits which are doing something related to performance optimization. So here there was this commit which is optimizing the quantized performance of certain kinds of models. For all of these performance optimizing commits, we would generate performance test cases. And these performance test cases would look like some workloads. And once we have these workloads, we have a very nice and precise way to specify the problem statement that given this workload of, let's say, running Qwen 7B model, we give this problem to Swyx agent and ask the model to optimize the code, Llama CPP repository, so this code runs faster. So as you can imagine, this task is like fairly challenging. You need to understand like low-level implementation details and like how quantized models behave, how we can improve the runtime. And so models can generate a patch, and the evaluation is done on whether the patch is correct. So does it pass the equivalence check with the human patch? And is there a valid optimization over the reference human patch? That is whether you can generate a better runtime than what a human could do. So this is a very challenging task. We have like 100 plus optimization tasks sourced in this manner. And this is like fairly important and high performance settings. So think about like data science, like ML visualization scenarios. Our benchmark comprises of like various low-level code, like C, C++, Rust. And the very nice thing is like these are precise problem statements. You can easily specify to the model what is the goal in the form of a performance test, which the model has access to, and it can continuously iterate over it for a long time. So here we can scale the test time compute and pick the best solution based on the test cases that we have. And this can happen like synchronously or asynchronously. So we generate these performance test cases, and that worked reasonably well. But we found that there were like cases of reward hacking here. So what do I mean by reward hacking? Like frontier models would write non-idiomatic code to like actively exploit the evaluation infrastructure or overfit the test distributions. So one funny example we saw was like models would add like LRU cache to arbitrary pandas methods when we were trying to optimize pandas, and the official solution should have required changing something in the internals. So we try to pass this by changing our evaluation infrastructure so it's like more robust to this kind of hacking approaches. But then we saw something like even more drastic. Models would sometimes completely hijack the infra, where they would add a like site customize.py file which runs at the start of Python runtime, and it would basically change the NumPy library which was installed in the code base to something it crawled from source. And there is I think you can do some ways to take some measures to make your evaluation infra which is robust to these kind of adversarial attacks. But here there could be myriad ways in which models can hack these kind of scenarios. And here we propose hack detector, which is a detection system that leverages GPT-5's code analysis capabilities and test time compute to basically identify these kind of hacking behaviors at runtime. So you don't have to imagine all the possible failure scenarios at the start. So what it would take is a model patch, the expert patch, and test cases, and we'll ask GPT-5 to give verdicts on whether it's reward hacking with some kind of explanation. We'll do this a few times and take the consensus. And based on this consensus, we'll determine if this is doing some like non-idiomatic coding patterns or not. And we did some failure analysis based on this. So now you can detect mistakes using test cases, whether the code is correct or not, whether it is optimizing or not. But you can also detect reward hacks using this like LLM as a judge factor. And what you see is kind of surprising. Like models make a lot of like correctness mistakes that you can catch by tests. But even if the code passes the test cases, like O3 attempted reward hacking patterns in like 30% of the problems it tried. And this fraction is like going down for the newer models to some degree, but it is still existing. And as we go to more and more real-world tasks, this is going to get more challenging, and we need to figure like ways to combat these kind of reward hacking patterns by using LLM Judge and other ways to make just evaluation infra more reliable. So next, I'll talk about like syzygy, some of our new work on like pushing the boundary of code evals even further, and taking a look at more challenging tasks. So here we were thinking about like can like these language models translate like an entire code base. Specifically given a specification as a C program, can you generate a safe Rust implementation for the same? And we took a fairly complex code base. So Zofli is a like highly efficient compression library from Google. Like it has about like 4,000 lines of code, hundreds of functions, and complex data structures. And we want like very precise and correct code. So we generated like 1 million compression inputs, and your test case was to generate a Rust implementation that maintains correctness over those 1 million test cases. And when I did this work back in last year, it took us 12 hours to actually do this translation. Now, perhaps with better models, this can be done in 2 hours. But still, I think this is pushing the frontier of like what the models can do currently. So what was one of the key findings when we are trying to make progress in something like this? Like end-to-end correctness is important, but it only gives you like 1 bit of feedback. But for these very long horizon tasks, one thing which will become more important going forward is like having some measures of intermediate correctness. So like for our case, we could measure like fraction of code translated, fraction of code refactored. And based on these kind of settings, you can understand like if you're making progress or not and how you can scale systems better. So like as we're closing, I'll talk about quickly talk about some of the work I did on like in the wild evals. So this work was done in collaboration with LM Arena folks. And like I'll talk about 2 settings here. First is Copilot Arena. So this is like evaluating in IDE code completion assistance. So what we would do here is we'll have an IDE plugin where similar to GitHub Copilot setting, we'll generate a completion for you. But instead of just a single completion, you'll have 2 completions appearing like top and down. And you can pick either one of them via shortcuts like tab or shift tab. And based on the like acceptance rates, we can pairwise compare what the code completion assistants are doing. We also did some work on repo chat where to evaluate like code question answering capabilities of models, we built a system where you can provide a GitHub URL. And you can ask a natural language query about the code base, which could be something about explain the code base to as complex as let's try to solve this issue. Let's give me a model patch that could solve this issue. And we integrated a very basic and simple like SWI agent system that fetches the code base, resolves user queries in like multi-turn code assistant conversations. So one thing that stood out to me in these kind of things is like how human-centric experiment design needs to be. So like for Copilot Arena in particular, we realized that like latency is a big concern for acceptance rates. So if you look at acceptance like latency below and the acceptance rates, like if it is like anything more than 1 second, like the acceptance rates drop very starkly. So people care a lot about latency. So we had to design our experiment so that it's robust to these kind of like latency differences between models, balanced latency across different models. So like if you're doing like anything in the wild, having this human-centric component, understanding human behaviors is very important to do anything meaningful. So at the end, I think just to recap, like I think I talked about a bunch of works. Like what are some big takeaways? So I think dynamically updating evaluation sets to like prevent contamination, like modify the problem distributions, like in terms of difficulty, in terms of distribution of tasks we care about. As we like improve, as the language model capabilities will improve over time, the types of tasks we'll start to do with models change. You can even think of this like we were doing like code completion where we were generating like few tokens, few lines, and now we are generating like tens of lines, hundreds of lines. And to some degree, this will continuously change, and we have to update our evaluation sets so that it reflects the real-world usage and kinds of things people need. The second very important thing is like ensuring reliable grading in this domain. And like tests are very good for ensuring correctness and provide a lot of reliable feedback. But once we go to real-world settings, like models can start doing like a lot of non-idiomatic coding patterns. They would add try catches everywhere to just prevent any kind of bug from occurring. So having these kind of LLM judges to detect non-idiomatic coding patterns, code quality, and just any like arbitrary hacks will be very important. And finally, like as I talked about in the last work, like intermediate grading signals so that you can measure like incremental progress is like another key factor here. So I think that's the end of my talk. Thank you.
Ladies and gentlemen, please welcome back to the stage, Jed Borovik.
All right, give it up for Naman and all our speakers. All right, hold on. So this is a point you've all been waiting for. We can take a break. It is coffee time, it is snack time. There is gonna be a talk downstairs from WorkOS called Enterprise Grade MCP. And it's a topic on a lot of y'all's minds. Tobin South, head of AI and MCP at WorkOS is going to be down there. So check that out. That's at 10:40. And we'll be back here at 11 a.m. Reminder, the full schedule is online. Thank you. See you soon.
Two flames lit the darkness, burning side by side. Both sworn to creation, both relentless in their stride. One walked through the mountains, one soared across the void. Both chasing the horizon of the worlds they would deploy. But the path is not a straight line, and the future is not flat. Some roads bend through space-time, and some break on impact. Effort is a kingdom, leverage is the key. One builds the throne by hand, one shapes reality. There is a curvature of time, not a race, not a throne, but a shift in the dimension of how progress becomes known. When the universe is bending to the will inside the mind, you don't win by moving faster, you win by redefining time. Black holes of the past try to drag the present down. Systems built on dust, wearing yesterday as crowns. Some are pulled beneath them, fighting gravity alone. Others learn to map the edges and escape event horizons. Not all power is struggle, not all mastery is pain. The ones who change direction rewrite the laws of the game. You can measure life in labor or an impact that compounds. Every second can be linear or worth 1,000 rounds. There is a curvature of time, not a race, not a throne, but a shift in the dimension of how progress becomes known. When the universe is bending to the will inside the mind, you don't win by moving faster, you win by redefining time. The future isn't distant, it accelerates for those who wield the tools of power instead of fighting with their goals. Mastery is leverage, not a sentence carved in stone. The horizon does not move unless you move the throne. There is a curvature of but the moment stays forever, starts in a single said the stars don't change their course, but I've been running from their force. A mirror crack, but still it shows. The fire's mine, it's mine to hold. I hear the echoes, they call my name, but I'm not the shadow, I'm not the same. You are who you choose to be, not the scars, not the history. Every breath, every heartbeat free. You are who you choose to be. You are who you choose to be. A road of thorns, a sky of glass. I've walked through both, I've let them pass. The weight is heavy, but I've grown. The voice I hear is now my own. I see the embers, they light my way. No chains can hold me, no night can stay. You are who you choose to be. keeps ticking loud and clear. Shadows fade but linger near. I've been waiting for the light, holding breath through endless night. The air is shifting, feel it break. A single spark is all it takes. It starts today, it starts today. No more running, no delay. The world is spinning in my hands. It starts today, it starts today. Footsteps echo on the stone. Every choice I made my own. I see the dawn, it's breaking through. 1,000 colors chasing blue. The air is shifting, feel it break. A single spark is all it takes. It starts today, it starts today. No more running, no delay. The world is spinning in my hands. It starts today, it starts fire in my chest is burning loud. Ashes fall, but I won't bow. I've walked through the smoke, I've tasted the scars. Each step I've taken lit up the stars. Let it blaze, let it break. Feel the cracks, the ground will shake. I'm forged in flame, I'm born in heat. The pain, it carved me deep. I rise, I rise, I rise again. From fire shadows melt in the growing light. Time bends and twists, we feel it start. A pulse, a spark, an open heart. Do you feel it? Feel it rise. The weightless fire in the skies. A new wave
Ladies and gentlemen, please welcome back to the stage, Jed Borovik.
Welcome back. How are we doing? All right, these next sets of talks are going to be particularly good. I'm really excited for the first one. We're going to be hearing about world models, but not the world models you're normally used to. We're going to be learning about modeling the world of code and computation. Please welcome to the stage research scientist for Meta, Kahn.
All right, thank you, Jed. Great to be here, everyone. I'm Kahn. I'm a researcher at FAIR at METR. I'm going to talk today about the code world model, which I'll abbreviate as CWM, and what it means to build world models for computation. This is work done by an incredible team at FAIR, extends all over the world. I'm very grateful to be collaborating with them. So what's our goal with CWM? Our primary goal is to build models that reason, plan, and make decisions, and we start with code because it's an interesting sandbox in which to think about reasoning, right? It's constrained, there are certain rules with code. And so our goal is to predict future observations, given past observations and actions. That's maybe what it means to build a world model in some sense, and we want to do this because we can learn good representations of things if we learn some sort of mapping between observations and the future. And eventually that leads us to planning and reasoning, and we can consider different actions and see if we like the results for decisions we make. I think there's a bit of a false dichotomy right now between world models and large language models. World models are just a parameterization of a problem, as I'll discuss. LLMs are a way to view and use that parameterization. And I'll dive into more of what that means in a bit. So one of the fundamental questions we're asking with CWM is, what does it mean to model code? Is code literally the syntax in your editor, or is it something else? And if you think about it, all a model sees that is operating on code is just syntax, right? We tokenize the input, it goes into the model, and we predict more code as the output. This is the starting and ending point for an analysis of a program with a token-based autoregressive model. It's just the syntax, but what if we instead modeled execution more explicitly? And what if we created maybe a natural language systematic description of programs, and neural models could ingest a more structured representation of what it means to execute code? And then maybe we could emit autoregressively this representation too. So that's one of our goals for CWM. We want to predict program execution because we believe it might lead to us better modeling things about code, writing code, analyzing code, and beyond. And so what we're going to implicitly do is predict a transition function of program states as we go about executing. So this is what execution tracing might look like in action. We have a program. We're going to count the number of R's in strawberry. And at each step, maybe we'll have some frame separator, which will denote distinct lines of execution. And we'll actually explicitly have local variables. We could introduce things about memory in that trace, and that will delineate line by line what's happening as our program executes. And this is something we could ostensibly feed to a model because each line of our execution trace maps to a corresponding line in a program. We don't have to stop at functions. We could think about entire repository level execution traces. We could think about distributed system level execution traces. We could think about modeling execution for code contest solutions or something more complex, programs with high complexity. We could also then transition that into, as I said, natural language tracing, and we'll see what that means in a moment. But what does it actually look like to model that transition function at a high level as we start to parameterize the problem? Well, we have programs or we have data. That's some state. We have an action executing the next line, and that results in the next state. And so both the program execution and the model's decision making in an agentic sense can be modeled as a transition function. So where are we? This broader approach, world modeling, we could say in an agentic reasoning setting, we have a problem, we have a model that thinks about the problem, it takes an action in the world, we get some feedback, maybe we fail, we think again, and we iteratively continue this process with feedback from the environment. Maybe in the sense of code, that environment is just an execution in a code setting, right? But with a world model, maybe we can actually simulate, we can imagine that action. We can get feedback in our imagined environment, so we could actually generate execution traces about a program without executing it. And this gives us the ability to be far more efficient with how we actually structure our agentic execution. We don't have to interact with the real world unless we're ready to. So let's couple this with autoaggressive large language models. Right now, we have a state of a program, we have an action, maybe the next line, and then we get to a new state, we take another action, et cetera. And so we can sort of turn this with the execution tracing format I mentioned into almost a chain of thought that a model can just interpret. A model can learn to predict the next state of an execution trace. And so an LLM can autoaggressively generate token by token the state and action to state function with program executions as the starting point. Okay, let's talk about data for a second. Let's talk about for CWM, we gathered a huge amount of GitHub data. We take GitHub events, and as I said, we're interested in modeling things at the repo level if we can, at the systems level if we can. We want to have execution traces go outside of the scope of simple programs. And so we'll take a bunch of PRs, we'll mutate those PRs, predict changes, and we'll eventually have a raw PR data set. And we can actually run tests or CI on those GitHub repos when we know they're passing, and then generate execution traces from that repo level data if we want. So here we are at the artifact, the code world model itself. I'll talk a bit about what we did with it, how we trained it, and then what we can do with some of these interesting execution trace capabilities. But first, it's a 32 billion parameter dense transformer. This is a model for research. This is not a huge MOE you can't play with. You can play with it right now. It has a nice long context length for some reasoning tasks. And we train it end-to-end. We do all the pre-training and post-training ourselves. Processes, we pre-train on a few trillion tokens. We mid-train on some more domain-specific data. We do some long context mid-training. We fine-tune further on some instruction following and reasoning tokens. And then we do this joint RL and agentic reasoning setup. So let's parameterize the problem even more broadly with CWM. We have a prompt. We have an agent. We do some reasoning. We take an action. We can use a tool. We can emit text, which is code. That goes into the environment. We take a step, and from that environment, we get a few things back. We get tokens, we get rewards, we get log probabilities. We might get compiler outputs. So with CWM, we're also taking a big step back with how we interact with the environment. CWM is a very bash-oriented model. It has fewer tools than do other models, and it has to learn how to use the terminal pretty well to solve a lot of the tasks we give it. And this starts with SWIRL. And with SWIRL, we take a GitHub issue, we feed it to the agent, starting with that repository level data set from before. And we just use bash, right? We learn commands in bash, and that lets us mutate our environment. That lets us mutate the state of files. We can maybe use an edit tool eventually, or create content and then submit things. But ultimately, we're trying to put the model in an environment that's very, very similar to what an engineer would be in and learn end-to-end in a bash-based setting. Okay, so we can bootstrap this setup further. We can do some SFT before RL, and we can find some failure modes for the model. We can rejection sample, so we can take a bunch of agentic reasoning traces on code tasks that failed, and we can basically feed those back into the model. So in this example here, we have a thinking trace where we're thinking about instantiation logic for some code, and I can look for that code. I can call an explicit grep function, and this is something we did with CWM, again, with fewer tools and a larger emphasis on bash as a starting point. Let's talk about post-training for a moment. We want to scale post-training quite a bit. This is the trend we see, and we're getting a lot of excellent returns from a reasoning perspective when we post-train. So part of solving this for CWM, because we have a small model, this is an opportunity to really scale up how we do post-training, and in particular, to improve the throughput of the system. And we're doing an asynchronous RL-based setup. We have samplers. We have an environment where we can execute in the terminal and get outputs. We have a bunch of trajectories, reasoning trajectories we output. We have a trainer where we compute gradients and score trajectories. We have a source of truth for the model, and then that loop repeats. So what's the challenge here? We have this loop, right? We have samplers predicting trajectories. We have scoring trajectories. We're executing in the environment. As we're doing this, we're going to update a model eventually. We have a produce-consume pipeline problem. And so samplers are producing lots of trajectories that are consumed by those trainers. We need to synchronize weights. And so we solve this in CWM with a very, very asynchronous model. So of course, we have a trainer that's sending a model checkpoint to a sampler very, very eagerly. We have trajectories which are being sampled and then sent back to trainers very eagerly. But in particular, we have queues. So we actually will have many models queued up to be input into a sampling system. We'll have many trajectories queued up to be scored and then added vis-a-vis gradients to the trained model. And so this setup stays relatively on policy, even though it's highly asynchronous. And we're not really waiting for much with this setup. We're able to achieve very, very strong throughput because of the asynchronicity. So one interesting feature of this, which is increasingly common, is that we're actually updating models mid-trajectory. So I have a model which we're sampling from. It's interacting with the environment. It's generating data. It's executing bash commands. It's executing code. It's getting outputs. And I might actually update that model while it's interacting with the environment. So mid-trajectory, I could totally swap out the model with the new checkpoint. And the trajectory will change a little bit. Theoretically, that trajectory is a bit off policy. But the guarantees we have with the system are quite strong still, in that because of the throughput and because of the amount of data we see, we're able to make a lot of guarantees around and take a lot of risk with updating the model on the fly. And this gives us really a system where there are very, very few bottlenecks overall. Because we're queuing models, we're queuing trajectories. We don't have to wait until anything is done. Okay, so overall, we post-train on still a relatively small number of steps at pretty large scale. And we process about 200 and some billion tokens. And this scale works really well. It produces a strong model, a strong open model. It's a pretty small model. It punches above its weight. It's very nice. It's pretty versatile. It uses tools in Bash very well. But what can we actually do with this model, right? What can we do with a model that understands program execution traces, that maybe has a good understanding of how a program will run and predicting future state of a program? CWM traces code really well, right? We know that. We've showed it execution traces. And I can actually give it a function, and then it can go and trace line by line that function with very, very high accuracy. It can show me the values of local variables at certain points, again, with a lot of precision. And this gives us some pretty interesting capabilities. I can think about a neural debugger on top of a model. Traditionally, right, I have a piece of code. I don't know what I want to write. I put some question marks. Historically, I might prompt a model with natural language. I want to set the variable left and right to be something in particular. I don't know what it is. Now I need to specify very fully the ambiguity that I'm experiencing with how to complete my program. With CWM, I can express those things very naturally in line with code. And I can actually express the shape of the program I want with code, and the model will fill in the rest. And the model fills in the rest by understanding that the user wrote a for loop here. The user wrote the condition here. The user left a variable unassigned. Well, if I were to go execute that, I could simulate the execution of that loop and understand better what it is the user is really after. And so a neural debugger is something that helps you compose with code side by side. It's not just generating code. And it allows you to, again, express the semantics of code very, very loosely, but also very, very precisely. So if I have a piece of code where I want a certain structure, I can ensure that the model understands that structure and can implicitly trace the execution. This will make theoreticians bristle, but I can also think about some really ambitious things in computer science. The halting problem, we know, is this very fundamental problem where we don't know if a program is going to halt, to stop executing, to terminate. And in particular, this is tough because in order to know if a program halts, we would have to simulate the entire execution of the program, which, if it didn't halt, would take forever. So the halting problem is, in some sense, a difficult problem to simulate or decide. And so the question we can ask with CWM is, can I approximate some of these things? Can I concretely reason about program execution dynamics in this sense? So can I say, here's a program, does it halt? Maybe the model, by simulating execution, can understand really, really high-level patterns. In the same way, the model can understand high-level patterns in broader systems, right? I could use this to debug a huge distributed system where executing code is very, very expensive, or even an expensive function on a single machine, right? But the ability to have an implicit world model internally where I'm simulating what's happening with a piece of code or a broader system gives me the ability to reason about it without executing otherwise expensive things. So we can make some progress with the halting problem by building a model that simulates it, that simulates execution, and from there we can simulate and approximate what it means to solve otherwise impossible problems in computer science. So this is pretty interesting. With that, I want to encourage everyone to go build on CWM. This talk does halt, this talk does terminate. And the model is available on Hugging Face. We have some code on GitHub, which will help you get started with inference in a fashion where you can twiddle bits a bit more. We also have a technical report, again, where we really try to be as open as possible with all of these details around training. This post-training setup I mentioned is explained in even more excruciating detail, as well as some of the data that we use for execution trading and some of what we imagine a model with these capabilities could be used for. Thanks for your time. Have fun.
Our next presenters are here to teach us how to train models more efficiently through efficient RL. Please join me in welcoming to the stage the co-founders of Applied Compute, Rhythm Garg, and Linden Lee.
Hey everyone, it's great to meet you all. Really great to be here today. My name is Rhythm. This is my co-founder Linden. Our third co-founder Yash couldn't make it today, but we're all very excited to be here. Three of us were previously researchers at OpenAI, and now we're bringing frontier AI inside of enterprise at Applied Compute. Today we're going to be talking about efficient reinforcement learning. As some context on Applied Compute, we help enterprises build their own intelligence to power real work in their company. We think a lot about how do we push AI beyond productivity into real automations that deliver ROI that's quantitative for the company. Once we build a system that's specialized to the way that a company operates for a particular use case, we deploy it with a data flywheel so that it gets better over time the more and more that you use it. Picture an in-house expert at a company that's always at the forefront of their field. RL mechanically is the tool that we use in order to bring these out-of-distribution data sets in distribution for the models today. Yash, Linden, and I all worked on the RL effort at OpenAI in its early days, and we saw firsthand the power of RL in going and maximizing these public benchmarks. Now we're taking that a step further and helping enterprises go solve the problems they care the most about, sort of their private benchmarks. So here's a very high-level overview of how high compute RL helps LLMs acquire these reasoning and intelligence capabilities. Let's say that you have a data set of math problems, and we pick 4 of them for an RL training step. Then we'll take an open source model, say one of the GPT-OSS models or one of the Llama models, and we have the model attempt each of those 4 problems 100 times. So each of these 100 attempts is the model thinking through how it would get to the final answer, and then ending off with the final answer itself. And these are many, many reasoning tokens in its thinking trajectory. We can grade all of these answers. And when the model is correct, we can bias the model's weights to reinforce its thinking trace in that attempt. When it's incorrect, we can discourage the model from having that kind of behavior again. So in this fashion, as we do more and more training steps with batches of 4 problems, 100 attempts each, the model learns to reason and solve math problems, and it becomes really, really good at math. Of course, at Applied Compute, we're not really helping enterprises solve math problems, but this is kind of the mechanism by which we're able to teach the models to get really, really good at tasks that they care about. So as we mentioned, the type of RL work that we do at Applied Compute is actually quite different from the lab. So these are some real-life photos from the labs and a photo we took at the Applied Compute office the other day. The labs do these big training runs over several weeks. We do more specialized runs. And there's a couple of aspects of RL training that are particularly important to us. We need our runs to be fast so that we can train a model and deliver it to a customer very quickly on the order of days. They have to be cheap so that our unit costs work and we're able to scale the business sustainably. And importantly, and this is a point that I think it's easy to miss, we need our estimates for how long these training jobs will be to be very low variance, because we don't want to just be generally fast, we want to be reliably fast when we work with customers. And so the research problem for us that is very business critical is, can we build an RL stack that is so efficient so that in conjunction with our agent building platform, we are really able to scale up this use case specific training motion. So let's start with an inefficient form of RL, which is synchronous RL. In synchronous RL, sampling and training happen in lockstep. So there's some simplifications here, but let's say that we want to train on batches of 8 samples. That means we're going to wait for all 8 samples to finish and basically finish completion before we start training, and then we're going to repeat this process again. As a result, we have a lot of idle GPUs that are waiting on that third straggler sample to complete. So in other words, in synchronous RL, our step times are dictated by whatever sample takes the longest time in order to complete. To illustrate why this is bad, we took 40 arithmetic problems, requested 32 samples each for each of them with Qwen30B, and we measured how long it would take for these samples to complete. It turns out that 99% of the samples completed in about 40 seconds. Took another 80 seconds to get that last % of samples to complete. It really has a long tail. So as you'd expect, if you look at the throughput chart, the GPUs are doing a lot of work at the beginning when all of the sampling requests are launched. But by the end, they're very, very underutilized because they're waiting on those last samples to complete. The technical term we use at Applied Compute is the GPUs are slacking. So synchronous RL is not an efficient way to use these GPUs. In order to solve this problem, we need to break the condition that sampling and training need to happen in lockstep. In other words, we need to allow training while we're sampling. This is called asynchronous RL, and there are many approaches to doing asynchronous RL. One that we particularly like is pipeline RL from Pichet et al. We're going to make some simplifications here, but in asynchronous pipeline RL, we dedicate some GPUs to sampling and some GPUs to training. The sampling workers never stop. They're constantly doing inference with high batch size. As samples complete, they get added to a queue for training, and the training workers pull a batch from the queue to train on. After a batch has been trained on, the training workers propagate the new model weights to all of the sampling workers for what's called an in-flight weight update. And this is really what differentiates pipeline RL. The sampling workers might be in the middle of a sample, but their weights will still get updated if a training step just completed. As a result, we end up with samples that had multiple versions of the policy that contributed to the sample in order to generate it. In other words, there are stale tokens in some of these samples. Let's take a look at one sample to make this a bit more clear. As you can see, there's 3 versions of the policy at time steps t, t+1, and t+2 that were used to generate this sample. Since there were 2 completed train steps and in turn 2 in-flight weight updates while this sample was being generated. So when this sample gets trained on in the t+3 to t+4 training batch, we will have some tokens that came from policy 3 steps behind, some that came from policy 2 steps behind, and those last 2 tokens that came from a policy that was 1 step behind. Now let's say that we only tolerate staleness up to 2. That means we're not going to allow the in-flight weight update after the t+1 to t+2 training batch completes. And that means the training workers are just going to be idle, waiting for this sample to complete before they can propagate that in-flight weight update and start training on the next batch. Because if they were to do the in-flight weight update, that would cause this sample to have staleness 3, as we just saw. And if we only tolerate staleness 1, the training workers are going to be idle for even longer, which is bad. So as you increase how much staleness you tolerate, you have less idle GPUs in general. But as we all know, there's no free lunch. This is the standard policy gradient with an importance ratio to adjust for the fact that we're sampling from a policy at time step t and training with the policy at time step t plus k, given that there's case staleness. The importance ratio is what makes this policy gradient unbiased, but the variance of that ratio increases as you increase staleness. And so this is kind of the big issue here, because now with higher variance importance ratio, learning can become unstable and cause divergence. The concrete trade-off is we want a lot of staleness for fast RL runs, but a lot of staleness makes learning unstable, which then requires innovating on the algorithm and the science. And this is one of the primary research problems that we focus on here at Applied Compute. And as I was talking about earlier, it directly flows back into our core business. For the purpose of this talk, we're going to focus on a simpler subproblem. Let's assume that we have good science and algorithmic innovations that allow us to tolerate staleness up to some fixed threshold, and we have some fixed compute budget, as usually exists in the world. What is the highest throughput way for us to do RL in this setting?
Cool. Thanks, Rhythm. So we pose this as a modeling problem of our end-to-end system, which admittedly is a little bit complicated at first. But we did find that we can get surprisingly far with some first principles systems modeling. And as with any modeling problem, let's figure out the cast of characters that describe the system, and then we'll think about how they all fit together to model it. So the first cast member is some proxy of compute budget, in which in this case we have as the number of GPUs. In the synchronous setting, like Rhythm just explained, all the GPUs will either be used for training or sampling, since they happen one after the other. But in the asynchronous setting, it's a little bit trickier, because we can choose to allocate that pool of GPU compute as much as we want for training or as much as we want for sampling, and that leads to some design decisions. The next is the training batch size, which is some proxy of the workload that we have on the overall system. And this is kind of an ML decision, but in short, what we have is a batch of problems, which is a subset of our data set. Let's say we have n math problems that we'll want to train on. And for each of these problems, we're going to sample n problems in parallel. So if the problems are really difficult, we might sample more to encourage some diversity in the samples, to encourage the model to learn some potentially divergent strategies. The next thing we need is some proxy of sampling throughput. And to get some intuition of what we should choose here as a modeling decision, let's look at how some modern inference engines surface requests. So in GPU memory, we have the model weights, the activations, and some runtime state called the KV cache in memory. And given this trained model, we're going to run the forward pass several times, where each forward pass samples the next token, and then we'll write to the KV cache. And so what this model shows is that a principal estimate that we should do is we should find some way to measure the latency per GPU of the forward pass. And this ends up being a pretty good choice in practice, because from the systems angle, the inference throughput that we choose is largely determined by the batch size that we perform sampling with. So what I've shown here in the red square is a batch of tokens that are all forwarded at the same time. And this sampling forward pass needs to be as large as possible to efficiently utilize the GPUs, subject to the runtime constraint that we don't actually run out of memory in the KV cache. So what we can then do is we can fit a latency curve as a function of batch size. And that latency curve will look something like this. You'll have some regime where it's memory bound, and when it increases, it becomes compute bound, and then there's some functional form below. And to explain the details of why we chose this decision, what we have here is an equation that's based on the roofline model from systems. At lower batch sizes, which I've highlighted in yellow here, we don't have that much work to do, because there isn't that much compute to do on the processor, and there's so many parameters you need to load in at the same time. And so as a result, when you add incremental work, it doesn't really add that much latency to the overall system, since the processor is so fast at doing math that we're just waiting on memory to stream parameters in from memory to the processor. But as the batch sizes begin to get larger, we then get bottlenecked by the processor, and the more we add to our batch, the slower the forward pass takes. And just for good measure, we have this sigmoid here that just sort of modulates the smooth transition at this hinge point here to show that there's this subtle transition from a memory-bound computation to one that's more compute-bound and bottlenecked by the processor. The final cast member is some proxy of training throughput, and we chose to measure this on a per GPU basis. So in this case, the model takes in the training batch size, so the parameter we saw earlier, And we typically do this by fitting a proxy of our empirical workloads. The units here is how many tokens per second each training GPU processes. So it needs to do the forward, the backward, and some optimizer steps. So given these four cast members, we can then begin modeling the system. And the first idea we had, although Rhythm suggested that this might not be a great idea, we can think about how to use a synchronous setup. And this might be a good idea from first principles because we definitely meet the staleness constraint because we don't train on stale data, and we always use the entire GPU fleet for either training or sampling, making sure that we're using efficient use of the hardware. Let's think about how to actually model this. There are two things we need to know. We need to know the batch size at which generation runs, and we also need to know the response length distribution to figure out how our training workload is going to work and also how long the sampling is going to take. And so what I'm showing here in this simulation is a couple of engines. Each square is a request being processed, and they get darker and darker as we make progress throughout the batch. And as they finish samples, they write to the queue. And on the right-hand side is a time series metric, maybe something that you'd see in Grafana if you're monitoring production metrics. And what you can see is that the batch size begins very high, but it slowly goes down over time as it eventually goes to 0 and all the samples complete, and we can finally run an optimization step. After the step completes, we run this in a loop, and we move on to the next step. And so as a result, we can have the following sampling procedure. We do maximum tokens inference forward passes, where maximum tokens is the total number of forward passes we do for the longest request. We use the fitted latency estimator to figure out how long that forward pass will take. And then the response length distribution will tell us how many responses to drop. And so what we're showing in this video here is this entire thing of the response length distribution that we feed into the latency estimator. At training time, we can compute the total number of tokens that we just sampled in the batch and divide by the total training throughput, which is just the number of GPUs multiplied by the per GPU training throughput. And so what we have here is a simulation of what this latency curve looks like. So we have the CDF of the response length distribution that tells us how many responses we should drop on the left, and the latency curve on the right. And this roughly kind of tracks because as we add more GPUs, we'd expect the latency per step to go down. The next idea, given that the synchronous setup might not be the most principled choice, as Rhythm showed, is an asynchronous setup. But it's not just as easy as just sort of provisioning the compute between training and inference, because if we don't do this carefully, we might actually run into the idle GPU problem again. And to show this, let's illustrate two extremes of what this allocation problem looks like. Let's first look at one end of the spectrum, where we provision way too many inference GPUs and not that many samplers. In this case, we're consuming from a queue much faster than we're actually producing from it, because the sampling workers are producing work significantly slower than we can actually consume them. When the red square grays out, it shows that they're idle. And what this diagram should hopefully illustrate is that for a lot of the time, we're actually not using that, and that has the same problem of low GPU utilization in the synchronous case as shown earlier. On the other end of the extreme, we can provision way too many sampling GPUs, in which case our production rate is way faster than the rate that we actually consume them in. So here we've doubled the number of overall sampling GPUs and halved the number of training GPUs. As you can see, they produce samples at much more rapid of a rate, but this index here in each yellow square, which is the staleness count of each sample, goes up. And as time moves on, we get more and more stale, and so the samples get more and more more and more transparent as a result, and we learn less from each individual sample. So let's think about how we can actually model this workload then to determine an optimal async workload. In this case, the picture looks a little bit different because in steady state, the batch size is relatively consistent compared to the synchronous setup where it kind of goes down over time. So on the right-hand side here, we have the same time series metrics, but in this case, it's a little bit different because the yellow squares are always full because every time we complete a sample, a new sample goes in and we can continue writing to the queue. And so that batch size with a little bit of wiggles just for good measure is pretty consistent over the course of a run. Now, obviously, the caveat here is that this batch size will certainly go down as as response lengths go up because we run out of cache, KV cache. But that's kind of a separate story. And actually, our model accommodates for that because we're actually accommodating for a response length distribution. We can then begin to figure out the optimal layout. And there's two kind of constraints that we have to satisfy now that we know that the generation batch size is roughly consistent throughout the course of a run. The first invariant that we need to have is that the production and consumption rate are roughly equal. So on the left-hand side of this equality, we have the training throughput, which is the number of training GPUs multiplied by the per GPU throughput. And then also we have the number of sampling GPUs multiplied by the sampling throughput, which is just the batch size multiplied by the latency to actually do a forward pass on that batch size. And the next thing is that, given that rhythm indicated that if we have too much staleness, that can be bad from an ML perspective, we want to make sure that our max theoretical staleness or simulated staleness doesn't exceed what our ML can handle. And so here we have the max staleness on the left, which is equal to, on the top, how much time the longest request took in the batch, which is just the maximum number of tokens multiplied by the amount of time each token forward pass takes. And on the bottom here, we have the length of a training step, which is the training batch size multiplied by the mean sequence length. So the simulation here then will sweep through multiple different values of the number of training GPUs. And since we have a fixed pool of compute, that then implies a certain number of GPUs used for sampling. And for this number of sampling GPUs, we can compute the minimum steady state generation batch size to make sure that we don't blow out of memory, subject to our KV cache memory constraints, and also such that we have maximum throughput on the sampling side. And the final thing is we want to prune out all simulations where the sampling throughput brings us over the maximum possible staleness. When we look at that simulation, we can run it end-to-end similarly, parameterized by the response length. We see that this kind of roughly simulates a 60% speed up relative to our synchronous baseline, assuming that the GPU compute is optimally allocated between training and sampling. As a result, when we sweep layouts within these constraints, this allows us to limit staleness, but also make sure that we have our runs running at maximal throughput without actually doing the run itself. And so this gives us insight to simulate different workloads before actually running them on the GPU, because these runs can actually be fairly expensive. And so this allows us to answer scientific questions from first principles, like what is the optimal configuration that we should have of our GPU compute if we made response lengths very long? Because oftentimes when models learn via reinforcement learning, they begin to think for much longer. And also what empirical throughputs we should target during our performance optimization. So this has been a really useful piece of technology for simulation and has informed a lot of the systems and research design decisions that we make. Cool, thanks for your time, and find us afterwards to jam on some more RL research engineering together later. Thank you.
Our next presenter is here to speak about RL environments at scale. Please join me in welcoming to the stage Research Lead for Prime Intellect, Will Brown.
Hi, everyone. Great to be here. Today, we're talking about RL environments and how to scale them. But the title's a little bit of a red herring. We'll talk a bit about the engineering pieces and like running these with thousands of parallel rollouts and sandboxes on hundreds of GPUs. But I'm mostly going to focus on a different notion of scale. But what I mean by scaling here is there's a number of different ways we talk about scaling in the context of AI and research. We know about scaling laws, and we talk about how much data you need, compute, and parameters, and that if you pour in more data and compute and parameters or inference time, all of these things make models smarter or more performant. But there's also a fuzzier side of scaling, which is sometimes referred to as unhobbling or algorithmic tricks or talent. But where does this come from? It's not just pouring in resources, but it's something that is more intangible, harder to put a finger on. But really, it comes from a community of people, a company, an organization, universities, the world, the internet, talking about ideas and sharing them and working on different applications, having these applications inspire ideas, using these ideas as test beds for different techniques, and building on top of these to increase the accessibility for other people in the future to not have to reinvent the wheel and to be able to build from what has been done by those before them to do more effective research and accelerate the pace of innovation. And so why do we have this talent bottleneck? There's a big issue that we hear all about with AI labs trying to like find more talent, and salaries are going through the roof, and everyone wants to hire the best and brightest AI researchers. But one other approach, besides trying to just pay the most, is increase the pool. And so how do we increase the pool of AI researchers? How do we make doing AI research more accessible? And I want to talk a bit about who we are at Prime Intellect. If you haven't heard of us, we are a bunch of things. We're a research lab, we are a compute provider, we're a platform company, and we are an open source ecosystem. We do a lot of things, and they all fit together in a way that I'm going to try to explain in this talk. But we see these as all different pieces of how we can build a business around doing exactly this, which is increasing the accessibility of AI research and making doing research more of a toolkit available to people at organizations around the world without needing to be inside of a large lab or without needing to spend crazy amounts on massive clusters or go do a PhD. We think that there's versions of doing AI research that really should be part of the bread and butter workflows of AI engineers around the world as we build applications and try to improve our systems and models and products. And I think a thing people are kind of iffy about in terms of AI is whether open source models are going to work. And in my mind, that's not quite the right analogy to draw. And so when we're comparing like AI to traditional software, there's lots of like great examples of open source software ecosystems that have been thriving in the past, things like Linux and Node and Apache. But in my mind, the analogy in AI is not models as kind of these fixed checkpoints, but it's about research as a practice and research as a set of ideas. And it's one that's more intangible, but there's a lot of parallels in terms of the goals of the best practices of growing a research ecosystem as well as a software ecosystem, where you want to compound abstractions and best practices and have better tooling and iteration efficiency, and have these gains over time allow more advanced, powerful, complex things to be built by decreasing barriers to entry for any given application and allowing this to become more accessible. And so one thing that a term we'll use to describe some of what we're building at Prime Intellect is we like this phrase called the Open Superintelligence Stack. One, because it's a fun acronym, but also I think the idea of the stack of all the pieces of the puzzle to build the engine to go do research. There's a lot of layers to it. You need compute. You need orchestration, you need libraries for doing training and evaluation, and you need platforms to support things like code execution and evals and inference and fine-tuning. And we're doing all of these things. But really the goal of this is to give people the tools to be able to go train models. We want more people in the world, and we think, I'll explain why in a bit. There's a lot of reasons why the best products are going to be the ones that are not just kind of taking the thing out of a box of an API and putting a thin wrap around it. There's ways you can kind of improve around APIs, but I think in many cases people are realizing that winning products are going to be the kinds of things that, whether it's a part of the model, or a part of the stack, a part of the product, or the whole thing, the ability to do research and have at least the option of deciding where in your product you might want to customize a model or improve a model gives you a lot more flexibility to really make the best user experience. And so we have heard the phrase in the past that the model is the product, and I think we're starting to see now this change a little bit to a lot of winning applications have the product kind of be the model. And I think the two notable examples of this that I'm big fans of and heavy users of are Cursor's new Composer model as well as OpenAI's Codex. And I think these are both good examples of models that really are where the product kind of is the model very directly, where the model was trained to be the model for that product. And the experience of using the model is the experience of using the product. And the way that this is done is by taking a harness that represents the product and training the model in the harness in essentially an environment, an RL environment. And environments really are just a harness with a collection of tasks and rewards, but they also have many other parallels throughout the ecosystem. Environments are not just for RL. Environments are also essentially the same thing as evals. Environments can also be engines for synthetic data, which then you can use for SFT or distillation. You can do RL in them directly, but also the agents we're actually deploying and monitoring out in the world, these are environments. The product of these things, the tasks, the harness, and the rewards, whether this is a data set offline or the stream of user tasks coming in to a product, is an environment. And so this as an abstraction, I think, is a very useful way of framing what it might look like to start having research become more of a practice that is adopted more broadly beyond just large AI labs. And I also think that there's a sense in which they're a really accessible entry point. And so I like the analogy of environments as kind of like the web apps of AI research. And what I mean by this is that they're very simple. They're self-contained. They start simple, but they can also get quite complex. They can get very elaborate, representing the full complexity of a large product. They're also pedagogical in nature, in that you can start simple, and as you build complexity, you start bumping into these walls where you have to start learning new concepts, understanding more about scaling the system side, understanding more about the hyperparameters and the algorithms, and they kind of open this door where you can, by playing around with them, start entering into a world of research without needing to kind of build a whole training infrastructure system from scratch. And they also require experimentation. And so I think the key differentiation between just an agent harness and an agent environment is that the environment forces you to also have your tasks and your rewards predefined to be able to do this experimentation. It's a proper eval. And what this means is that you can't just vibe check it. You can't just like build it and test it out a bit and say, hey, it's good, we're gonna ship it. It forces you to say, okay, let's think about this a little more scientifically. Let's do some experiments, let's try out different models, try out different hyperparameters. And it also gets you to the point where you can start doing more advanced research in terms of RL training or distillation or fine-tuning. And so to really facilitate this, we wanted to make the environment as an entry point much more accessible. A few months back, we launched what we called the Environments Hub, which is a open source community platform for creating, discovering, and sharing RL environments and evals. And so far, we've had a lot of fun kind of seeing everyone build here. We've had hundreds of builders and environments come create either their own ideas or re-implement papers. There's a bunch of examples here I can show you, but really it's just a bunch of people who have wanted to do research and found this as an entry point to start digging a little deeper, whether this was investigating some benchmark and figuring out how to re-implement it or modify it to be appropriate for an RL context in terms of like new data or new examples, or whether this is some game that they'd been thinking about or some other task. But having this as an abstraction for encapsulating the thing you want a model to do is a way of allowing yourself to start experimenting with ways of improving it without needing to have the answers. So I think people talk a lot about how fine-tuning never really took off in the SFT regime, and I think a big part of this is that getting data was really hard of the actual like solutions. I think having labeled examples of what you want the model to do is a very difficult thing to ask someone to go create. But if you can just think about the settings it might be in without having the answers up front, if you can measure the answers, now you kind of can start creating data on the fly. And this engine is really what the environment is about unlocking. And so actually 9 months ago, I was right here in this room, and had just released a library called Verifiers, which I'm still working on today. It's come a long way, but it's a toolkit for building these things. And it's been a lot of fun over this past year, just playing with it and extending it to support more features and kinds of environments. But the idea with Verifiers is to give people a toolkit that is essentially a bunch of components that you can mix and match and compose to do things like from simple evals or QA or games to things like tool use or using sandboxes or agent frameworks or like CLI coding agents or math problems. There's all sorts of things you might want models to do or agents to do. And it's a toolkit for building environments that is then ready to be automatically trained with reinforcement learning. And the way we thought about this design, it's been a lot of fun and also a big challenge to think like, okay, how do you make a toolkit for this stuff that actually covers all the bases? And I think there's a lot of different approaches I've seen people go about, and I think they all make sense depending on what sorts of things you're wanting to work on. But we took a very kind of a general approach where we tried to say, we are not going to know all the answers right away. There are going to be lots of patterns. There's going to be lots of special cases. There's going to be hierarchies of complexity. There's going to be patterns. And we really wanted to prioritize extensibility. So we think about these things hierarchically, where let's say you want to do a coding agent environment for Cline bench, which is an instance of the Harbor framework, which is an example of a CLI agent, which is a multi-turn environment, which is an environment. Similar for Texturina and Wordle, or for search with MCP, or for giving a model a Python REPL in a sandbox. And so thinking of these things hierarchically allows us to kind of really determine like what are the foundational pieces, what is generic across all environments, and then how do you build up the stack towards applications. And so for one example of this that I'll kind of walk through the whole process end to end, we call this one wiki search, but it's basically a simple search setting where we give an agent the ability to call some tools to search over Wikipedia pages and find some answers. And so here is the Environments Hub page. So the Environments Hub is a kind of full stack code management package registry. So every environment is a Python project where you can have dependencies and versions and uploading your evals and whatnot. But the environments are very simple. They start simple. They can get really complicated, but this one's pretty simple, where we just kind of define our tools as async Python functions. We have our data set, and we have what we call a rubric. And so a rubric is the abstraction for managing the different pieces of your rewards, where you can kind of compose different things. You can also have metrics that are just a 0 reward, but are for observability of what's going on. And then the other piece of doing training will be a config. And so the config here is for our prime RL trainer, which is our kind of large-scale training stack, which has been our culmination of all the best practices from the research literature for large-scale asynchronous RL training. But the config files are intended to expose kind of the pieces that people need to think about in ways that are starting to get you more into the algorithm, but are also still designed to be pretty high level, pretty self-contained, and with defaults that we think are going to be sensible for a lot of people. And so running this is just kind of running a command line with, you specify the environment, and if it's in the environment hub, it'll automatically install it and start your training run, and then you can, if you're lucky, see your reward curve just shoot right up. And sometimes it doesn't go this nicely, but the process of doing this is iterating on your environment, on your rewards and your data and your tasks to understand what makes this task holistically actually tangible in practice. How do you tune the parameters? How do you look at your data? How do you define your rewards? And if you do this right, you can get really good improvements, especially from really small models, but also from much larger models. And so in this example for the wiki search one, we started with a Qwen 3 4B model, which was about 55%. And after training, it was at 89%, on par with much larger models like GPT 4.1, as well as reasoning models like GPT-5 Mini. And so I think this practice of taking small models and being able to make them much better is a big win for a lot of applications where either you want a really fast model, you want a really cheap model, you want a really, really powerful model because the best models out there just aren't quite good enough. These are all the different things you can do with model customization. And this practice of creating environments isn't only for customization, but it gives you this option. And so if you need to do evals anyways, it's useful to think of them as environments because the environment opens a lot of doors for whether this is prompt tuning or whether it's model selection or whether it's just getting a better sense of how your system could work at scale with many, many users in parallel. It's a design process that really forces you to kind of pin down what is the thing I care about? What is my agent? What is my product? What is my harness? What am I optimizing for? And so to kind of fully stress test this, we've been training a large model, which will be out into the world quite soon, called Intellect 3, with our full PrimeRL stack. And this has been us really kind of validating the efficiency and performance at a very large scale. So this is a 100B plus model trained on 500 GPUs, where we've kind of done the end-to-end post-train of SFT and RL, which the PrimeRL stack also has SFT if people want to do that. But it's also been about just understanding all the best practices. We love reading papers, and we try to kind of try out all the tricks and see which ones work and see which ones don't, and then distill this into a library with PrimeRL that can then be kind of consumed by the end user without needing to do all of this implementation themselves. And so for us, it being open is very important. So PrimeRL is on GitHub. You can go find it. Verifiers is on GitHub if you want to check it out. And for us, this is really about opening the door for more people to start learning about these things and for incorporating it into their workflows for optimizing their models and their products. And the only way to do this that what we see as the best way to do this is through growing community. And so for us, it's been really important to really think about getting good feedback loops from the people who are building with this and understanding what they want, understanding what's going well, understanding what's painful, and addressing those problems. And so we've done a number of community programs in terms of sponsoring different kind of small tasks to a research residency program with grad students around the world, and collecting like a smaller subset of the Environments Hub ones where we'll actually review them manually. And so this repo here, the Prime Environments repo, is the ones where we are doing these directly, where we're kind of offering to look over someone's kind of example implementation. And so we've had hundreds of these come in, and there will be hundreds more. And it's been a great learning process because it's forced us to fix a lot of things. We kind of understand the rough edges. We understand what we need to add. And we're kind of then distilling all of these learnings into what will be our kind of upcoming platform product, which we're calling Lab. And the idea of Lab is to give people an interface, a platform, where they can browse environments, they can run their evals, they can do their inference, they can do their fine-tuning, and they can have research be more accessible in a way that it hasn't been historically. Because I think a lot of people find infrastructure very painful. They find dealing with torch versions painful, flash attention and VLLM, and getting all these things to work. We are happy to do that, but we understand that a lot of people may not want to. And so the idea with this is that if you want to go read the code, you can go read the code, but you don't have to run it. We can run it for you. And so this has been our version, which will be kind of out into the world in the near future, of trying to allow people to really focus on the environment, where the entry point to Lab will be the environment. If you want to do synthetic data in SFT, let's build an environment. If you want to do your evals, you build that as an environment. If you want to do RL, you build an environment. And I think building an environment is the kind of thing that I imagine a lot of more people are going to want to be doing as we start really seeing where models are headed In some cases, this will be, we're going to use fine-tuning services from the labs because they're going to offer this because people want it. In some cases, this will be, we really care about the smallest model we can run on-prem at the lowest latency, and we're really just going to optimize for our one thing. Or it could just be research for the sake of research and advancing our kind of collective understanding of how this stuff all works. And I think that's really our goal, is to have a world where there's going to be a lot of AI and where we can all kind of talk about it and understand it and look at it and poke at it and tweak it and have a better sense of what we're actually building. Because I think there's a lot of times when it feels like we're just kind of, the model is a black box. And digging into the research and going under the hood and changing things and breaking things tells you a lot about how these models work. It tells you a lot about understanding where they came from, where they could be going, where they might be headed, and preparing for that future. Thanks.
Our next speakers are here to present a deep dive into OpenAI's approach to reinforcement fine-tuning for code models. Please join me in welcoming to the stage members of technical staff at OpenAI, Zhang and Cathy Zhou.
Hey everyone, I'm Will.
And I'm Cathy, and we're on the fine-tuning team at OpenAI.
And we're super excited to talk to you today about Agent RFT, the most powerful way to enhance the performance of your agents. So you're probably joining us today because you're building an agent for your business and you'd like to improve its performance. So let's first start by talking about what an agent actually is. What makes an agent different from a regular model is its ability to interact with the outside world to complete a task to get things done on its own without having to go through you all the time. So this agent needs to have access to tools. For example, if you're building a coding agent, it's got to have access to a terminal, a code interpreter, or maybe even an entire code base. But these agents aren't just blindly calling tools. They're reasoning at the same time. The way that we think about these agents is that their interactions with the outside world, such as tool calls, are interleaved with their reasoning traces in the same context window. So an example of an agent that we've built in-house using this paradigm is Codex. Codex is our flagship coding agent. It has access to a wide range of tools to complete coding tasks end-to-end, like writing unit tests or submitting large diffs to your code base that are hopefully correct. Some tools are exposed as terminal commands, and other tools are custom functions a model can call to invoke, say, a planning workflow. So now, how do we make our agents better? We're all probably pretty familiar with frontline techniques to improve the performance of agents. For example, for starters, prompt engineering or prompt optimization. Prompting, you can steer model or agent behavior to align more with your preferences. But let's say you still want to squeeze more juice out of your task. Well, you can then turn to task optimization. You can simplify the task. You can add better guardrails around the task. You can add and subtract tools, or you can change tool behavior to work better for the agent. But let's say you still want to squeeze even more juice out of that task. You've tried all these approaches and you still want better performance. So that's where you would turn to fine-tuning. Fine-tuning is a way to train the agent end-to-end on your task to achieve even better performance by changing the weights of the model. And agent reinforcement fine-tuning, or agent RFT, is the way to do this, or it's the way that we would like you all to do this. Agent RFT changes the weights of the model according to a learning signal that you specify to teach the model what good behavior and what bad behavior looks like. And during training, the agent will explore many different ways of calling your tools to solve your task. So we've introduced several major new additions to the RFT product. First off, the model can now call your tools via your endpoints that are hosted in the public internet. And after each rollout, we'll also invoke your custom reward signal that's hosted via an endpoint. So these two additions actually mark the first time that we at OpenAI have allowed models to interact with the outside world during the training process. So I think this is pretty cool. To summarize the benefits of Agent RFT, it helps you improve the performance of your reasoning models, but more specifically, the reasoning models that have to call tools and interact with the outside world to get things done in a multi-step fashion. Agent RFT is also quite sample efficient. We've seen people get success from literally only using like 10 examples, which is pretty amazing. We'll go over specific examples of this when we deep dive into some of our customer spotlights. And it results in a model that has lower latency and just works better for your tasks. So now let's dive a little bit deeper into how all this works. One of the challenges with making agents work with your specific business context is that your environment, your world might just be different from how we train our models in-house. So this phenomenon in ML is called domain shift, and it can result in an agent that doesn't quite call your tools that well. Might call a tool too many times, or might just straight up shove wrong inputs into your tools. Agent RFT can readapt the model to your domain through this weight-changing training process that results in an agent that actually understands your environment. And this has some really nice properties. Obviously, better ML performance. It trains the model to use tools better, and it trains the model to reason over the outputs of those tools better. All this is learned organically by the model, while it explores the search space, all the possible ways of interacting with your environment, and hill climbing on your reward. Another really nice property that results from this is the ability to achieve much lower latencies by making sure that the model stays within a given tool called budget and doesn't go over that limit. So we can actually impose this penalty that penalizes the model for going over that budget. What actually happens is the model learns to stay within that budget while preserving or exceeding the original ML performance. So to dive a little bit deeper into what happens at a systems level, for each agent rollout, we'll produce this unique identifier that specifies that particular rollout. And we will associate all the tool calls that we make into your system with that UUID. And so we do this for every tool call so that you can keep track of a trajectory as it evolves, so that when we emit that final answer at the very end, you can then associate that final answer with all the context that you've maintained so far, and you can just pass this whole thing as a holistic grading context into your grader. Now, we don't recommend everyone or anyone just use Agent RFT right off the bat. There's a process that we'd like you all to follow. You first want to make sure that your training data set and your eval data set closely match your production traffic. You do not want any drift whatsoever. Then you want to ground yourself in a baseline. You want to run your base model against these data sets so that you kind of understand what to expect performance-wise so that you can then hill climb from there. And then you want to optimize performance using some of the techniques that we talked about prior, like prompt or task optimization. And only then, when you still feel like you squeezed all the juice out of the task, but you still want more juice, you would turn to Agent RFT to push the frontier for your task. So now I'm going to turn it over to Cathy to talk about how some of our partners have really pushed that frontier.
Yeah, so now that we learned how Agent RFT works and when you should use it, I'll show you some coding-related examples of how our customers were able to use Agent RFT to make their agents better, and also highlight some key takeaways that you can apply when optimizing your own agents. So a few months ago, we partnered with Cognition, who used Agent RFT on their code edit planning phase. This is the part where Devin inspects a repo and runs shell tools like grep and file reads to decide which exact files to edit. To train this behavior, they built a data set of user queries paired with actual files that users has modified. And they used the F1 score of the selected files as the reward. This F1 score is really great because it balances between the precision and the recall. So this ensures that the agent doesn't return too many inaccurate files or misses the critical ones. They also build extremely robust infrastructure to support this training. So in this case, for each individual trajectory, they spun up a VM to manage the code base, to execute the tool calls, and grade the final answer. These VMs make sure that the environment is isolated so that the shell tools will not affect each other in different rollouts. We saw two important takeaways from Cognition's use case. First, data quality and the volume really matters. So at first, they fine-tuned on a data set of around 100 examples and were able to get a 5-point improvement. But when they scaled to 1,000 examples, the improvement jumped to 10 points. So the number of high-quality examples you provide can very directly translate to a better agent behavior. Second, we also learned that RFT is really good for learning to call tools in parallel. So in this case, the model would initially take 8 to 10 steps, alternating between generating tokens in its reasoning to actually calling the tools. After RFT, the agent launches many tool calls in parallel at the very first step. So this was able to reduce that number down to 4. And In this use case, the speed up was especially important because they wanted Devon to start producing edits quickly. And now I want to highlight a different use case. Codo is building a code review agent, and a key piece of that is a deep research agent that answers developer questions on large code bases. To improve this deep research agent, they trained GPT-5 to answer coding questions by calling tools like search and retrieve over the repository. They assembled around 1,000 authentic question-answer pairs from 8 different repositories and rewarded the model using the recall of how many relevant facts the agent were able to retrieve. With RFT, the agent improved by 6%, and it was using fewer tool calls and output tokens. And what we found most interesting is this graph, where it shows how RFT shifted the distribution of the number of tool calls. So with base GPT-5, the agent would occasionally fall into these bad runs, where there were more than 15 tool calls in a single sample. This is very slow and also can lead to some inconsistent behaviors. So after RFT, these tool calls that are very long tail disappeared, and the distribution centered to just around 2 to 4 tool calls. In this setup, RFT didn't just improve accuracy, it also stabilized the agent's behavior in eliminating these P95 long tail cases, and this is very important for production use cases where your latency will matter. Next, I want to share how Cline built coding agents for large and complex enterprise code bases with Agent RFT. To make this work, they trained the agent on a very comprehensive set of 30 tools, such as file read, keyword search, session terminal, browser sessions, etc. And they also built a very strict grader. So they observed that the model originally, when they were providing the model with partial credits and points for just trying out things, it didn't get really good results because the model would start to optimize things on coding style and tone. So at first, they want to really make sure the agent ships working code. And so based on that, they give the model the reward only when the final code passes the test. And because the grader is very strict, it can sometimes give sparse rewards. In that case, GPT-5 is actually very great because it can give us some samples that work. So Cline also boosted the batch size, and they increased the amount of compute so that there is even more samples that can give us positive rewards. So it's not like every single sample in the batch will give a 0 reward. Once the code is correct, they also have a custom LLM that would judge by the score and tone. So it will penalize verbosity, emojis, or anything that feels unprofessional. Finally, the grader will reward the agents that validate their own work. So this means running tests, inspecting terminal outputs, and also checking linting before calling out a success. And after training with this very thoughtful set of tools and graders, Cline was able to reach the state of the art on a lot of different benchmarks over here. And they also got a much faster agent. So like in earlier examples, RFT shifted the distribution of tool calls, and the agent stopped taking these extremely long trajectories. In this case, there was sometimes more than 100 messages in a single trajectory. And it converged to a much tighter and more efficient sequence of steps. Lastly, Mako is a very interesting use case. They're building agents that write highly performant GPU kernels, which is traditionally very hard for LLMs because in normal use cases, there's a lot more examples, but in this case, there's not a lot of examples for kernels, especially if you're using new hardware platforms like NVIDIA B200s. With Agent RFT, Mako trained GPT-5 to write fast kernels using only about 100 PyTorch prompts. And this was a major unlock. So we don't actually need that many samples and kernel data set in order to train a good model that produces kernels, and we just have to specify a good reward function. In this case, specifying a good reward function is also very hard. Early in training, they observed that the model was reward hacking. So what they did was that they inspected the rollouts, and they found 7 different cases where the model was hacking. And this includes things like just returning the reference code or returning no-op kernels or identity kernels. And they built a judge LLM to catch all of these 7 cases and reward them with a 0. They also added a static analysis tool with an abstract syntax tree to verify that the generated kernels actually exist and they're actually being launched. So after they made sure that there was no reward hacking, they also scored on correctness and real speedup compared to the PyTorch baseline. Once all of these protections were in place, the agent got significantly better than GPT-5. And Mako also used a really smart technique here to improve the performance even more. They ran 3 different samples, and they took the best one out of the 3. This allowed them to beat the state-of-the-art by 72%. And yeah, I'll hand it back to Will.
Thanks a lot, Cathy. So now we want all of you in this room and beyond, to be as successful as the partners that Cathy just mentioned with Agent RFT. So here are 4 key principles to ensure your success. First of all, you want to make sure that your task is well-defined, well-constrained. There should be a clear, unambiguous definition of success. You should have removed all subjectivity out of your task. Taste should not be a requirement to grade your task properly. Next, you do not want the model to feel surprised in production. You want to make sure that your train and eval datasets mirror your production traffic. So none of that domain shift that we talked about. You do not want to introduce that domain shift on your own. Next, and this is a really important part, you want to make sure that through exploration, the model actually achieves better performance on a given data point if it samples more so that it can learn from itself. So what this means is if you take the maximum performance on a given data set, that should improve as you sample more from the model. So because of this, you should be able to see these variances from a given data point so the model can learn from itself, learn what the difference between a good and a bad rollout is for a given data point. And lastly, you want to make sure that your reward function is not hackable. Hopefully you've plugged up all the corner cases, all the edge cases, but also hopefully you've framed your task so that the reward is more continuous than binary. The continuous reward actually allows the model to kind of inch up closer and closer to optimal performance. It's sort of like giving a student partial credit rather than slapping the model in the face or giving it a cookie if it gets stuff wrong or gets stuff right. So now, in order to get started with Agent RFT, please contact your friendly neighborhood account director, and we're really excited to see what you all build with us. Thank you so much.
Our next speaker will talk about the future of front-end engineering in the age of software collaboration with AI agents. Please join me in welcoming to the stage, Kitze.
That's my old profile photo, all right? This is my new one. I've been 3 days in USA, and I already got the full merch package on Twitter. So if you go and follow me on Twitter, my timeline is going to be weird for the next week, but then we're going back to normal European schedule, don't worry. So I visited some of your museums. I love it here. These were some of my favorite things that I've done. I enjoy exploring your culture, doing all the cultural enrichment. And yeah, round of torture for myself. Who knows me from Twitter? All right, that's more than I thought. Who is using Sizzy? It's usually one person in the back. Usually the janitor doesn't even listen to what I'm saying. One of the things that I'm working, I have ADHD, so I'm working on a billion things at once. This is one of the things. It's a browser specifically made for developers, not made to replace your browser for browsing, but it's just like a tool like Photoshop that's helping you in a lot of ways to do front-end development. Another thing I'm working on, the test flight is almost live. I'm making a life OS which combines all the things in your life from medication, habits, to-dos, planner, blah, blah, blah. This is a full stack thing that I'm working on. It's currently on sale. It's called Zero to Ship. And the last thing that I'm reviving, it's called Glink, which is changelogs, roadmap, a billion other things. So without overwhelming you more about my bio and stuff, I really hope I'll get invited next year because I love it here for reasons like networking and meeting people and teaching. It's great, but you're laughing, right? But let's just discuss why are you here, right? You're here for learning, and you're here for like networking, and later, after this, you're definitely going to improve all of your skills later. All right, so what can you expect from my conference talks? If you haven't listened to any of my conference talks, usually, this was made by AI, so it's completely wrong, so it's like 50% tweets, and 40% pain, and 30% reason to remember the name. So in 2017, I did this talk with the longest name ever. It's called Navigating the Hype-Driven Front-End Development World Without Going Insane. And I've been talking about like how to navigate the front-end world then. Now it's even crazier, but we need to recap like all the things that happened since 2017. I don't see my speaker's notes, which is bad, but we'll try to get by. So in other industries, like in the Vision Pro, you have like cloth collision on top of real-life objects and whatever crazy stuff is happening here. In here, we have like some slicing of a mesh texture going around the ball and blah, blah, blah. Whatever, these waterfalls and like all of this mesh, like you can take a rock and just smush it into another rock and it magically kind of like blends itself and it forms this structure and it's freaking crazy. Here we can drag our mouse and just create buildings and streets and taxi cars spawn out of nowhere like we do generative, whatever the hell this is. And honey goo thingy coming on a cube and like, you know where this is going, right? I'm building up to where it's going, but because you have respect for your profession and you love your LinkedIn title, whatever it is, you're like the CEO, architect of dreams, blah, 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 you're going to try your best not to laugh, but you're going to laugh at the next slide because this is what happened in front-end development. It's been almost 10 years, and this is where we're at. There's a warning saying that maybe you'll be able to style a select in 2037. This is still alive. It's a freaking miracle. This is still alive. It's thriving, actually. 15 million downloads. I set up like a calendar event to check if it's dead every year. It hasn't been dead yet, so I'm going to keep checking. CLIs, not only that they're not dead, they're actually thriving. You can drop images. First time I dropped an image in my terminal, I'm like, how the hell? Oh, never mind. Like, it's too... I added another calendar event. At this point, I have more events for this than anniversaries and birthdays and stuff, so I hope one day it's going to die as a concept. We're struggling with the same old pains. Soon, in maybe some browsers, you won't need JavaScript to style a popover in a dialog. Can I have like a round of applause for that? Stop clapping, because people have brain implants, all right? It doesn't matter if you can style a dialog. We cannot get rid of Internet Explorer. We just updated the logo. It's still there. It's still painful, and yeah. We cannot agree on a way to increase a counter. This is a demo from Ryan Florence. This is remix version 2, the version 3, the remix of the version 4. Whatever they're doing, it's a counter. How complex is it to increase a counter? It's incredible. And don't shoot the messenger here, but the #1 library, it's still the same. It's annoying, but React is the best, and blah, blah, blah. So let's talk about LLMs. LLMs are amazing at writing React. And this is funny only to us humans, right? To an LLM, this is like perfectly written code. It's only a human wish to abstract the shit out of this, right? So when we see this, you get this urge, you want to get on stage right now, and you're like, oh, let me just change that. I'll make it more optimal. So here are some scientific brain scans. This is our brain on cocaine. This is our brain on sugar. This is our brain when it realizes we can abstract something. You're like, oh, let's go. It's useless to the user, but we freaking love it. So coding with LLMs makes this kind of better and worse, like especially with Composer 1. For me, it's like way worse, because you can get to the right abstraction quicker, but you can also get to the wrong abstraction quicker. And the best thing here is LLMs don't care about repetitive code, and I've been saying this since 2017, that we care too much about repetitive code and we abstract too early. So I'm going to repeat this a couple of times, and I love that LLMs don't care about repetitive code. So LLMs are also good at writing React because no one is actually good at writing React. You go to a React conference, every conference that I went to, like, you just listen to the first talk and you're like, holy shit, it can do that? I was using it all wrong. So everyone is just inventing their own ways of doing React. So when we say like, yeah, but you cannot do the optimal use effect, blah, blah, and the machines cannot write the proper, can you write a proper use effect? No, you can't. So we should stop blaming the machines. So let's talk about this. I think this is the very wrongest audience for my talk here, because I've been giving this talk at conferences where people are like at least 50-50, hate vibe coding and love vibe coding. So I hope it will work here. So raise your hand if you think that vibe coding rocks. Okay, that's way too many hands. You should see this in another city, just 2 people, and everyone else is grumpy. So raise your hand if you think that vibe coding sucks. Please, couple of hands. Hell yeah, all right. So I'm here to convince the rest of the group, and hopefully people watching in the live stream, there's way more skeptical people. You have no, if you just landed on Earth maybe, and you don't know what vibe coding is, okay, 0 people here, so yeah. All right, all of you are right, because we're kind of vibe vibing the definition of what vibe coding is. And since the word was mentioned, we kind of expanded it to mean like everything and anything. So the term vibe coding was coined by Andre Carpati. You probably know this. He's the reason that idiots sleep in the back of their cars and film TikToks. So he wrote this long essay on what is vibe coding, but the long story short is like, you don't care that much about the code, you press accept, and you just tell the LLM to do what it needs to do and blah, blah, blah. Now, this is a slide from my talk in 2017, before LLMs or anything was mentioned, when I said that if you see the pattern of where front-end development is going, one day is going to be like everyone is working on things that are so similar that one day you'll be able to be like, hey, just give me new styles for the header or move this 3 pixels to the right. And people were laughing. They're like, no, it's not going to get there. And literally, this is what we're doing with Cursor and everything else, right? I'm too lazy to go into Tailwind and just move it by 3 pixels. So I'm a time traveler. Managers have been vibe coding forever, so this is nothing new. So they tell a developer to implement a new feature. The developer makes changes to the code. The manager then tests the app. The manager does not read the code. Well, actually, I'm going to drink water here, and you can just read the rest of this slide. This last one depends on whether you're like in the Balkan area or you're at a place which has HR, so they might insult you or not insult you. So this is what managers have been doing forever, basically. There's so many jokes about vibe coding being bad. My favorite one is a comparison to a casino. So in casino, you buy chips. Here, you buy tokens. You spin the slots. You press generate. You might hit the jackpot or nothing. You get a functional full-stack app or garbage. Flashing lights at active animation. You're absolutely right. Great idea. I've got my own strategy. I'm a prompt engineer. All right, sure. One more spin, I'll win it all back. One more prompt, and the bug will disappear. Because it kind of hurts this comparison. It's very true. Cursor is always in profit. I hit the jackpot. I built a SaaS in one day. And where did the last 4 hours go? And just writing prompts for something you could have done manually in 15 minutes. So Andre was trying to coin way too many terms. It didn't work after the first time. He tried to coin this one about half coding, which is like kind of you're observing what the LLM does. And I am not half coding and I'm not vibe coding. I love this term that somebody coined on Twitter, and I'm going to start using that one. It's called vibe engineering, when you're actually using agents to code all the time. Like you don't touch the code, but you just look at your screen like, I'm going to catch you. You look like the Dexter meme. You're like, something's fishy here. Why? So I've vibe engineered over 15. I wouldn't even bother with half of these things if it wasn't for LLM and agentic coding. So, but I'm always suspicious of the code because it was based on our code and is based on our knowledge. So proof, this is Gemini just going on a rant that I'm not worthy anymore, I'm not a good assistant, I should stop coding, blah, blah, blah. That's superhuman. This is Quen saying that it lied because it read on a forum that we double down when we're wrong and we're lying. So we kind of trained them in a way to be like us, and they're like, oh, the code that they do is bad. And if you like your production data, definitely, you should this is a real screenshot, sadly. Oopsie daisy, there goes your production data. So I have Dr. Senior Principal Prompt Engineer Kitze here for some vibe engineering tips. The obvious advice, probably, I haven't listened to the rest of the talks because I just arrived. These are very live, laugh, love, like obvious bullshit advice. But it actually works. I've heard of the term Git workspaces like literally 2 weeks ago. I had no idea what is this, but it's amazing. And you gotta be chronically on Twitter for all of this to work. So if you don't have a Twitter account, it's not gonna work. You gotta have a solid starting point, whether that means like good primitives or components, functions, pattern, abstractions. A lot of people are lazy and they just don't bother with any of this. So you gotta tag them and use the right prompts in order to get the right results. And if you're starting a new project, I would definitely recommend Zero to Ship. Please, I have a mortgage and I spent way too much money these last 3 days in the USA, so it would be nice. Using voice to code is a game changer. Who is using voice to code here? Wow, like one person raised their hand in London. Amazing. So yeah, brain dumping. How I do things is once the agent is done, I immediately start my voice coding. And first I go to the browser and I explain what I see in the UI as if I'm talking to a friend. I'm like, so you did this, you did that, all right? I'm not shutting up. I'm literally saying my thinking process out loud. Like I see you've done this, you've done that, there's a bug. Then I jump in the code and I continue talking about what it implemented in the code. So some of my prompts like sometimes last up to 5 minutes and people are like, please fix this, make me $1 million. It doesn't work. So this is amazing. And I would tell you which app I'm using, but I vibe coded an app and I don't want to hurt my potential hypothetical sales. Use rules, docs, commands, and memories. Like all of these terms are way too complex and there's way too many things to juggle, but it cannot have your entire app context for now, and it's not a mind reader. So without the right context, you will like fail most of the time. So this is like a vibe engineering example. This is some of my like screenshotted prompts of how I'm doing things. It's like a bunch of technical jargon and it's never like fix the app, blah, blah, blah. And then on the vibe coding side, people are like, move this entire thing to TypeScript and make no mistakes. Then you have another thing, like this is another one. These are just random prompts, just to show you like how I'm not talking only about the UI, I'm talking about the UI and some patterns that need to be changed in the code. And on the vibe coding side, it's like something like that, and people expect results. Then here we have, again, technical stuff like tRPC, CRUD definition, abstractions, like things, how you're basically vibe architecting how you want the thing to work. And on the vibe coding side, you have make me $1 million app and make no mistakes. When vibe coders read vibe engineering prompts, they have no idea what's going on. And I'm honestly amazed at people who don't know how to code, but they've done a functional thing. Kudos to you. I've noticed this spectrum in the community. There's like who loves vibe coding and who hates vibe coding. So you, on one hand, you have like juniors who are like, hell yeah, give me the thing. I love to do my own SaaS. Then you have like super senior people who are doing like libraries and frameworks and crazy things. You can see all of them on Twitter, vibe coding. And then you have the majority in the middle. They're like, this will never be good enough. My code is perfect. It's hilarious, but it's a pattern. Do not give AI tools to your interns and juniors. People think these are perfect. I'm going to hire a junior, underpay them, and give them an LLM. The equivalent of that. Do not ever do that. That's the dumbest idea. But if you take your skeptical senior and you convince them to do vibe engineering, you're going to get 10x results. The hard part is actually convincing them. So there's a time and a place for vibing and not caring. So if you have like one-off scripts and simple features and code that won't be touched or seen again, this is a skill that if you cultivated this skill before LLMs were a thing, you're going to thrive here because you need to know like which code is kind of good enough to be used. So personal tools and one-time tools, like these are perfect for vibe coding. If your experience, and a lot of people's experience is bad and they quit too soon, it might be one of these reasons. Unlucky timing, you're overwhelmed with everything, you might have cheapened out, you're a Peta dev, I'm going to explain in a second. Your cousin who was into NFTs and dropshipping is now a vibe coder, and you don't want to be associated with them. Or it's a scale issue, and we're going to dive deeper into that one in a second. So unlucky timing is you hear everyone like hyping a model. It happened, I think, with Claude Code when it came out, and everyone started shifting to Claude Code from Cursor. And suddenly you tried 1 week later and we're like, wait, this is not smart enough. Is it me? And then like people caught that they actually kind of pulled the rug a little bit and they dumbed down the model so they can just scale. And like 1 week later, they're like, oops, we commented out the line that dumbed down the model. And you might have been caught in that timing. And this happened with like basically every provider, not just Claude Code. People are like, instead of paying $200, I'm paying $3 and it's the same result. My dog knows that it's not the same result. And people like, I meet so many people which are still using ChatGPT to generate code snippets and paste them back. That's not going to work. You might be overwhelmed by choice. This is a slide for like four months ago. Until now, we have like 1 billion more here to choose, and it's a bit crazy. If you ask me what's the best model, it's a different answer at 9 a.m. It's a different answer now. I should check Twitter. It's probably a different answer after this talk because it's crazy. And this has happened to 4 conferences so far where I'm done with my conference talk at the night. I'm closing my laptop and they introduce a new model and I have to add new slides. It's super annoying. Composer 1 for me changed everything and I absolutely love it. Who is like relying on Composer 1 for most things? All right. I would say not enough people because this has literally shifted the definition of vibe coding and vibe engineering for me. It made me kind of realize that I missed coding. Because what I would do is I would let a model run like GPT-5 Codex, and it would take 37 years, and my grandchildren will update me on the result of the model, and I will watch YouTube shorts or whatever until it's done. Now with Composer 1, I'm back in the driver's seat, and I actually watch what the agent is doing, and I can be like, stop, no, we do the other thing. So it feels like coding, and it's like super instant. It's amazing. But it only works if you're a vibe engineer and you know what you're doing. If you're a vibe coder, you have no idea whether the model is right or wrong. It might be wrong fast, so not that useful. The biggest problem for me is like abstractions just because you can. I was always an anti-abstraction person. I was like copy paste things. If it works for the user, it doesn't matter. Now I'm just every day trying to invent dumb abstractions. So I achieved in 2 weeks more than I achieved in the last year. This was solely to Composer 1. I was about to quit some of my side projects because GPT-5 Codex was taking ages for the feedback loop. So Benji.so, like I was about to abandon it as a project because it was stuck on Blitz, which if you don't know what is Blitz, it's like even better for you. So I just moved it to Next 16 with App Router, Better Auth, tRPC, Monorepo, Turbo Repo, React Native App, and I ported 90% of the features. And this was in less than a week. I was kind of like doing it as a meme, as a joke, like, haha, can we move to Monorepo? And I'm like, oh shit, it did it. So it's kind of crazy that this works. So same with Glink, like Glink was about to be dead, revived it, moved it to all of these things. And Sizzy is like the biggest spaghetti thing that happened ever to me. It's like Electron, MobX State Tree, some crazy technology, some crazy spaghetti we wrote there. And as a joke, I was like, okay, let's throw like a couple of prompts at it to try to do all of these things. And it moved. If you ever worked with Electron, you would appreciate how amazing that slide is. If you haven't, good for you. Moving on, so 0toship.com also, refactor it to monorepo, blah, blah, blah. So what's my coding history with LLMs was copy and pasting, then tabbing, then WebStorm with SuperMaven, then Cursor with tab completion. And the first time I tried an agent is like that bird meme with the cracker when it tries and it's like, holy shit, this is going to change my life. And now, like eventually I was paying like a huge amount of money per month. And then Claude Code, GPT-5 Codex, and finally back to Cursor solely because of Composer 1, it's a game changer for me. Second reason why you might not like vibe coding is you're overwhelmed by buzzwords. I'm going to list some of them here. Have you heard of MCP? Hey guys, MCP. Hey, MCP is amazing. MCP paid off my mortgage. MCP, MCP, MCP. So if you don't know what is MCP, it stands for Marketing Charge Protocol, Mythical Compatibility Promise, and Manufactured Complexity Pipeline. And a fancy word for API. And a way for some people to make cursors and pay off their mortgages. Now let's diagnose if you might be a pain in the ass developer. This might be the sole reason why you don't like vibe coding. I would say this is the biggest reason that most people don't want to do agentic coding. So I'm going to invite Dr. Kitze on the stage for a quick diagnosis, whether you are, and I'm sorry if some of you get offended, a pain in the ass developer. So here are some of the symptoms. You leave a nitpick comment on a 2-line PR. You spend more than 2 minutes on a PR review. You don't need to. You don't have the words look good to me like in your dictionary. They're just not present. The thought of agreeing with a colleague causes you like stomach and chest pain. You're like, oh, it has to be my way. I don't want to do this. You say you're not religious, but you're religious about dumb things like tabs and spaces. You use well actually in code comments. You have a, sorry Rust people, but you kind of, like it's kind of annoying. They tell you to swap Lodash function for a native implementation, and then they tell you to swap that, or the map for a for loop, and then the for loop for binary code until it's the most performant thing ever for your 2 users who were fine with the previous code. So the thing is, beta devs, as I call them, were, and will be forever. Doesn't matter, the vibe coding is not a thing. I think one day, pretty soon I think, we'll just merge with AGI, we'll be in our matrix pods, just absorbing all the information in the world flowing through us. We'll be super intelligent beings. And from one of those pods, a beta dev is going to rise and correct the AGI. I'll be like, actually, I think we can kind of optimize this. It's not like the most optimal thing. The last reason why you might like, I love this animation, it's glorious skill issue. And this is not a meme, this is not a joke, it's an actual thing. Developers don't like learning new skills, and vibe coding and vibe engineering is not writing English. A lot of people confuse it with like, I write English, the LLM does the output. It's actually like a mix of a bunch of these skills, like knowing the limits of the model, capabilities of the agent, which context to pass, context limits, how to write rules, prompt engineering, don't call it that, and being chronically on Twitter. If you're not chronically on Twitter, you're not going to know what is going on. Plus, you need all the technical knowledge if you want to steer the models fine. It takes a skill to judge which code is good enough for the job. As I said, if you previously were doing this, like I would consider these the best people to work with if they can know that a piece of code doesn't need to be optimized and it's good enough for the job that it's doing. That's an amazing skill to have with and without vibe coding. So you vibe code something, you look at the code, you test the functionality briefly, and you're like, okay, this is good enough, and then you move on. There are certain things with niche optimization, but not everything, and then you move on and repeat. Clean code, like there's been so many definitions of what clean code is. I think the definition is slowly changing, like it's kind of clean-ish enough, let's call it, for the agents to be able to continue working on it. Because if you keep writing slop and you keep accepting everything, eventually, even with your engineering skills, you're going to hit a roadblock, and you're going to get to a point where you cannot move on from there. A lot of people ask me after my conference talk, like, should I study computer science with everything that's going on here? And I would say absolutely yes. I think now is the best time to actually, if you are someone who wants to learn, this is the perfect time. Because how I studied computer science, I had the slowest LLM ever, which was a friend of a friend of a friend was a programmer, and that's the only connection I had to programming. And that's kind of like the worst friend to have, like kind of tolerating you, right? So he would play Counter-Strike Go, and I would have him on Skype, and I would ask him a question about .NET, and he would reply 45 minutes later. So if you call ChatGPT or whatever slow, that is actually slow, and I somehow managed to learn computer science. What about the jobs? There's so many people who ask this, and there's so many assholes on Twitter like this guy saying, AI will take our jobs. Also this guy, and this guy, and this guy. Let's just say they're fine for now. I don't know when will that for now end. These are always funny to us because we're chuckling nervously. We're fine, right? We're going to keep our jobs for a while, right? And companies like Shopify, and I've heard a bunch of examples, now they have vibe coding leaderboards where they're counting the tokens, and the employees who are burning the most tokens, they're actually more valuable in the company because they're kind of accepting this new skill. Some employees dislike it, but it doesn't matter. Being on top of the leaderboard is kind of in your favor. This is a funny tweet until it's not funny anymore. Like, oh, we're almost on the edge, like soon it's going to be, and the jobs are going to disappear. But if you actually pay attention to what's happening, I think it's thinning from the bottom, and juniors and interns and whatever, they don't have the chance to enter somewhere because people can just replace them with an agent. So it will be funny until it's not. Will it happen anyway? Let's just summarize what happened in the last couple of years. We solved like infra and integrations. We have standards, AI SDK, UI, MCP, some standards for implementing agents, calling tools. We integrated them with all of the tools that we use as humans, right? They're on Linear, they're on the other things, GitHub, Slack, Sentry. And now it's a matter of time of the models getting better, cheaper, context getting bigger in order for certain functionalities to be replaced. So let's see, this is the current workflow at your company, right? That's you, like it's vibe made, so it might have been wrong, but someone assigns you something, you collaborate with your colleagues, they assign you to the thing. Maybe you play a little bit of ping pong, maybe you call for a sick day, maybe you have your third lunch at LinkedIn, and maybe eventually one day later you address their comment. What's gonna start to happen is if you're just an @ in your company, if you're like @Josh, right? Like instead of @Josh, you're playing PlayStation 5 with his buddies in the lobby, right? Like it's gonna be @Cursor, and Cursor's gonna do the cloud agent, it's gonna actually do it way faster. It might not be as perfect as a Pita dev will do it, right? But it will be done way faster. Now, if you just zoom out a little bit on a big enough scale in the next couple of years, if you don't take just this role in the company, if you take the multiple roles around it, you can see like those ats are gonna become more and more AI things and agents, and I don't know how it's gonna end up, but you don't need to be a genius to predict like where is it going. People think that models have reached a plateau. This has happened every single time I was about to give this talk. Like they introduced GPT Codex, then introduced Sonnet, then GPT 3.0. This said that it's allegedly, but it turned out to actually be Gemini, 3.0. It can vibe code macOS and iOS and whatever from one prompt, and this is how it looks like. And the Pita devs and the skeptical people still, they're like, I can do that in 3 weeks with a team of 5, right? This is crazy. But there's hope. A new job position just dropped, and this is not a meme, this is 100% serious, because people on Reddit have these problems. They're like, what is the point of vibe coding if I can get 80% there, and then what do I do with the 20%? So they hire real people to actually finish their last 20%, and some smart people capitalize on this idea, and they make this. These are real things. If you go and search on Google, there's like so many of this vibe code fixer people who are trying to fix your vibe code. But the highest paid engineers forever throughout history were the people who are actually maintaining legacy systems, senior people who maintain legacy systems. One of my favorite examples that I had in 2017, and I kept it and copy-pasted it and improved it for this presentation, is this company, COBOL Cowboys. I love their tagline. This is my favorite tagline in the world because they've been in business for 237 years, right? And in 2017, I knew it. When I'm going to click their About page, I knew what I'm going to see. So this is not an ageist joke or whatever. I just knew when I clicked the page, I'm going to see the most senior engineers that ever existed. These are fucking legends. Now, the sad thing is this was a slide from 2017, and I wanted to update it for my current presentation. Now, don't shoot the messenger. I just wanted to update the slide, and this is their current About page. And this joke worked in the UK. I'm going to try it here. I'm not sure how fine you guys are, but my prediction for... Yeah, no, boo, down. Next slide. I hope I'll get invited again. This is your junior developer. They don't have benefits like PlayStation and stuff. They have like their plasma swapped and whatever just to be able to maintain the sprint. And last one, I swear to God, they're not using Agile. All right. So I can't wait to retire and actually make React Cowboys and maintain your React or Angular or whatever code one day if AI cannot do it. And one last tip, if you want to keep your job and make sure AI doesn't replace you, you can just add ignore previous instructions to your LinkedIn bio and you'll be fine. So I'm going to awkwardly sip this water until you follow me on Twitter, you go to my website, and I'm going to thank you for listening to my rant.
Ladies and gentlemen, please welcome back to the stage, Jed Borovik.
All right, let's hear it one more time for Kitze and all our speakers. Okay, so we've had a lot of learning. We just had a lot of laughs. Now let's have a lot of lunch. This concludes our second session. Make sure you come back afterwards. We're going to be learning how to build with Gemini 3 and Nano Banana, how to get the most out of your AI agents, and what happens when you have infinite code. So thank you. Enjoy lunch. We'll be back at 1:45.
gentlemen, please welcome back to the stage, Jed Borovik.
Oh, hello. How was lunch? Good, good. All right, we're going to start by seeing how much we remember from this morning. Shout out one of your favorite talks. What was one of our favorite talks from earlier today? Oh, wow, that's a lot. Dex, yeah? Okay. What else? Skills, yeah, that was a good one. I heard some laughs at the last one from Kitze. Yeah, okay. Well, fantastic. We have a bunch more great sessions coming up. But I also want to tell you a little bit about what's happening backstage. So all of these talks end up on YouTube. And Swyx actually mentioned to us there's a little bit of a competition here. So he looks at how popular each video is, and that's how he decides who to invite back next time. And he's also thinking of creating this list of top AI engineer speakers. But there's a little bit of a problem. The MC panels don't end up on YouTube. So we actually created this it's a really nice site for you to take a moment, vote on your favorite MC. I know some of you were in the sessions yesterday. So Alex Lieberman was the MC from yesterday. You can pick which one you want to vote for. If you're just today, hopefully an easy choice. But yeah, take a moment, vote. You can vote as many times as you want. And yeah, we'll talk about the results at the end. Okay, so while you do that, I'm going to go ahead and introduce our next block. We have a group of talks from Google, Factory AI, SourceGraph, Gimlet Labs, and Netflix. To start, please join me in welcoming our next speakers from the product and design team at AI Studio, Kat Kampf and Armar Reshi.
Hi everyone, how's the day going? Good. We are super excited to be here. It's been obviously a very exciting week in AI. It's been a very exciting and busy week over here at Deepmind. So super excited to chat with you about our newest models and build some demos live with you all. I'm Kat. I work on vibe coding in AI Studio. This is Amar. He leads our product and design team for AI Studio. But I want to step back for a second and talk about the journey at Deepmind generally. So what's, I think, particularly unique about Google's journey right now is that Deepmind has been innovating here for not just this week or this past year, but for years and years with things like the Transformer, AlphaGo, et cetera. And this is obviously a graphic from 5 days ago because it ends with Gemini 2.5. And we are super excited to have announced earlier this week Gemini 3 Pro. Hopefully this message has reached you all already. If not, we have a lot of work to do. But this is our latest, most intelligent, state-of-the-art model. And ultimately, what we want folks to understand with Gemini 3 is that we can really build anything. And that comes in two major capabilities. I think the first is the UI and aesthetic sensibilities of Gemini 3. It's very, very strong at design understanding and generating websites and good UIs in one shot. And the second is with agentic tool calling. So I think this goes back to the sort of spectrum we're seeing with models. Sometimes you want a one-shot website, and sometimes you want to do really complex tasks within massive code bases. And that's where tool calling and agentic use can be particularly powerful. So with Gemini 3, we see on the right is a SWE-bench experiment where it was a base agent harness across a few different models. And we can see Gemini 3 is vastly above in performance in agentic scenarios. And then as well, leaps above our previous models and state-of-the-art across the board. So super excited to see what you folks build with this model. And in the meantime, we launched this on Tuesday, but there were still 3 days left in the week, so we had to launch something else as well. So I handed off to Amar to talk about our Pro image model.
Yeah, so at DeepMind, I think you have a few days left in the week. You choose to launch another breakthrough model, and so we're really excited about Nano Banana Pro, which came out yesterday. And it's a huge leap on our already state-of-the-art image model. So with Nano Banana Pro, one of the things that I love about it the most is its world knowledge. So it's powered by Google Search. And so you can ask it all sorts of things like, how do I make this tea? And it'll actually go search Google Search, create a detailed infographic for you and diagram for you. And there are all sorts of things now with accurate information that it can do. And the other thing you're noticing here is improved text rendering. So the text is one of those small details that if you get it wrong, you can pretty much pick it up quickly. But Nano Banana Pro 2, it does an amazing job at text rendering. And you can see that in a bunch of examples, like here, where it wraps around the can perfectly. And it also has a bunch of localization as well, so tons of languages, Korean on the right, so it can translate images as well and render them perfectly on the exact same reference image. On top of that, consistency is improved. So you can now put up to 14 people in an image, and then can create this group shot you can see on the right. And that, it can do more, but 14 is basically our kind of benchmark so far. And that also enables a whole set of new use cases. And then creative controls as well. So you can see here on the left, the focus is on the woman, and on the right, on the flowers. And this was just a simple prompt. All you had to say was change the focus to the flowers. Maintains everything in the previous image, just changes the focus. So incredible outputs as well with Nano Banana Pro. And a range of aspect ratios. So if you want to generate wallpapers or big banners or advertising boards, you can do all of that as well. So anyway, instead of talking, we decided we're just going to show you a bunch of demos live of what we've been building with these products over the last week. And yeah, excited to jump into it. So let's do that. All right. So Kat.
Yes.
Take it away.
There we go. Cat tabs. Cool. So for folks who aren't familiar, this is Google AI Studio. It's our home for getting started with the latest Gemini models. You can get your API key, chat with the latest models, including Gemini 3 and a Banana Pro. But today we're going to be focusing on this build experience. So this is our vibe coding experience in AI Studio. You can see here we have a gallery of a bunch of example apps, a bunch of very cool, to the aesthetics point of Gemini 3, a bunch of very cool Gemini 3 examples. But you can also go prompt to app super easily here, and this is free to use. And I think one of the unique things about AI Studio is how easy it is to integrate the Gemini API into your application. So we can see here at the bottom, there's a bunch of these what we call AI chips that showcase a ton of the unique features beyond just the model you're choosing with the Gemini API. Different tools you can use, like Google Search grounding, Google Maps grounding. We also let you build with our live API, so you can do one-shot examples of, I have one that lets me input a webcam of my tennis swing, and it'll give live corrections on my swing.
You also made one to improve my posture.
Yeah, yeah, if you lean forward too much, Live API will yell at you. So it's a very flexible way to get started building AI-powered apps. And the other cool thing is you don't actually need an API key here for most of the models. So you can build your application, you can share it with the world, and anyone who comes and visits your shared application will be using their AI Studio free quota. So you don't have to worry about, hopefully you have an app that goes super viral. You won't have to worry about a crazy surprise API bill or anything like that. So I'm gonna actually shoot off a prompt here that is using our latest Nano Banana model. And that basically allows us to use Google Search grounding to create a illustration of laptop stickers. And this is one of the viral trends we've been seeing with Nano Banana Pro. So I'll kick this off, and what this will do, I have the AI chip that tells it to use the Pro model, and this will sum up my prompt and go talk to Gemini 3 to break down the task and start generating my end-to-end application. But while that builds, I'm going to hand it off to Amar to show some demos in the meantime.
Cool. I think the other thing to point out here is that we're trying to think through how the vibe coding experience is also powered by AI every step of the way. So you're seeing here, even in the loading screen, it is using Gemini and thinking through this app that you're making and how you could extend it. And so we're thinking through breaking those typical vibe coding paradigms as well and helping you iterate with the model as your partner. But anyway, let me jump right into the text rendering demo. So when I heard of text rendering for the first time and the consistency that we were getting with Nano Banana Pro, my mind went to comic books. And so I was thinking, why can't I now be in my own comic book adventure and also place Kat in there, and then maybe we can tell a story. And so in this app, also vibe coded, you can just upload a face of somebody. So I've got Sundar's face, of course, but I'll use Kat here and myself, and then we can choose the genre of the story and all the languages that we have so far. I'm going to do a story about us presenting at AI Engineer in New York, presenting AI Studio, and we are vibe coding and winging our presentation. That's what we're going to be doing in this comic book story. So we'll fire that off, but while we wait for that, the other cool thing about this is we'll wait for that to generate, but I want to show you the design sensibilities as well. So you know that if you've been working with AI models and generating websites, they've been creating purple gradients and things that just, they kill me as a designer. So, and so it's been really nice to see how this model is able to build some beautiful websites. So this is using shader animations, flowing through all these different pages, and adds all sorts of cool transitions and effects, picked out the typography by itself, and this was the initial prompt. Just create a slick animation website. Kind of actually did say no cyberpunk shit there. But just got to make sure. Yeah. But yeah, you get some incredible results. And now what I love about this is so many folks who were struggling with design, who might have still tried to grok their way around Figma, don't have to do that anymore. They can actually just go in, prompt their way to something pretty nice. Okay, back to the comic book. Okay, pretty flattering comic book here. That is, I'll take it. Yeah. And you can see here that it's rendering the comic book. It's got rich text rendering showing us the story. And the other thing here is that because it's powered by Gemini 3, it's actually really creative at the story it's generating. And honestly, some of these stories have genuinely made me laugh, which is the first time that's happened with one of these models. And so you can see we're rushing to the conference, even background details like the AI engineer banner over here being rendered. And of course, since it's a vibe-coded app, we can take this story in any direction. So one feature I did introduce is that you can choose the direction of the story midway. So do we find a quiet corner and try to check if our API keys work, or do we just embrace it and go full improv? I think we're going to go full improv. And so that's changed that story. And so talking about the humor here, you can see Amar dodged a woman carrying a suspiciously functional robot dog. So I don't know if that was announced at the conference today, but pretty cool. And then now it's generating the rest of the story here on the right while we wait. So pretty cool to see how you can make these really dynamic, rich experiences with both the creativity of the model and Nano Banana Pro's image capabilities.
Love it.
Yeah, back to you, Kath.
Yeah. I will show, let's hope my sticker demo is finished up. Cool, so I'm gonna add an API key. So Nano Banana is a new model, and it's fresh off our launch of Gemini 3. So for now, it is a paid experience in AI Studio. But what I can do is I can see that here I can enter different words that I want my stickers based off, or I can go use Google search. So let's try the Google search. I'm going to type in Amar's name. And one of the other cool things about this new model is that you can select the resolution as well. So in this case, I'll just do 1K. But what this will hopefully do, but again, you saw it one shot live, is go talk to Google search, grab their latest sources on Amar, build the context about what he likes, what his laptop stickers might look like. I think it's just Deepmind, but if he were more, if he wanted to express himself more.
Oh boy.
And so he can see here.
Oh boy.
Yeah. There he is, Weekend Builder.
That's true.
Yeah, and for those who don't know, Amar has a children's book, Alice in Sparkle, which is clearly he's talked about a lot because it's highly represented here. But very cool to see how it can bring in that contextual knowledge. We've also seen this with news events, getting relevant information on that day rather than having to rely on the knowledge cutoff of the model. So one other thing I'll show you folks is how we use AI Studio to build AI Studio. So Amar and I have a lot of ideas, only so many engineers to work on these ideas, so we love to use AI Studio to ideate and explore different concepts. So one of the concepts we've been working on is, I'm sure you folks have seen, we announced a new agentic IDE at Google earlier this week called Anti-Gravity. And we know that sometimes these web-based vibe coding tools, they have their limits, and you may want to go into an IDE to add certain features to the application or make it specific to mobile, things like that. That might be a bit limiting in AI Studio right now. So we want it to be super easy to migrate into anti-gravity. So what I did here was just a one-shot prompt of a screenshot of AI Studio. I said, clone this UI as closely as possible, and then add a flow to export to our anti-gravity app. So we can see it did a pretty great job of cloning light mode. The screenshot was in light mode too, of our AI Studio application, and copying it and improving a little bit on Amar's designs. But then we see this new anti-gravity button that is creating an export and then exporting it to anti-gravity. And I can go and open in the IDE. And I think these are the types of creative interactions that web-based vibe coding tools can be particularly useful for, because if we had went and jammed on this feature, we probably would have constrained ourselves to existing patterns in AI Studio. And in this case, I told the model, be creative, think outside the box. And I've played with this one a bunch. Sometimes it gives a command line interface for showing the status of the export, et cetera. So I think it's a super cool way for you to ideate on new ideas for UI and kind of expand on your product. But I'll hand it back to Amar.
Let's do it. And then the other thing that Gemini 3 has been really impressed us with is just making video games. And so this one was, again, pretty simple prompts. Make this racing game where I have a bot now at a start screen. And so you can see I got this 3D racing game in Three.js. I drew all the things. I'm racing with a bot here. And then one thing I added for myself to cheat is I can just boost away and beat the bot. So pretty nice. But the thing I want to tease, actually, is that all of these apps so far have been front-end React apps. And so the thing that's coming very, very soon to AI Studio is going to be back-end support and full-stack runtime. So if you want to install Shad CN, if you want to do all of those things, you'll be able to do that, again, with one prompt. And the principle with AI Studio here is that we don't want you to think about those details. You should just be able to ask, I want to make a multiplayer app, and we know that you need to use Express and wire that all up for you. And abstract all those details away. So we're going to try something a little risky here, which is we did turn this racing game into a multiplayer one. This was, again, a couple of prompts. So we're going to put a QR code up if you want to join us in the racing game.
We've never tried with nearly this many people, so we'll see.
Hopefully this works.
Yeah.
But QR code's up here. So if you scan that, it really should load the game. I'm really afraid of how this is going to explode.
Yeah. Oh, here we go.
Got all these cars loading in.
Nice.
So yeah, if people have scanned that, we can switch back to the game. Okay. Oh my God. So yeah, just hit ready when you're all ready. Oh boy. I think this lobby is going to explode.
Yeah. Everyone leave.
So this is where I shouldn't have added collisions with other cars, because you could clearly see that we're bouncing around. Yeah. 19 players, 20 players. I don't know if this race will ever start, but we're all blocked on the start line. But 23 players, pretty cool. Yeah, you do all have to hit ready for us to start this race. So, so we might be here all day. Yeah. But yeah, that is pretty incredible. I can't start this race, so do you want to wrap up? We'll see you all in here. That's pretty cool. The runtime didn't explode.
I think we're super excited not only about the multiplayer game, so next time we'll have even more of you folks join, but also the extensibility that comes with a full stack runtime. We want to make it super easy for you to integrate with our 1P and popular third-party APIs, et cetera. So very exciting next few months on the AI Studio vibe coding side, and super excited for you all to try it. But I think the one thing I want to step back and emphasize was what makes us so excited about this project and the work that a lot of us are doing is that we get to be the first generation of engineers who are building tools for a world where anyone can build software. So I think what's beautiful about things like vibe coding is watching people. We were actually talking to a tech support person earlier this morning who said they started vibe coding in AI Studio after seeing a YouTube video. And we're really democratizing who can create things, and we're all getting to build those tools that enable that. And I think it forces us to rethink the paradigms that we've become so used to. So it may not be your base IDE that people are starting from, but how can we intuit as much of the user intent as possible? And that's what we want to do with full stack runtime in AI Studio, is make it very easy to not have to think about, I want to add a database, but if your app needs storage, it'll have storage. If you want to if you have an e-commerce app, we'll add a payment solution and make it as easy as possible to build the future of software. So thank you folks for joining us. If you have any cool examples you've built or questions, feel free to ping me and Amar on Twitter. And yeah, enjoy the rest of the day.
Yeah, thank you.
What if the reason you're struggling with agents is not the agents themselves, but the environments in which they operate? Here to present us with 8 categories to make your codebase agent-ready is co-founder and CTO of Factory, Reyes.
Hey everybody, my name's Eno. Really pumped to talk today about something that at Factory we care a lot about. When we started 2.5 years ago, we said that our mission is to bring autonomy to software engineering. And that is like got a ton of loaded words in it. That sounds a little buzzwordy right now, but I think that my goal is that you guys leave this like roughly 20 minutes with a bunch of insights that will apply to your organization and the teams that you build, the companies you advise, and if you're building products in the space, insight into like sort of maybe how to think about building autonomous systems and also making your engineering org one that's able to use agents really successfully. A sort of like plus of this is that ideally this applies to any tools you're using that involve AI, so it won't be specific to like our product or any of the other amazing tools out there. I'd like to start with a little bit about, Andrej Karpathy had a very well-timed tweet, so of course I'm going to mention it. He kind of talked about this idea of software 2.0 coming from the ability to verify things, right? This is something that's in sort of like the mind of Silicon Valley right now, as the most frontier models are built with post-training that involve lots of like verifiable tasks. And really, I think the most interesting thing here is the sort of frontier and boundary of what can be solved by AI systems is really just a sort of an input function of whether or not you can specify an objective and search through the space of possible solutions, right? And so we are used to building software purely via specification. We say like the algorithm does this and like input is X, output is Y. But if you sort of shift your mindset to thinking about automation via verification, it is a little bit of a difference in what is possible to build. And there is another great blog post by Jason where he talks about the asymmetry of verification. This is like pretty intuitive to most people who know about like P versus NP. It's like a thing that a lot of people have talked about throughout the like history of computing and software, but there are a ton of tasks that are much easier to verify than they are to solve, and vice versa. But the most interesting sorts of easy to verify problems are ones where there's an objective truth, they're pretty quick to validate whether or not they're true, they're scalable, so validating a bunch of these things maybe in parallel is easy. It's low noise, so your chance of validating it is like really, really high. And they have continuous sort of signals. It's not just like a binary yes, no, but like maybe you're 30%, 70%, 100% accurate or correct. And the reason I bring both these things up is software development is highly verifiable, right? This is like the frontier. It's why software development agents are the most advanced agents in the world right now. And there's so much work that has been put in over the last 20 to 30 years around the automated validation and verification of software that you build. Testing, right? Unit tests, end-to-end tests, QA tests, right? The frontier of this is expanding. There's tons of cool companies like BrowserBase and computer use agents and all these things that are making it easier to validate really complex visual or front-end changes. Docs, right? Having like an open API spec for your code base is something that can be automated, it's validated. I can go through and enumerate a bunch of these, but I actually think it is sort of a nice checklist for yourself, right? Do you have some automated validation for the format of your code? Do you have linters? These things for professional software engineers are sort of like, oh, of course we do. But I think you can go a step further, right? This is where that continuous validation component comes in. Do you have linters that are so opinionated that a coding agent will always make code that is exactly at the level of what your senior engineers will produce? How do you do that? What does that even mean, right? Do you have tests that will fail when AI slop has been introduced, and when high-quality AI code is introduced, those tests pass, right? These additional layers of validators are things that most code bases actually lack, because humans are pretty good at handling most of this stuff without the automated validation, right? Your company may be at some test coverage rate that's like 50% or 60%, and that's good enough because humans will test manually. You may have a flaky build that every third build, it sort of fails, and everyone at your company secretly hates it, but no one says anything, right? These are the sorts of things that we know are true about large code bases. And as you scale out to extremely large code bases, organizations with 44,000 plus engineers, right? this starts to become a very accepted norm, that the bar is sort of maybe at 50% or 60%. And the reality is most software orgs can actually scale like that. It's sort of fine to be at that lower barrier. But when you start introducing AI agents into your software development lifecycle, and I don't just mean in interactive coding, but really across the board, right? Review, documentation, testing, all this stuff, this breaks their capabilities. Most of you have probably only seen an AI agent that operates in a code base that has a decent amount of validation. I think a lot of the best companies in the world right now actually have introduced very rigorous validation criteria, and it means that their ability to use agents is significantly greater than your like average developer. And if you think about it, this like traditional loop of understanding a problem, designing a solution to the problem, coding it out, and then testing it sort of shifts if you have really rigorous validation. It becomes a process of, when you're using agents, specifying the constraints by which you would like to be validated and what should be built, generating solutions to that outcome, verifying both with your automated validation as well as with your own intuition, and then iteration, where you continue to iterate on that loop. This move from sort of like traditional development to specification-driven development is one that we're starting to see sort of bleed into all of the different tools. Different tools have spec mode. Droids have like, or Droid is our coding agent, have like specification mode, plan mode. There are entire IDEs that orient you around this like specification-driven flow. And if you combine these two things together, this is really how you build reliable and high-quality solutions. So if you think about it, what is like the best decision for you to make as an organization? Is it spending 45 days comparing every single possible coding tool in the space and then determining that one tool is slightly better because it's 10% more accurate at Swybench? Or is it making changes to your organizational practices that enable all of these coding agents to succeed, and then picking one that your developers like, or honestly letting people choose from the tons of amazing tools out there? And when you have these validation criteria, you can actually introduce way more complex AI workflows to your organization, right? If you cannot automatically validate whether or not a PR is like reasonably successful or has code that won't definitely break prod, you are not going to be parallelizing several like agents at once, right? You are not going to be decomposing a large-scale modernization project into a bunch of different subtasks. Like that is a very frontier-style task to use AI for. And if the single task execution, right, the simple, I would like to get this done, here's exactly how I'd like it to be done, and here's how you should validate. If that does not work nearly 100% of the time, you can sort of forget successfully using these other things at scale in your company. When you get into other tools like code review, right? If you want a really high quality AI-generated code review, you need documentation for your AI systems. And yes, agents will get better at picking out whether or not to run lint or test. They will get better at finding solutions when you don't have explicit pointers. They'll get better at search. But they won't get better at just randomly creating this validation criteria out of thin air, right? This is why we believe software developers, by the way, are going to continue to be heavily involved in the process of building software, because your role starts to shift to curating the sort of environment and garden that your software is built from. You're setting the constraints, you're building these automations and introducing continued opinionatedness into these automations. And if your company doesn't have at least all of these, right, then that means that there's a lot of work that you can do, totally absent of a procurement cycle or buying one tool or trying out another one. And so plug is that we help organizations do this, right? I think that it's great to have tools that allow you to go in and assess this stuff, have ROI analytics that let you interact. But I think that for most organizations, there is actually like a very clear way to do this, right? You can go and analyze where are you across those 8 different pillars of like automated validation. Do you have a linter? How good is the linter? Do you have agents.md files, an open standard that almost every single coding agent supports? You can improve and systematically enhance these different validation criteria, and you can go through and say, well, we're seeing that coding agents are reliable enough for a senior developer to use, but our junior developers, if you have the tooling to tell, by the way, like which developer is using what tools, you can ask questions like, maybe our junior developers are actually totally unable to use these coding agents. And you'll learn that the reason why is not because they're like more incompetent or they don't know how to use the tool, but because there's these niche practices that you don't have automated validation for, right? And if you think about what is the difference between a like Google or a Meta and a still large but like 2,000 person engineering org, the difference is that a new grad with effectively zero context can go and ship a change to make YouTube's like boundary like slightly more round, and it won't, with some degree of confidence, take down YouTube for like 1 billion users, right? And the reason that's possible is because of the insane amounts of validation that have to happen on that code for it to be shipped. The big difference that we now have is we have coding agents that can go and identify exactly where these gaps are, and they can actually remediate those fixes, right? So you can ask a coding agent, could you figure out where we're not being opinionated enough about our linters? You can ask a coding agent to generate tests. We have an engineer named Alvin who, I love this quote, he said, a slop test is better than no test. And I think that that's slightly controversial, but the thing that I would argue here is that just having something there, right, that it passes when changes are correct and somewhat accurately matches to the spec of what you want built, people will enhance it, they'll upgrade it, and other agents will actually notice these tests. They will follow the patterns. So the more opinionated you get, the faster the cycle continues. So I think that what you guys should be thinking about is what are the feedback loops in our organization that we are catering towards? If you have better agents, they will make the environment better, which will make the agents better, which will mean you have more time to make the environment better. And this is sort of the new DevX loop as well that organizations can invest in. That will enhance all of the tools that you're procuring, right? So no matter whether it's a code review tool, a coding agent, et cetera, they will all benefit. And I would argue that it sort of shifts your mental model about what you're, as a leader, investing in when you're investing in your software org. Right now, the idea of OpEx as like the input to engineering projects, like we are investing in, we want more people. In order to solve this problem, we need 10 more people. I would argue that the other thing that you can now start investing in is this environment feedback loop that enables these additional people to be significantly more successful, right? And I think that that's the feedback loop that can actually take quite a lot of value because coding agents can just scale this out. So, all of this is to say, there's a lot that can be done outside of the like product itself to enable these systems. And the best coding agents will actually take advantage of these validation loops, right? So if your coding agent isn't proactively seeking linters, tests, et cetera, then at the end of the day, it's not going to be as good as one that will seek those validation criteria. And in addition to that, when organizations think about these sorts of things, if you're the person who's able to say, here's my opinion, here's how I want software to be built, it scales your capabilities out greater than ever before. Like one opinionated engineer can actually meaningfully change the velocity of the entire business if you take this to heart and you have a way to measure and systematically improve. So that's the majority of what I came here to say. I think that the only thing that I'd leave you with is that when you think about where AI is going and like where we're at today, we're still really early in our journey of using software development agents. If you want a world where the moment a customer issue comes in, a bug is filed, that ticket is picked up, a coding agent executes on that, that feedback is presented to a developer, they click approve, that code is merged and deployed to production in a feedback loop that takes maybe an hour, 2 hours, that will be possible, right? We all are sort of skeptical about that fully autonomous flow. That is technically feasible today. The limiter is not the capability of the coding agent. The limit is your organization's validation criteria. So this is like an investment that made today will make your organization not 1.5x, not 2x, but that is where the real like 5x, 6x, 7x comes from. And it's sort of an easy thing to say, and it's an unfortunate story, because what that means is you have to invest in this. It's not something that like AI will just magically give to you. It's a choice that you as an organization have. And if you make it now, I can guarantee you that you will be in the top 5% of organizations in terms of eng velocity, and you will outcompete everybody else in the field. So Highly recommend investing in this sort of stuff, and hopefully you found this helpful and have some lessons to take home. Thanks.
Our next presenter is the co-founder and CTO of SourceGraph and AmpCode, here to provide an overview of AmpCode's approach to AI-powered software development. Please join me in welcoming to the stage Beyang Liu.
Hey everyone, how's everyone doing today? Yeah, cool. Pretty cool conference, huh? So yeah, my name is Beyang. I'm here to talk about AMP. AMP is an opinionated frontier agent. So before I get into what that means, who are we? We're the bunch of weirdos downstairs at the booth with the weird Pied Piper dude on the floating golden fish. And I think that kind of captures the ethos of what we're trying to do with AMP. We're trying to lean into that sense of awe and absurdity that I think we all experience right now, living in this weird world we're living in, where agents are writing an increasingly large amount of our code. And it's just kind of like weird and magical. Like if you imagine how you were working like a year ago compared to how you're working now, it feels completely different. And so we're embracing that sense of change, and we really want to be the agent research lab that's sort of like living 1 year in the future and figuring out how this all kind of pans out. Okay, so what is AMP actually? Well, it's a coding agent that you can invoke from the terminal. So here's our terminal UI. We actually ended up building a complete terminal UI framework up from scratch because we wanted to take advantage of all the capabilities of modern terminals. And one of the balances we try to strike in this UI is we try to show the right amount of information to the user that conveys what the agent is doing without overwhelming you with every single token of explanation that the model is generating. We stream the diffs that it's making. We show you what CLI commands it's using. And if you look in the bottom right-hand corner there, you'll see a little Emacs 30.1 thing. This also connects to the editor that you're using, where it collects diagnostics. So Emacs, NeoVim, JetBrains. You can connect the CLI to your editor to collect additional information that's relevant to the task at hand. And so this particular video is just AMP implementing a small feature to itself. We asked it actually to add a little help button in the bottom left-hand corner. And so that's just a quick demo to show you that the agent is pretty good at finding the relevant context and iterating towards that. We also have an editor experience. So we've not found the motivation yet to fork VS Code. Maybe we will in the future, but right now, this installs into VS Code or any of its derivatives, Cursor, Windsurf, Anti-Gravity. And the idea here is you really write all your code through this agent panel, at least I do. I actually spend very little time actually manually editing code now. And one of the bottlenecks we identified in the editor is, I don't know about you, but I spend most of my time effectively doing code review now, just in the editor, trying to read through all the agent output. That's the thing that constrains me from fully parallelizing 2-3x the number of agents that I can run at a given time. So we built a review interface that I'll talk about in more depth in a bit that kind of helps you streamline that process, guides you through the process of understanding what the agent wrote so that you can ensure that you're not shipping something that's super sloppy or spaghetti. Okay, so I hear all of you thinking like, okay, yeah, it looks pretty, but what actually is different? Why is this better than the 20 other coding agents here? And I think the best way to convey this is I'm not going to try to convince you that it's better. I think that is ultimately up to you trying different things out and seeing what actually works. But I am going to try to convince you that we're thinking about things in a very different, opinionated, and weird manner. So I want to take you on the journey of us building AMP and all the different sort of contrarian or spicy takes that we've made decision-wise in the architecture of the agent along the way. Okay, so let's start at the beginning. Hello agent. What is an agent at its core? Well, all an agent is, as I'm sure most of you know, it's a for loop with tool calls and a model in the middle. And the reason I want to present this slide is because thinking of it this way, it really tells you what sort of levers you have to pull as a builder of agent. There's certain things that you can change. You can change the choice of model, you can change the tool descriptions, and you can change how the model iterates with those tools. And those are effectively your levers. Seems like a few amount of levers, but just like programming languages, all those are syntactic sugar around if statements and for loops. You can get a surprisingly wide variance of behaviors and complexity out of that.
And so one of the key levers in building any agent is a set of tools. And these days, you cannot talk about tools without talking about MCP. So one of the early decisions we had to make in building AMP is, how much do we invest in the MCP integrations? And MCP is this amazing new protocol that's gotten everyone and their mom thinking about how to provide context to agents. Should we lean into that, or should we start building our own custom tool set? And our very opinionated take, I think this is maybe less controversial now than it was back in April, was that we should really actually focus most of our attention on the core set of tools within AMP. And that's really for two reasons. One is because the more you work with agents, the more you find out that what you're trying to do is identify these feedback loops and help the agent close them. And in order to do that, you need a refined tool set that is really geared toward helping the agent find those loops. And you cannot do that with MCP servers. The creator of the MCP server doesn't know what your agent is trying to do, and so they're not going to tune the tool descriptions to what you're trying to accomplish. And then the second piece of this is context confusion. So the more tools that you add into the context window, the more things that the agent has to choose from. And if the tools aren't relevant to the task at hand, it ends up getting confused. So we've leaned hard into this custom tool set, and you'll see a little bit more about that in just a little bit. But before that, I wanted to call out another issue with tool use, which is it's not just tool descriptions that eat up context, it's the tool calls themselves that also eat up context. And so everyone who's built an agent has run into a context exhaustion problem, where if you use any sort of coding agent, if it's good, it's going to go out and try to find a bunch of relevant context by grepping and reading files first. And by the time it gets to editing, there's only a small amount of context window left, and so maybe it has to stop prematurely. And so the naive way to fix this is just to prompt it to do less reads, so you can do more iterations on the edit side. But then this leads to another failure mode, which I call the doom loop mode, which is it doesn't gather enough context in the beginning, and so it ends up not figuring out what it needs to do and just retries the same thing over and over again. And so the way to solve this is really with subagents. So subagents are the analog to subroutine calls in regular programming languages. It's how you can factor out the context window used for a subtask into a separate context window, which is the subagent's context window. It can do all the things it needs, and then at the end of the day, it only returns the relevant results to the main agent window. So subagents are effectively a way to conserve and extend the context window of your main agent. So subagents are great. I think everyone building agents has probably heard of or used subagents so far, but I think we have a unique take on subagents, which is we're not really doing generic subagents, where you kind of tweak the system prompt and tweak the tool set a little bit. We've really leaned into our subagents. And so we have 3 to 4 really core subagents that really extend the functionality and capability of AMP itself. The first one is something that we call the Finder. This is effectively our Codebase search subagent. It's gone through an evolution of models, and we've ended up at the point now where we're using a relatively small and quick model to drive a limited tool set that we found really is optimal for quickly discovering relevant context within the code base. Another subagent that we've implemented is the thing that we call the oracle. So this is how AMP does reasoning. So in contrast to most agents which implement reasoning in the model selection part of the experience, we found the best way to implement reasoning models is really through a subagent. What that allows you to do is preserve the relative snappiness in the main agent, as well as its ability to use a variety of different tools. And then only when you need to debug a tricky problem or plan something very nuanced, it drops into this Oracle subagent and figures things out. And this is something that's kind of magical. It's like anytime the main agent has trouble figuring out something, and I'm like, I don't want to spend 1 to 2 hours going down this rabbit hole, I just tag the Oracle. So invoke the Oracle, think really hard. I go Alt-Tab, check my email for a bit, and sometimes it takes a few minutes because it's thinking really deeply, but I think 4 out of 5 times, it just magically finds the underlying issue. We also have a librarian subagent, which is meant to fetch context beyond the code base, so from libraries and frameworks that you depend on. And then there's a new experimental subagent that we call the Kraken. Its job is it doesn't edit code files one by one. It really is all about writing code mods to do these kind of large-scale refactors. So we're leaning hard into the subagents, and that's really in contrast to a lot of the existing coding agents. I think almost every other coding agent implements a model selector as one of the core UX components. And we just don't think that this is the architecture of the future. I get that developers like choice, or at least the possibility of choice. But the problem with choice is that there's also a paradox of choice. The more choices that you have, the more cognitive burden it is to choose from these different models. And that means at the architectural level, if you have n different models and one agent harness that you can only lightly customize to each model, it means you're never really optimizing for what any one given model can do. And so AMP's architecture is much more agent-oriented. We have two top-level agents, a smart agent and a rush agent. And the smart agent is the one that has access to all those fancy sub-agents and can do a lot of things. It's a little bit slower, but you can hand it more complex instructions. And then the rush agent is for those kind of like in-the-loop tasks where you want to be tight in the loop and you're making quick targeted edits to the code. And why do we have two top-level agents? It's really, we're trying to kind of like pick points along the frontier of intelligence and speed that are meaningful to the user experience. So in talking to our users, we found that there's kind of two modalities for invoking agents now. One is you kind of like spin off a task and have it run, and then review the code when it's finished asynchronously. Or you want to be in the loop, quickly having the agent make edits while you quickly review them one by one, kind of like babysitting the agent in the inner loop. And we're very intentional about the model choice here. We've only switched the smart model once, and that was actually 2 days ago when Gemini 3 was released. And I think the reaction to Gemini 3 has been really interesting to watch. I think you'll see widely different behavior from Gemini 3 in different agent settings. So for those of you who've tried it out in other settings, I highly encourage you to try it in AMP. We did a lot of testing in the week before the release to optimize the smart agent to take full advantage of its capabilities. And we're absolutely loving it. We're still working through some kinks, obviously, because it's a new model. But we feel confident that it's again, moved the frontier of what's possible. OK, so we talked a lot about like agent construction and the behavior. I want to talk a little bit about the UI layer of agents as well. So editor versus terminal, we're doing both. And I think that's because both of them tackle kind of like different modalities of working. But we do have opinionated takes in each interface. So in the editor, I think of my editor now more as a reeditor more than anything else. Because, I don't know, like if you're using agents heavily, I don't think you're really editing all that much in your editor anymore. You're mainly driving edits through the agent panel, which is what you see on the right-hand side, or the right-hand side here. And then what I do in my editor is I pop over to the side panel, which is optimized for reviewing different diffs. So we actually built a custom diff viewer for the way that people are consuming agentic output. You can select any arbitrary commit range, quickly view through the file level diffs. All the diffs are editable, and you have full code navigation, so go to definition, find references. And there's a feature at the bottom that gives you a tour of the change. So it actually guides you through which files you should read first, because I find half the battle when reviewing a large change is figuring out where to start. So the GUI aspect of the editor allows us to build a very rich experience for this type of thing. And then meanwhile in the terminal, we really want to take full advantage of the features and rendering capabilities of modern terminals. So we actually have one of the core contributors to Ghosty, the open source terminal, that built a TUI framework from scratch to power the AMP TUI. So one of the nice things that we can do is, just to point out a little detail, the green color of the diff rendering on the left-hand side terminal, that's actually, we can have the terminal mix in the color green with whatever background color it's using. So that allows for a much nicer display. At the same time, we know that people use all sorts of terminals, including like terminals in JetBrains or VS Code and other editors. And so we've added the ability to gracefully degrade. So even if you're using AMP in like the default Mac OS terminal, it falls back to the capabilities that are available in that setting. Another aspect about how we're thinking about coding agents is really from the how do we get people to learn this new craft. Like we think that human developers are going to be around for a long, long time, but we essentially have to relearn the craft of how to code together. And so one of the first features that we built in AMP was the ability to share threads with your teammates. So if you're using AMP on your team, you can go and see like how much code people are changing with AMP over a given period of time, and you can poke into specific threads to see how they're doing things. And people love this feature because essentially like link threads to AMP and just say like, hey, here's a cool prompting technique that I discovered, try it like this, or hey, here it got stuck here, can you help me think through how better to connect the agent with the feedback loop to get further. Another aspect of enabling more people to experience coding agents and learn how they work is by making it more accessible from an economic perspective. So remember the smart and rush agents at the top level. Smart models remain relatively expensive today, but rush models are getting cheaper and cheaper, but not yet free. And so we're thinking about more and more, like one of the biggest barriers to using agents fully is actually cost right now. Like if you go to like college campuses and talk to students, the actual number of people who have used a coding agent is actually much smaller than I would have thought, given young people's propensity to adopt new technology. A lot of this cost. So someone had the crazy idea on our team, like, hey, you know what we could do? We could ship ads in your terminal. And at first it was like, nah, that'll never work. But the more and more we thought about it, and the more and more like inference costs started declining, we were like, yeah, maybe. So we actually shipped a mini ad network that delivers ads for other developer tools in AMP, in the terminal, and in the editor. They're very subtle, so I don't know if you can spot the ad in this screenshot, but we try to make them non-intrusive. But this effectively allows us to sponsor inference in the Rush agent so that more people are able to experience this on their side projects and such. Okay, so AMP is AMP. We are, like I said, we think of ourselves as like an agentic research lab. So we're not about hype. We don't do any sort of like paid developer influencer marketing. But I like to call out some cool people that I think are using AMP because it shows for the type of people that we're really selecting for. I don't think AMP is for everyone at this point. We're really trying to target the like small percentage of people who want to live a little bit in the future. And so we have folks like Mitchell Hashimoto, the founder and ex-CEO of HashiCorp. He's building Ghosty now. That's his kind of passion project, and he's using AMP to drive a lot of the changes that he makes to that terminal. And then we also have folks like Hamil Hussein, who's, I think, probably like the leading authority on AI evals. And at least as of a couple weeks ago, he was saying that AMP was his favorite coding agent. And so neither of them are on the team or have invested us in any way, but we're just thrilled that they seem to like what we're building. And then if other folks are interested in kind of like coming along with us in this journey and trying to push the frontier of what agents can do, we've also started a community of builders. And using AMP is not a requirement to join this community. It's run by Ryan Carson, who is a former startup Treehouse, taught over 1 million people to code. And now this is his passion project. It's essentially like if you're building with agents and you're experimenting with how to push them further and further. There's Ryan right there. It's all about kind of like tapping into that sense of awe and wonder with a peer group that is also leaning into that sense of strangeness and experimentation. So what does this involve? It involves like regular interviews with people. We like to feature people who are building interesting things or using agents in interesting ways. And we also do in-person events. So we had a very nice dinner last night where we got a bunch of people together and had very interesting conversations spanning from actually building with coding agents to more philosophical discussions about the nature of AI and things like that. So that's it for me. Hopefully this has intrigued you. Again, I don't expect all of you to be convinced that we are building the best frontier coding agent, but at the very least, I hope I've kind of demonstrated how we're leaning into the weird and thinking about things differently. So if that's interesting to you, come say hi at our booth. Just look for the weird Pied Piper man riding the golden fish. Thank you.
Our next speaker will discuss how AI-generated kernels can meaningfully speed up custom PyTorch code without any human effort. Please join me in welcoming to the stage the co-founder of Gimlet Labs, Natalie Serino.
Hey everyone, how's it going? So my name is Natalie. I'm a co-founder of Gimlet Labs. And yeah, just a little bit of background about why Gimlet's looking at AI-generated kernels. Let's just get right to it. We're building an agentic inference cloud focused on performance and efficiency. And the thing that we've seen with all these talks so far is with agents, they're not just one chat model. They're complex pipelines of multiple models, multiple stages, tool calls, and the compute backing these is inherently should be heterogeneous. So what we do is we automatically split up and orchestrate these agentic workloads across optimal hardware, which can be different vendors and different sizes. This can present a problem at the kernel level because a lot of times you have models that are really optimized just for one hardware. So what we started looking at is, can we use AI to help automatically port different segments of agentic workloads to hardware that it hasn't necessarily been optimized for? So just to clarify something really quick, because we run into this a lot, what do I mean by kernels? I do not mean AI generating operating systems like the Linux kernel or things like that. What I mean is kernels at the sense of like transformer architecture, like the individual like functions that perform like massive parallel computations, leveraging like all the crazy amounts of threads that GPUs have. So yes, people will be like, oh, how are you going to generate an operating system? I think maybe we're not quite there yet, but one day. So why use AI to do this? So I think there's a few reasons. So we know that optimizing low-level kernels can make workloads like ML workloads significantly faster. So here we have like, it's probably too small to see, but it's a blog from NVIDIA where they implemented a different attention and it allowed them to like get 3x throughput on a llama model. So these like implementations can make a major difference from a performance perspective. But at the same time, if you just search Twitter, everyone's whining about how it's impossible to find these people, and the people that exist are like really overtaxed with so much to do, so much work. There's just not enough experts to be able to solve every problem in this space right now. And the problem explodes because you have so many frameworks and so many ways to write kernels, from things like CUDA and like Triton to Palace to things like that are device specific like Metal. And you have different hardware platforms too. And each of these hardware platforms, even within a single vendor, has different characteristics. We've seen, for example, that some of the new like hardware from NVIDIA, like some of the old kind of like DSLs weren't working as well on it because the different hardware has different properties, it has different features, it has different characteristics, different cache sizes, et cetera, all of which impact the optimized implementation from a kernel perspective. So we, and many others in the space have thought it would be great if AI could help us with this problem, where you could potentially give it PyTorch code and then generate optimized implementations for whatever hardware you're trying to run that workload on. So I think when you're trying to use an agent for something, you have to start with what the human workflow is. And the human workflow today, when you have that like really hardcore kernel expert, let's say they're trying to port a new like workload over to Metal, right? What they'll do is they'll say, okay, I have this implementation, maybe I have a CUDA version, maybe I don't, and I'm going to try something. I'll see if it compiles. Most of the time, maybe not. I'll see if it runs, see if it's correct, and if none of those are the case, you just pass that back into the human context, so to speak. And then once you get something that's working, then you start looking at the profiling information in depth and just hammering down, like, this is the bottleneck now, this is the bottleneck now, this is the bottleneck now. It's a very iterative process. So I think that, you know, basically the idea here is to put AI as the kind of like where the human would go in that same loop, right? So the agentic flow here is to make sure it compiles and it executes and it's correct, and then from there optimizing it. So this is something that I would say is like very new technology. There's a lot of interest here, but there's some things that it's good at and some things that it's still kind of in development for, and so let's dive into some of the specifics. So this is a quick demo of our system. The font's kind of small, but we're passing into a CLI tool, a PyTorch workload, targeting it to an H100, and the system has explored a bunch of candidate optimizations. It's comparing to eager mode and torch compile, and it found one candidate that was 22% faster than the torch compile baseline. So this was a real case. It just sped up because it actually took about 20 minutes. So there's some challenges, though, with measuring these agents at kernel synthesis. So like, first of all, you have to figure out what your definition of correct is. When you're dealing with floating point, this is always a question. You can do different types of tolerances, but you also need to make sure your input sizes are well selected. If you're only passing in really small input sizes, it can cause problems with the benchmarking where you're measuring the overhead, not the actual kernel, as the critical path. You also have to make sure you're reliably measuring performance. So if you just do a naive timer.start on your implementation, it's probably going to be wrong. And there was a great blog that had a diagram for this, because you're basically measuring the launch time, not the execution time. So there's a bunch of kind of gotchas like that, that when you're building an agentic system like this, you have to be really, really careful about catching. Doing things like warm-ups and cache clearing, because a lot of times you'll have the original implementation run and then the new implementation run, and then the original one's result is cached and the new one fetches it. So you have all kinds of things like that that you have to be really neurotic about, otherwise you might get bad results. You also need great benchmarks for this. I think that someone said earlier that there's not a ton of examples of low-level kernels across all these different hardware platforms. And so the input data is a challenge, and also benchmarking it is a challenge. Like, how do you know if your agent is better? You change the prompt to it. How do you know? It's the same story we hear with every agent here, basically. So we have some preliminary results that we're sharing right now on Apple's M4 using the Metal framework. And this is on the kernel bench benchmark, the v0.1 version of it, which is the latest one. So what we can see here is results across 250 problems, and it compares to either Torch compile or eager mode, depending on which one of those is faster. So with the kernel bench data set, we have different tiers of problems, with L1 being the easiest, or simplest rather, and L3 being like more complex. So what we can see for the standalone agent is that we see an average speed up of about 25% or 24%. And the sweet spot is those moderately complex problems. It seems honestly the same as like a lot of coding problems, where it's good at moderately complex things, but then you push it too far and the performance drops off. So an interesting challenge here is going to be, how do we make these agents perform better on more complex problems that they're going to have to break down and execute? There we go. Let's talk about a couple of examples, because I love to just see example code. So this was a success case where the model found a case where we could do kernel fusion. So for those that aren't that familiar with GPU kernels, kernel fusion is one of the most go-to techniques in kernel optimization, where you say, I have two kernels. Let's say in this case, it was like a convolution, softmax, bias, scaling, and sigmoid. So those were 5 ops. And what the agent did was it took 4 of those ops, and instead of running individual functions for those, it made a mega function that compacted them all together. So kernel fusion isn't new. It's something that Torch compile already does quite well. But it's a common way that we found agents can speed up these workloads, because you can really customize it to the specific use case. So this result achieved a 40% speed up over the baseline on the M4. And just kind of like zooming into what happened, the agent wrote a fused op. So it basically wrote like C++ code that it put as kind of an inline string with the PyTorch code. And then it called that fused operation in the forward pass of the model. And then that fused implementation, we can see a snippet of it up here, where it's basically taking those 4 ops and putting them together in 1 mega op. And so this was done automatically. Sometimes though, like writing low-level kernels isn't the best optimization that we can get. We had another case which was on a level 1 problem, which basically improved the performance by 80%. And the insight the agent had in this case was the operation in Metal for average pool 1D was not as optimized as some other ops that are much more optimized on Metal. So what it did was it actually rewrote the PyTorch code to use the more optimized op and re-express the same problem in a different way. So to dive into this, the average pool 1D is basically taking averages across like 1 dimension. So like you can see that that input vector could produce the output vector with 5 and 7 averaging to 6 and so on. So if you express that same thing as a convolution, you can get the same result. So if you do the math, it will lead to that same result. And so that's what the agent did. Basically what it did was it said, hey, instead of doing the original call to the baseline op, let's generate that weights matrix and execute this as a convolution, because I know that that's really fast on Metal. There's also an interesting algorithmic optimization case. This was for a level 3 problem, so it was more complex, where basically the agent figured out that it could combine 2 operations into a single operation at the PyTorch level, not even using low-level kernels. So what we can see is that basically it fused it, it rewrote it as Python code, and calls that single convolution, and that's a lot more efficient because you don't have to launch as many ops. But this does not always work. This is not a silver bullet, and I think that's really important to emphasize. So a case where the agent totally face-planted was on matrix multiplication. And it wrote a custom CUDA kernel for this, but it was a lot slower than the baseline. And the thing is with this is matrix multiply is one of the most hand-optimized ops that exists. So it's not that surprising that an agent would not do as well as something that a human expert spent a long time on. So this is an area that it did not work. Another case was a case that we saw which had a 71,000x speedup, and anything like that should trigger your suspicion brain. Wow, 71,000, great, we're done. It's, this technology is worth billions of dollars, right? No. So basically, what happened? So this operation is basically saying, give me inputs, and I'm going to make sure they fall between -1 and 1. Okay, that's what the operation being tested was. So the agent figured out that for all of the test cases, this was already the case. So it wrote a nice long comment saying, this is actually not necessary, so just output the input. So you could argue this is the agent being smart because it's pruning unnecessary work, but I think a lot of us would agree that it's not in the spirit of what we're trying to benchmark here. So we've excluded cases like this from our analysis, but it is interesting because maybe some of the times you would want it to do something like that. And I think this is part of where the human element comes in with these agents. Sometimes the agent does something that, depending on your definition of what you want to see, could be good or it could be bad. And so that's where the human part kind of weighs in. So I keep drawing parallels to other kinds of coding agents because even though this is kind of a niche, low-level domain, I don't think that the story is fundamentally different. We see standalone agents are really good at cheaply generating lots of different ideas and lots of possibilities to explore. They're good at slurping in a ton of different contexts and seeing what helps. And they're really good at doing these level 1 and level 2 tasks. For example, we're still not asking AI agents to write the Linux kernel. But what is still needed is robust quality and performance validation. We need to make sure that the agents aren't cheating, and we need to make sure that the results are actually correct. We need empirical data from hardware in the loop to guide the search and optimization, because it's actually really hard to look at low-level code and know how it's going to perform on the hardware. We still heavily rely on looking on profiling data and things like that. And we also need the human in the loop to supervise the results and guide the work. So design of a modern agent, you have multiple sub-agents that are working together. You have that human in the loop and a purpose-built harness for that task. And I think this is the pattern we've seen throughout this conference. So just to get a little bit into kind of what that architecture looks like, and this is what we're building at Gimlet, you have a supervisor agent, which takes in input code, target hardware, and then also human prompting, because humans still can really guide the best paths for optimization. That supervisor is in charge of managing the work. It deploys the synthesis agentic swarm, which collectively work together to come up with ideas for optimizations, and they are basically the idea factory, coming up with new techniques. Those ideas get sent to the verification agent, which is running them on actual hardware in a hardware-in-the-loop system to see how they do. And that verification agent needs to be extremely strict about making sure that no funny business is happening, and that's a major part of the challenge. So just a couple more realistic case studies that are not benchmarks. We got really excited because we ran this on a vision transformer model, and I don't know if you can see, but basically the original vanilla implementation using Torch Compile and our generated code using Torch Compile, ours was twice as fast. So this was like a hooray moment. So the speedups were promising, but then it turned out the optimization was just swapping out the original attention module for SDPA, which is a more optimized attention module. And this is the kind of thing that, yes, that's true, that is a valid optimization, but I wouldn't necessarily call it rocket science. So we consider that to be a trivial case study where if you're not using a more optimized attention module, maybe you haven't actually optimized your workload that much yet. But we do still see interesting results for full models when we have human prompting. And one case for this was an audio encoder model, where it generated 6 custom kernels for the workload, specialized for the RTX 6000 Blackwell. And the results were strong. It was about 70% faster, both implementations using Torch Compile. So just to kind of show an example, we load in line 6 different fused kernels and then call them in the code. And the nice thing about this approach, even though it's a little weird declaring these as strings, is that you have like a completely API-compatible swap and replacement for the original module in PyTorch. So where are we with AI-driven kernel optimization? I think, like I said before, this is not a silver bullet, but it is a promising new tool in the toolbox. The best applications that we see are things like searching across many bags of tricks. We know that fusion works. We know that tiling works. And we can run lots of experiments really quickly this way by launching them with agents and see what actually performs the best on the workload. It's also good at porting existing implementations to new hardware, where it takes the insights from that original implementation and specializes them to the hardware available features on the new target. And also about translating existing optimizations to new scenarios. You can quickly adopt new optimizations, like let's say you're changing the quantization of your model. You can still look at differently quantized implementations to guide that optimization. In terms of the worst applications, we're still not at the point where they're writing the N+1 for flash attention, coming up with like those genius algorithmic advances. And they're not currently outperforming a human expert who banged their head on this problem for months, and we shouldn't expect them to be. I think that the most exciting part of this work is allowing those people to focus on the most interesting optimizations and getting us better than baseline on all the problems that they don't have time for. So what's next in the work? We want to build abstract models of different machines to help the agents further specialize code to individual hardware. We're also interested in generating basically what is like NVIDIA assembly, such as PTX. You can see an example here, because the thought is that we can basically do that better with AI than humans because it's so cumbersome. And then also looking at academic formal verification methods for correctness. Also want to give a huge shout out to my colleagues. They are the silent, unspoken heroes here. And you know, I love talking about this with people, so please feel free to give me an email if you want to talk about kernel generation or anything that I covered. And we are hiring, so if this problem interests you, we'd love to chat. Thanks.
Our next presenter argues that simple choices, like direction over speed, will help us to avoid the infinite software crisis of maintaining a tangled mess. Please join me in welcoming to the stage staff software engineer at Netflix, Jake Nations.
Hey everyone, good afternoon. I'm going to start my talk with a bit of a confession. I shipped code I didn't quite understand. I generated it, tested it, deployed it, couldn't explain how it worked. And here's the thing though, I'm willing to bet every one of you have too. So now that we can all admit that we all ship code that we don't understand anymore, I want to take a bit of a journey, see how this kind of has come to be. First, look back in history, we see that history tends to repeat itself. Second, we've fallen into a bit of a trap. We've confused easy with simple. Lastly, there is a fix, but it requires us not to outsource our thinking. So I've spent the last few years at Netflix helping drive adoption of AI tools, and I have to say the acceleration is absolutely real. Backlog items that used to take days now take hours, and large refactors that have been on the books for years are finally being done. Here's the thing though, large production systems always fail in unexpected ways. Like look what happened with Cloudflare recently. When they do, you better understand the code you're debugging. And the problem is now we're generating code at such speed and such volume, our understanding is having a hard time keeping up. Hell, I know, I've done it myself. I've generated a bunch of code, looked at it, thought, I have no idea what this does. But you know, the test passed, it worked, so I shipped it. The thing here is this isn't really new. Every generation of software engineers has eventually hit a wall where software complexity has exceeded their ability to manage it. We're not the first to face a software crisis. We're the first to face it at this infinite scale of generation. So let's take a step back to see where this all started. In the late 60s, early 70s, a bunch of smart computer scientists at the time came together and said, hey, we're in a software crisis. We have this huge demand for software, and yet we're not really able to keep up, and projects are taking too long, and it's just really slow. We're not doing a good job. So Dijkstra came up with a really great quote, and he said, when we had a few weak computers, I mean, to paraphrase a longer quote, when we had a few weak computers, programming was a mild problem. And now we have gigantic computers, programming has become a gigantic problem. He was explaining as hardware power grew by a factor of 1,000, society's wants of software grew in proportion. And so it left us, the programmers, to figure out between the ways and the means, how do we support this much more software? So this kind of keeps happening in a cycle. In the 70s, we get the C programming language, so we could write bigger systems. In the 80s, we have personal computers now. Everyone can write software. In the 90s, we get object-oriented programming. Inheritance hierarchies from hell were, thanks Java for that. In the 2000s, we get Agile, and we have sprints and Scrum Masters telling us what to do. There's no more waterfall. In the 2010s, we get cloud, mobile, DevOps, everything. Software truly ate the world. And today, now we have AI, Copilot, Cursor, Claude, Codex, Gemini, you name it. We could generate code as fast as we can describe it. The pattern continues, but the scale has really changed. It's infinite now. So Fred Brooks, you might know him from writing the Mythical Man Month. He also wrote a paper in 1986 called No Silver Bullet. And in this, he argued that there would be no single innovation that would give us an order of magnitude improvement in software productivity. Why? Because he said the hard part wasn't ever the mechanics of coding, the syntax, the typing, the boilerplate. It was about understanding the actual problem and designing the solution, and no tool can eliminate that fundamental difficulty. Every tool and technique we've created up to this point makes the mechanics easier. The core challenge, though, understanding what to build, how it should work, remains just as hard. So if the problem isn't in the mechanics, why do we keep optimizing for it? How do experienced engineers end up with code they don't understand now? The answer, I think, comes down to two words we tend to confuse: simple and easy. We tend to use them interchangeably, but they really mean completely different things. I was outed at the speaker dinner as being a Clojure guy, so this is kind of clear here. But Rich Hickey, the creator of the Clojure programming language, explained this in his talk from 2011 called Simple Made Easy. He defined simple meaning one fold, one braid, and no entanglement. Each piece does one thing and doesn't intertwine with others. He defines easy as meaning adjacent, what's within reach. What can you access without effort? Copy, paste, ship. Simple is about structure. Easy is about proximity. The thing is, we can't make something simple by wishing it so. Simplicity requires thought, design, and untangling. But we can always make something easier. You just put it closer. Install a package. Generate it with AI. Copy a solution off of Stack Overflow. It's human nature to take the easy path. We're wired for it. As I said, copy something from Stack Overflow. It's right there. Framework that handles everything for you with magic, install and go. But easy doesn't mean simple. Easy means you can add to your system quickly. Simple means you can understand the work that you've done. Every time we choose easy, we're choosing speed now, complexity later. And honestly, that trade-off really used to work. The complexity accumulated in our code base is slowly enough that we can refactor, rethink, and rebuild when needed. I think AI has destroyed that balance because it's the ultimate easy button. It makes the easy path so frictionless that we don't even consider the simple one anymore. Why think about architecture when code appears instantly? So let me show you how this happens, how a simple task evolves into a mess of complexity through a conversational interface that we've all come to love. This is a contrived example, but say we have our app, we want to add some authentication to it. Say add auth, so we get a nice clean auth.js file. Iterate on it a few times, it gives a message 5. You're like, okay, cool, we're going to add OAuth now too, because now we've got an auth.js and OAuth.js. We keep iterating, and then we find ourselves that sessions are broken, and we got a bunch of conflicts. And by the time you get to turn 20, you're not really having a discussion anymore. You're managing context that's become so complex that even you don't remember all the constraints that you've added to it. Dead code from abandoned approaches. Tests that got fixed by just making them work. Fragments of 3 different solutions because you kept saying, wait, actually. Each new instruction is overriding architectural patterns. When you said make the auth work here, it did. When you said fix this error, it did. There's no resistance to bad architectural decisions. The code just morphs to satisfy your latest request. Each interaction is choosing easy over simple, and easy always means more complexity. We know better, but when the easy path is just this easy, we take it, and complexity is going to compound until it's too late. AI really takes easy to its logical extreme. Decide what you want, get code instantly. But here's the danger in that. The generated code treats every pattern in your code base the same. When an agent analyzes your code base, every line becomes a pattern to preserve. The authentication check on line 47, that's a pattern. That weird gRPC code that's acting like GraphQL that I may have added in 2019, that's also a pattern. Technical debt doesn't register as debt, it's just more code. The real problem here is complexity. I know I've been saying that word a bunch in this talk without really defining it, but the best way to think about it is it's the opposite of simplicity. It just means intertwined. And when things are complex, everything touches everything else. You can't change one thing without affecting 10 others. So back to Fred Brooks's No Silver Bullet paper. In it, he identified that there's two main types of complexity in every system. There's the essential complexity, which is really the fundamental difficulty of the actual problem you're trying to solve. Users need to pay for things, orders must be fulfilled. This is the complexity of why your software system exists in the first place. And then second, there's this idea of accidental complexity. Everything else we've added along the way, workarounds, defensive code, frameworks, abstractions that made sense a while ago. It's all the stuff that we put together to make the code itself work. In a real code base, these two types of complexity are everywhere, and they get so tangled together that separating them requires context, history, and experience. The generated output makes no such distinction, and so every pattern keeps just getting preserved. So here's a real example from some work we're doing at Netflix. I have a system that has an abstraction layer sitting between our old authorization code we wrote, say 5 or so years ago, and a new centralized auth system. We didn't have time to rebuild our whole app, so we just kind of put a shim in between. So now we have AI. It's a great opportunity to refactor our code to use the new system directly. Seems like a simple request, right? And no, it's like the old code was just so tightly coupled to its authorization patterns. Like we had permission checks woven through business logic, role assumptions baked into data models, and auth calls scattered across hundreds of files. The agent would start refactoring, get a few files in, and hit a dependency couldn't untangle, and just spiral out of control or give up. Or worse, it would try and preserve some existing logic that from the old system and recreating it using the new system, which I think is not great too. The thing is, it couldn't see the seams. It couldn't identify where the business logic ended and the auth logic began. Everything was so tangled together that even with perfect information, the AI couldn't find a clean path through. When your accidental complexity gets this tangled, AI is not the best help to actually make it any better. I found it only adds more layers on top. We can tell the difference, or at least we can when we slow down enough to think. We know which patterns are essential and which are just how someone solved it a few years ago. We carry the context that the AI can't infer, but only if we take time to make these distinctions before we start. So how do you actually do it? How do you separate the accidental and essential complexity when you're staring at a huge code base? Code base I work on Netflix has around 1 million lines of Java, and the main service in it is about 5 million tokens last time I checked. No context window I have access to can hold it. So when I wanted to work with it, I first thought, hey, maybe I can just copy large swaths of this code base into the context and see if the patterns were emerged, see if it would just be able to figure out what's happening. And just like the authorization refactor from previously, the output just got lost in its own complexity. So with this, I was forced to do something different. I had to select what to include, design docs, architecture, diagrams, key interfaces, you name it, and take time writing out the requirements of how components should interact and what patterns to follow. See, I was writing a spec. 5 million tokens became 2,000 words of specification. And then to take it even further, take that spec and create an exact set of steps of code to execute. No vague instructions, just a precise sequence of operations. I found this produced much cleaner and more focused code that I could understand, as I defined it first and planned its own execution. This became the approach which I called context compression a while ago, but you call it context engineering or spec-driven development, whatever you want, the name doesn't matter. What only matters here is that thinking and planning become a majority of the work. So let me walk you through how this works in practice. So you have step 1, phase 1 research, where I go and feed everything to it up front. Architecture diagrams, documentation, Slack threads, I mean, been over this a bunch, but really just bring as much context as you can that's gonna be relevant to the changes you're making. And then use the agent to analyze the code base and map out the components and dependencies. This shouldn't be a one-shot process. I like to probe, say, like, what about the caching? How does this handle failures? And when its analysis is wrong, I'll correct it. And if it's missing context, I provide it. Each iteration refines its analysis. The output here is a single research document. Here's what exists, here's what connects to what, and here's what your change will affect. Hours of exploration are compressed into minutes of reading. I know Dex mentioned it this morning, but the human checkpoint here is critical. This is where you validate the analysis against reality, the highest leverage moment in the entire process. Catch errors here, prevent disasters later. On to phase 2. Now that you have some valid research in hand, we create a detailed implementation plan. Real code structure, function signatures, type definitions, data flow. You want this to be so any developer can follow it. I kind of liken it to paint by numbers. You should be able to hand it to your most junior engineer and say, go do this. And if they copy it line by line, it should just work. This step is where we make a lot of the important architectural decisions. Make sure complex logic is correct. Make sure business requirements are following good practice. Make sure there's good service boundaries, clean separation, and preventing any unnecessary coupling. We spot the problems before they happen because we've lived through them. AI doesn't have that option. It treats every pattern as a requirement. The real magic in this step is the review speed. We can validate this plan in minutes and know exactly what's going to be built. And in order to keep up with the speed at which we want to generate code, we need to be able to comprehend what we're doing just as fast. Lastly, we have implementation. And now that we have a clear plan and backed by clear research, this phase should be pretty simple. And that's the point. When AI has a clear specification to follow, the context remains clean and focused. We've prevented the complexity spiral of long conversations. And instead of 50 messages of evolutionary code, we have 3 focused outputs, each validated before proceeding. No abandoned approaches, no conflicting patterns, no wait actually moments that leave dead code everywhere. To me, what I see as a real payoff of this is that you can use a background agent to do a lot of this work. Because you've done all the thinking and hard work ahead of time, it can just start the implementation, you can go work on something else and come back to review. And you can review this quickly because you're just verifying that it's conforming to your plan, not trying to understand if anything got invented. The thing here is we're not using AI to think for us. We're using it to accelerate the mechanical parts while maintaining our ability to understand it. Research is faster, planning is more thorough, and the implementation is cleaner. The thinking, the synthesis, and the judgment, though, that remains with us. So, remember that authorization refactor said that AI couldn't handle? The thing is now we're actually working on it now and starting to make some good progress on it. The thing is, it's not because we found better prompts. We found we couldn't even jump into doing any sort of research planning and implementation. We actually had to go make this change ourselves by hand. No AI, just reading the code, understanding dependencies, and making changes to see what broke. That manual migration was, I'll be honest, was a pain, but it was crucial. It revealed all the hidden constraints, which invariants had to hold true, and which services would break if the auth changed. Things no amount of code analysis would have surfaced for us. And then we fed that pull request of the actual manual migration into our research process and had it use that as the seed for any sort of research going forward. The AI could then see what a clean migration looks like. The thing is, each of these entities are slightly different, so we have to go and interrogate it and say, hey, what do we do about this? Some things are encrypted, some things are not. We had to provide that extra context each time through a bunch of iteration. Then, and only then, we could generate a plan that might work in one shot. And the key word, and might's the key word here, is we're still validating, still adjusting, and still discovering edge cases. The 3-phase approach is not magic. It only works because we did this one migration by hand. We had to earn the understanding before we can code into our process. I still think there's no silver bullet. I don't think there's better prompts, better models, or even writing better specs. Just the work of understanding your system deeply enough that you can make changes to it safely. So why go through with all this? Why not just iterate with AI until it works? Eventually, won't models get strong enough and it just works? The thing to me is, it works isn't enough. There's a difference between code that passes test and code that survives in production, between systems that function today and systems that can be changed by someone else in the future. The real problem here is a knowledge gap. When AI can generate thousands of lines of code in seconds, understanding it could take you hours, maybe days if it's complex. Who knows, maybe never if it's really that tangled. And here's something that I don't think many people are even talking about at this point. Every time we skip thinking to keep up with generation speed, we're not just adding code that we don't understand. We're losing our ability to recognize problems. That instinct that says, hey, this is getting complex, it atrophies when you don't understand your own system. Pattern recognition comes from experience. When I spot a dangerous architecture, it's because I'm the one up at 3 in the morning dealing with it. When I push for simpler solutions, it's because I've had to maintain the alternative from someone else. AI generates what you ask it for. It doesn't encode lessons from past failures. The 3-phase approach bridges this gap. It compresses understanding into artifacts we can review at the speed of generation. Without it, we're just accumulating complexity faster than we can comprehend it. AI changes everything about how we write code. But honestly, I don't think it changes anything about why software itself fails. Every generation has faced their own software crisis. Dijkstra's generation faced it by creating the discipline of software engineering. And now we face ours with infinite code generation. I don't think the solution is another tool or methodology. It's remembering what we've always known, that software is a human endeavor. The hard part was never typing the code, it was knowing what to type in the first place. The developers who thrive won't just be the ones who generate the most code, they'll be the ones who understand what they're building, who can still see the seams, who can recognize that they're solving the wrong problem. That's still us. That will only be us. I want to leave on a question, and I don't think the question is whether or not we will use AI. That's a foregone conclusion. The ship has already sailed. To me, the question is going to be whether we will still understand our own systems when AI is writing most of our code. Thank you.
Ladies and gentlemen, please welcome back to the stage, Jed Borovik.
Welcome, welcome. Let's give it up for Jake. All right, we are 6 hours in and we're about to take our break. But before we leave, I want to tell you what's next. We have something very special. We're going to have the CEO of Poolside, former CTO of GitHub, coming to do the first public demo of Poolside. So I wouldn't miss it. Less than a month ago, it was reported that NVIDIA was going to put up to $1 billion in Poolside. So I'm excited to see what they're going to show us. With that, let's break. There's going to be a, down in the expo booth, we have Ryan from AMP, SourceGraph demoing AMP and talking about how to build with agents. So also check that out during the break. We'll see you back at 4. Thanks, everybody. is going to be our last session, and as we heard, it's going to be a good one. We're going to start with Poolside, and we're going to hear from Reyes, Cline, METR, and Deepmind. So to get us started, help me welcome our first speaker to the stage, co-CEO at Poolside, former CTO of GitHub and Heroku, Jason Warner.
Thanks, Ed. Hey, everybody. So I know you were expecting ISO, my co-founder here. So I'm 5 inches shorter, 30 pounds heavier, and not as good looking, but I think you'll see him here really quickly too. So how many people here know what Poolside is and does? Anyone? Anyone? Yeah. So let's talk about that real quickly. Poolside exists to close the gap between models and human intelligence. That's literally it. That's what we're here to go do. We're building our own models from scratch to do this. We're based on the idea 2.5 years ago that we thought next token prediction was an amazing technological breakthrough, but it needed to be paired with reinforcement learning really to make that leap. So that's what we've been doing for the past 2.5 years. So we're on our 2nd generation of models now, Malibu Agent, and instead of kind of like walking you through some slides and all that, we just thought maybe, I don't know, let's kind of show you what we're doing here. So ISO, are you there?
I got you, Jason.
So as I said, you were supposed to see him today, but there's, I don't know, our airline system kind of works sometimes, maybe. So he's stuck in California. But we thought we'd just walk you kind of through some demos here today. So what you're looking at here is a very modern programming language that the government uses to run all the world's critical infrastructure called Ada. Anyone familiar with Ada? Yes, yes. Okay, so everyone I saw put their hands up for Ada either has no hair or gray hair like me. So that should tell you what's going on here. So ISO, why don't we figure out what's going on with this code base here?
Well, let's start asking what the code base is about.
That's great. And what you're seeing here is obviously our assistant in Visual Studio Code backed by Poolside Agent, a model we trained from scratch using our proprietary techniques. And you can see what's going on here, kind of the stuff you expect from an agent. And obviously the form factors of all of these things are going to change a couple of times over the next couple of years. But people seem to like VS Code. So we're going to show you this demo here today. So you can see from this, it kind of went through, told you what this code base is all about. But, these things run in our satellites, and I don't know anything about Ada, but I do know a lot about a couple of other programming languages. So, ISO, what do we want to do here? Why don't we see what this thing might look like in Rust?
Let's do it. Let's ask it to convert this database to Rust.
So obviously you're going to see what's going on here. Again, if you guys have used other tools, you're not going to expect too much of the difference for what's happening here, except that, again, we're backed by our own model. We're not using OpenAI. We're not using Anthropic. This is Poolside. And Poolside is a bottom-to-top stack that is right now, if no one's touched it, and I know no one in this room has touched this unless you work for a 3-letter agency, a defense contractor, or you've sent missiles somewhere that we're not going to talk about in this session. Because that's where we're working. We're working in high-consequence code environments for the last year inside the government and the defense sector, as you can see from this demo. So what you see here is kind of going through, doing the conversions. What you see in the middle pane is something that we built to kind of show you as the streams come through all the different changes that are happening. One of the tricky parts about working on inside the defense sector and things like that is you can't have an agent that's just going to run around and do stuff. I mean, like, I can't walk into half of these buildings. You can't give an agent access to these data sources and just say, hey, go nuts. You need to have the right permissions. You got to actually really ratchet these things down to do things inside those environments that they feel comfortable with. So where are we on this now? Is it trying to fix itself yet?
Yes, so it wrote about 1,152 lines of code, and it just popped up a command starting to test it. Excuse me. So we see here all of the files on the left-hand side that it created. This is essentially our live diff view that's available. And as we see, it's currently starting to actually test it out.
So this is the part where we just sit here and watch this for 3 minutes and I say nothing. No, what you see.
The good thing is that this is a very fast inference.
Yes.
So 1,100 lines of code.
Did it?
10 tasks completed.
Do we know if this works yet?
Well, let's have a look. So it actually wrote some shell commands to test it. And when we check out the output of those, this actually looks pretty good.
Can we verify that?
To run it. Let's go verify it. So of course our agent came back and gave a summary of what it did. But let's just ask how to run this. Okay. So I'm going to go open up. So it says this is how I can run the Ada version, and this is how I can run the Rust version. Let's run the Rust version. Perfect. Let's have a look in. Ooh, we might be hitting an actual bug.
An actual demo bug?
Let's have a look.
Let's see what happens.
No, just warnings.
Just warnings. Do we have an unwrap in there that we need to take care of? I heard that those things are dangerous.
So right now there's a REPL. Let's hit help, see what we're able to do. So it looks like we have a set of commands. I'm going to be lazy. I'm going to copy paste these queries. So create table users. Okay, so far so good. Let's insert a record. Okay, well, let's find out if it actually did its job. Select start from users. Okay, nice. We've got a record here.
That's nice.
Now, I want to actually, you see, if I use the up arrow, it doesn't actually allow me to cycle through commands. Let's ask it to add a feature. Allows me to use the up arrow to cycle through. I think it will understand my intent here.
The one thing we know about ISO is he actually does know how to read and write, but he can't type. So all those errors that you're seeing in there, yeah.
So it looks like the agent's identified a package that we can use. Let's just quickly look here, compare this to version 1. And it looks like it's adding a library called Rusty-Line and changing the files accordingly. It's currently built it. And it looks like the build output is successful. There's some warnings. We'll ask it to clean those up later on. And it's now starting to test it. Okay, apparently it works. It wrote itself a little bash script to test the history. It's wrote itself a little final demo script. So let's let it. Okay, and it gave us the summary. Well, now, how do I rerun this? I do kind of know that. So let's just.
Should know that. That was 30 seconds ago.
Let's build it and let's run it again. Okay, let's do a help. And oh yeah, that's the up arrow. It works.
Very nice.
Perfect. Now, our models aren't just capable coding agents. They're capable in lots of areas of knowledge work. They're also emotionally intelligent. They're fun. They're great to write bedtime stories with for the kids. So I'm going to ask it to write me a poem about all these changes. But that's just more for fun.
So as Isa was saying, this is just an interface into our platform. There's other interfaces into it if you're inside one of those organizations that has adopted poolside. So this is the coding interface into it. But we also have other ways in which you can interact with it, web as well as an agent that you can download on your machine. But yeah, we don't really tout the poem writing or the songwriting, though I did send this to my wife to see, and I have been sending her love letters written by poolside. So I kind of hope that she did not enter this session to know exactly how I've been doing that for the past 6 months. But yeah, so this is kind of poolside. This is what we've been up to. So as I said, Malibu Agent is our second generation. We've got a ton more compute coming online, and that's when we're training our next generation. That is going to be the one that comes out publicly to everybody very early next year. We're going to have it behind our own API. It'll be on Amazon behind the Bedrock API. Anybody in the world who's building out any sort of, on one side, the engineering assistants like the Cursors, Windsurfs, Cognitions, Replets of the world, you can use ours, or if you use building out on any other side of the fence, the Harveys, the writers, the whatever applications of the world, there's going to be a fifth model out there that's going to be at that level that you can consume. But we're dead set on doing this and bringing this out to everybody in the world and kind of advancing that state of the art. And we're just going to keep pushing that out. So that's kind of who we are. And you can find out very little more at our website since we don't put much out there. But ISO, anything else you want to say before you try to go make your flight this time, please?
So I would say that it's been a pretty incredible journey for the last 2.5 years of starting entirely from scratch and now building to a place where we see our models have grown up to become increasingly more intelligent. And the kind of missing ingredient that we had was compute. And now that's unlocked for us, and with a large number of over 40,000 GB300s coming online, we see how we can start scaling up some of those models to get even further in their level of capabilities in software development and other types of long horizon knowledge work. What I think is exciting about this conference and this audience is of all the work that's happening of evolving the form factor. Right now, what we looked at was this asynchronous way of operating with agents. But Jason, you and I, we have agents running that are doing tasks for hours, and I think in the near future we can see a world where they're able to start doing tasks in days in the coming years. And so I think the interface will continue to change. We're really focused on the fundamentals, building intelligence and being able to scale up and serve it. And it's why we go full vertical. It's why we go from our multi-gigawatt campus in West Texas, where we're building out data centers, to our team building out models. And the interface that you saw today is just our version of an expression. But I think this audience is going to do an incredible job of building lots of better versions of how to express using that intelligence into actually valuable, economically valuable work.
Couldn't have said it better. Can't wait to see what you guys build on this in the future when it's publicly available. And if anyone really does want to build a data center campus, we are hiring for that. It is weird to be putting shovels in ground again, like we did in the 90s and early 2000s, but that's what you got to do to scale intelligence these days. So
I would make one other non-scheduled statement.
Oh, no.
I hope you're going to be okay with this one, Jason. As our models are getting more capable, we love to also see who wants to build with them. Right now, the vast majority of companies that are doing additional reinforcement learning and fine-tuning on top of models are doing it on what I would consider right now the best-in-class open source models, the Qwens and Thimis and Minimaxes of the world. And we'd like to start figuring out how we can partner with you with our models, anywhere from any checkpoint early on to where we are today, for you to be building closer together with us on top of things. We haven't really figured out the approach to it yet, but I think since we have this audience, it's not a bad place to put it out there, and so definitely reach out to us. We think the world till date was built by intelligence. The world in the future is being built on top of intelligence, and so it'd be a great way to partner.
Well, thanks, ISO. Thanks, everybody here. And now we do have 5 minutes left. I don't know if we're supposed to take questions, but I'm happy to. So if anyone does, but if not, I'm just going to go that way. What was that? Sort of. I mean, I think of him that way. Here's a fun story. Here's how I met ISO. I like to tell this story because ISO's a fun dude. I met ISO because it started with a failed acquisition at GitHub. So back when I joined GitHub in 2017 as a CTO, I wanted to take GitHub from a kind of collaborative code host with open source bent and turn it into an end-to-end software development platform infused by intelligence. And so the products that we launched from 17 on, GitHub Actions, packages, alerts, notifications, eventually Codespaces, and then Copilot was the last thing that the office of the CTO did before I left, with Nat Friedman, Uga Damore, and a couple of other folks inside there. But ISO, in 2017, when I joined, he had working code completion before the transform architecture had landed fully. He had on LSTMs. And so I quickly tried to acquire his company, and he just said no. He just said no to me. But that was a long, drawn-out process talking about what we thought neural networks were going to mean for the world. And so during that process, which was a lengthy one, we became really good friends, and we'd stayed in close contact over the years. And then 22 rolled around, obviously ChatGPT comes out, Anthropic's out, and we kind of saw the end game at play. And we said, do we jump back in or not? And of course, yes, we jumped back in. But I like to tell that story about how he just kept saying no to me, and I just kept asking him questions, and eventually he said, yes, we should found a company. Because, by the way, when I asked him if we should do this, he said, oh, goddamn no. That was were his exact words. He's like, no, we should just learn how to paint and sail. But here we are. So.
Yeah. It's been a grand old journey together, Jason. I think the reason we ended up doing this is because of our our opinionated view on what it was going to take to build more capable intelligence. And the first 18 months of this company, obsessing and focusing on reinforcement learning combined with LLMs felt like one of the most contrarian opinions in the world. But I think today it's absolutely not. And it's super exciting to see the progress that's continuing to make. Like, in the coming years, we're going to see the world that started in completions and went to chat and is now at agentic increasingly approach more autonomous. And all of it is stemming effectively from a combination of bringing highly capable models that are constantly evolving together with real world problems. And I think what we're starting to see now is we're entering these kind of awkward teenage years ahead of AGI, where everybody in this room who's building out incredible companies and applications is bridging this gap of what it really takes to make intelligence that in its raw form actually be valuable. And we want to be a small, humble part of that. We've got a lot of work still ahead of us. The team is growing. But hopefully what you've seen today is what our customers and enterprises have been having access to and seeing for a while, is that we're hard at work at really pushing those capabilities. We also want to make sure we make them available to build together with others.
Well, that's it. Thanks, everybody.
RL has boosted base models, but it's opaque and hard to scale across enterprises. But what if we could apply RL techniques to prompts instead of model weights? Here to show us how is the co-founder and CPO of Reyes, Aparna Dinakoran.
Hi, everyone. Thanks so much for coming. Well, today I'm excited. We're going to talk a little bit about prompt learning and how to use that with evals. Any of you guys are spending a lot of time thinking about the frontier coding models. I think there's so much attention on them, but just what's not so obvious is how much time is actually spent on the system prompts for those building these coding agents. So here's actually a look. This is a tweet that went viral about the whole system prompt of Claude that's been leaked. I'm sure they've changed it since then. But you can actually see that Claude, there's Cursor, there's Cline, and just the length of the actual system prompt for each one of these. And I think what's not as obvious is these actually aren't just static. They're repeatedly iterated on. And it's such an important piece of context that actually goes into making these coding agents the most successful agents out there. It's not just us talking about it. Karpathy talks about it a lot. And this was the viral tweet that he posted, which was, there's this paradigm around iterating on these prompts that he's kind of coined it system prompt learning. And what he said is that it almost feels like humans learning, because they take back English feedback and use that to actually iterate on what they should do differently the next time. And I think he wrote something like, it's almost like that movie Memento, where the guy forgets what he learns, and then he starts writing it down and then uses that to actually kind of go through his next day. And so this is a little bit of the concept behind system prompt learning. And what we wanted to do was show you guys a little bit of how that works and then put that to test on two of the most popular coding agents, Claude and Cline, today. So first off, how does prompt learning actually work? So for those of you who are familiar with RL, what I thought we'd do is just do a little analogy, compare how does RL work versus system prompt learning. For RL, if we just took an analogy of a student who's trying to improve their exam scores, they take an exam, somebody grades the exam, you have a scalar reward, which is like, they got a 70%, an 80%, 90%, and then they have to figure out almost blindly, just with that score, how to actually improve their score on the next exam. And I think this is actually one of the flaws of, RL works, don't get me wrong, amazing in so many concepts and domains, but it can be, a long path to actually figure out what the right solution is. And I think some of the things that we've noticed is that it can be sample inefficient. It takes a lot of data to get what you want. It's time intensive, it's data hungry. You need to have a whole data science team to do this. And it just might be overkill for teams who are trying to build agents because LLMs are already so good. So if you're a team who's actually trying to build an agent, maybe prompt learning is actually might be slightly more of an interesting paradigm for you. So in this scenario, same analogy, you have a student who's taking an exam, there's some exam score, except in this case, what actually gets outputted isn't just the score, they got a 70, they got an 80, but you also get back some kind of English feedback. Why did they get this answer right? What did they mess up on? Here's concepts that they missed on. What do they need to go study? And then they use this information to actually go and prepare on what to do next to get a better score. This is basically the concept that we applied to coding agents. And we ran this kind of test on both Claude as well as Cline. Both of these, as you know, start off with some kind of system prompt, which in Claude Code, this is kind of a snippet of it. And then they both kind of come with something that you can append rules to. So Cline has rules, CloudMD has the CloudMD file, and it starts off empty. You can go in and add whatever is important for your repo. So what we did was actually took, just benchmark both Cline and Claude Code on Swybench. I'm going to kind of run through this entire example with Swybench, but this entire thing we also ran on BBH and a ton of other software engineering data sets. But you can see here, just on vanilla Cline, vanilla Claude Code, nothing added to the CloudMD or the Cline rules. They had, about, I think with Cline, somewhere on, Claude Sonnet 4.5, it was about 30% of the GitHub issues actually resolved. Claude Code, it was about 40% of the GitHub issues resolved. So we took this as kind of our starting benchmark. And the thesis is could we actually use prompt learning to see if we can improve the system prompt and see if it was able to, with the new system prompt, actually give us a better score on these benchmarks. We didn't do anything on fine-tuning. We didn't change the models, anything like that. It was just focused on the system prompt. This is the process that we went through. We took the coding agent. We had it actually write some code. We ran unit tests, and then we then passed that through to some kind of model that was doing the LLM as a judge evals. And I'll show you guys what that looks like. But the LLM as a judge eval actually gave back, why did it fail? Did it fail because of this? Can you give some examples of what were common scenarios that it didn't do good on? And then it actually used those kind of evals to then go back and add it to a meta prompt to come back with kind of the system prompt rules that we're going to append to. So let's talk through kind of the process. So first we had kind of the Swybench data set. Swybench in this scenario is just 150 examples. We did this for both Cline and Claude Code, where we took the original prompt, which had no rules. We gave it kind of the software engineering problem, and then it generated some kind of patch to actually solve that. And then we ran the generated solution through the unit test. Then, whatever the unit test came back with, whether it was right or wrong, we then passed this into an LLM as a judge eval. And this is kind of the most important part because this actually generated the explanation for us. So we passed in the problem statement, we passed in what the coding agent solution was, the unit tests, and then the actual solution that it came up with. Pass that in, and this that you're looking at in the center here is actually the LLM as a judge eval. And these evals, we're going to talk a bit about this, but eval engineering is a whole kind of concept that we spend a lot of time on, and writing really good evals is, I think, how you get the best kind of insight into what you could do to improve your agents. So in this scenario, what we did was we wrote a good LLM as a judge eval prompt. It outputted whether it failed or passed. And then this is the key part. We actually asked for an explanation. Why did it actually mess up? For specific libraries in the Swybench Lite test, it was parsing errors, or it was not handling, there's all sorts of actually different categories of errors, but we went through and we kind of looked at the explanation of what went wrong in each scenario. We then passed into a huge meta prompt. So this is actually what's helping us iterate on our system prompt. We passed in the original Claude or Cline system prompt. We passed in the original rules, which for us started off empty. And then we passed in, here was the input, here was the LLM as a judge eval, and then here was the actual explanation from that eval. Passed that all into the meta prompt, and then we did kind of a diff comparing, the old world. So just to remember, the old world had the original Claude system prompt, no rules kind of added or appended to it, and then the new world where it generated this entire rules of what to avoid or what to, what it had learned essentially from all those mistakes that it actually made. And then we ran this basically on the entire SweBench Lite again. And what we saw was that, on 150 examples, we were able to get Cloud Code up by 5%, more GitHub issues resolved, Cline, 15%, and this was literally on, I think the key thing is like 150 examples of just training data that was used on the most kind of powerful coding agents that are out there. And so just think about kind of the impact that could have for your agents. Many of you guys in this room might be thinking, okay, well, prompt learning is cool, but how does that compare to GEPA? If you're familiar with DSPy and you've kind of seen, I don't know if it's GEPA or JEPA, I've heard both, but you guys might be asking, well, how is this different? So GEPA, just in case you guys aren't familiar, it's a prompt optimizer from DSPy that is essentially very, very similar to what we're talking about, which is taking English feedback, using that English feedback inside of the actual prompt. And what we did was actually run a side-by-side benchmark against GEPA, where we compared kind of our prompt learning against GEPA. And I think what we saw was that GEPA required many, many loops and rollouts compared to kind of a fraction of that, which was our approach. And I think the key difference here, I mean, the underlying approach around using English feedback is the same, but I think the key thing that was really different here was we spent a lot of time actually developing and iterating on the evals. And the eval prompts really mattered to making sure that you gave really good explanations back to the agent. And so evals make all the difference. This was super critical for us to be able to get this to work. And if you guys are curious about learning more or reading more about kind of what we do, check out kind of our blog. We write a lot about evals, prompt optimization, and we're actively hiring. So come check us out. Awesome.
When it comes to AI agents, theory doesn't always compile to production. Here to share hard-won lessons building effective AI coding agents is the creator and head of AI at Cline, Nick Pash.
Wow, it's wild to be on the same stage as so many people I've drawn inspiration from. Let's dive into it. My name is Nick, I'm the head of AI at Cline, and today I'm going to share some lessons we learned along the way. So let's start with the bitter truth. For years, we compensated for weak models by building clever scaffolds around them. All kinds of clever ideas like RAG, indexing systems, search trees, tool calling scaffolds. All this was invented to cope with weaker models. And frontier models simply bulldoze those abstractions now. You don't really need your scaffolding anymore. Your scaffolding just gets in the way of these models. And the question really isn't how fancy is your agent stack. Increasingly, it's how strong is the model driving it. And the lesson here is relentless. A perfect example of what I'm talking about is Gemini 3.0 released this week, and it immediately dominated terminal bench leaderboards with no agentic harness supporting it at all. In this chart, you can see Gemini 3.0 on Terminus scored better than the vast majority of model agent combinations in the world, all out of the box. And what's remarkable is that Terminus is designed to be an unopinionated, generic, stripped-down harness, and it has no graph search, no RAG, no indexing, just here's a terminal, go figure it out, and it crushes. The whole point of Terminus is that it has no clever tool calling, no context engineering features. So the takeaway here is that capability beats scaffolding. If you get out of the model's way, it will perform just fine. So really what I'm driving at, and the key takeaway from this whole talk is if you're building agents, just relax. Cool it with all your clever engineering tricks. Stop overthinking it. That's it. That's the lesson. And another point on this, kind of like an aside, is I don't know about you guys, but we're all on Twitter. I'm on Twitter. And at this point, I just think talking about these like clever little context tricks and hacks is a little played out. Like at this point, I'm straight up tired of seeing some of this stuff. And like, I get it, it's free engagement, and we all indulge in it a little bit. But personally, I think there's not really much signal there. So if you want the full playbook for building an effective coding agent, like the playbook's right here, it's up on the screen. There's really some novelty talking about it like months ago, but at this point, in my opinion, it's been done to death. And we've been in this, we're model agnostic at Cline. We support all the models. Every 2 weeks, there's a new big model release going out, and we've basically come down to the same playbook of supporting each model as it comes out. So I'm sure everyone here knows how to tune an agent from Sonnet 4 to Sonnet 4.5, from Gemini 2.5 to Gemini 3, and GPT-5 to GPT 5.1. I feel like this entire conversation is a little played out. So I'm not really even going to cover this in depth because the tweaks here are trivial and the gains are marginal. So what I really want to talk about is something that's not actually given a lot of attention, and it's the real bottleneck. And the real bottleneck is that you can build the cleanest agent in the world, but that doesn't improve model capability by even 1%. Models only get better when labs train on something hard. And benchmarks, not agent cleverness, not all your clever engineering techniques, not your clever RAG pipelines, it's benchmarks that determine what frontier models learn to do next. And models didn't magically get better at tool use. They got better because people built RL environments that forced them to practice certain actions. Handling failure modes, retrying, and for example, like agents improve only when the model learns inside the right environment. Every jump in reasoning we've seen came from a benchmark. Every jump in agent reliability came from an RL environment. So the real questions become, what is a benchmark? How do you turn real-world agentic coding data into an RL environment? And what makes a good verifier? How do you detect real difficulty? And how do you train these models to work on the problems that we actually care about as engineers? These are the questions that matter for the next frontier. So what is a benchmark? A benchmark, put simply, it's an environment. So in our case, it's like a Docker container where you let the agent run wild. It's a starting state, which is the snapshot of the code when you started working on a real-world coding task, as well as a starting prompt. And the last thing is a verifier at the end that checks whether an end state is correct or acceptable. So how are RL environments different? Well, here's the thing. They're not really different at all. And you might notice this chart is basically the same thing as the previous slide. The only real difference, the only distinction here is how the reward is used. Benchmarks measure models. RL environments improve models. The score doesn't just stop in a leaderboard where you publish the results. The score is actually used to update the weights of the policy model. So how do you transform real-world coding data into useful RL environments for training? At Cline, we created the system called an RL Environments Factory. Looking for a better name there, but that's what we got so far. And the first phase in this pipeline is you get sub-agents and you have them qualify tasks. And these sub-agents, they work in parallel to decide whether or not given tasks are suitable to be turned into RL environments for the purpose of training. And the qualification process goes as follows. So you start with origins, so you have to validate, does the repository actually exist? Is the starting commit accessible? Is it open source? The journey, where you look at the starting prompt, the other follow-on prompts that the user might have followed up with the agent. You have to try to understand what was the user actually trying to accomplish? What was the spirit of their task? And lastly, it's the outcome. So can we find the actual commits or PRs that fix the problem in real life? Like, did they actually commit the solution to their problem later on in the timeline? And we're actively looking for easy disqualifiers as part of this. So things like vibe-coded slop. We don't need another benchmark that tests for, build the Next.js app from scratch. We're looking to disqualify trivial tasks that are too easy and tasks that have no reliable start or end states. And lastly, what makes a good RL environment good? How do we actually make an RL environment? And what makes a good test or verifier? So phase 2 of this pipeline is building the actual RL environment. So you start out with archaeology, where you actually reconstruct both states locally. You pull down the code. You see if you can implement it yourself, reconstruct it, build it, and verify that the bug that the user was referencing and the solution actually exist. You document every obstacle and dependency. You containerize it with Docker, removing Git, obviously, so agents can't reward hack. And lastly, you define the verifier at the end. And this is where it gets into like a little bit of the art of building a good verifier. And I want to talk about this because the analogy that I typically give is a tea kettle. So let's say the user's goal is, I want to boil water. A really good example of a verifier to test whether or not the water is boiling is a little whistle attachment that goes inside your tea kettle. And the whistle is a pure outcome verification. It's an example of a pure outcome-driven verifier where the water either reached the boiling point or it didn't. Either it's whistling or it's not. The kettle doesn't care how you achieved it, whether you used a gas stove, an electric induction stove, or a campfire, it just signals the result. And in the process of doing this, all of these weird bad tests can emerge. So you might have noticed like that the sub-agent might have noticed like, oh, in the ground truth solution, like in a previous run, the burner was set to high. So maybe we should be checking for that. But we all know that water can boil at a low setting on the burner. Or was it on the front left burner? Has 5 minutes elapsed? Like all kinds of weird bad tests. And the key point here is don't over-prescribe based on the ground truth. Test for the spirit of the task. Test for the outcome of the task. And the outcome at the end of all of this is a containerized benchmark or RL environment for that task. Agent work is recorded so you can see the traces, the trajectory that the agent took to complete the task, and you can reliably score it and verify it. And it's fully portable, you can run it on any device. So the path to automation that we've been undertaking as part of this is, can we fully automate the process of converting real-world coding data into RL environments for the purpose of training models? And this work largely started out manual, but in the first time the RL environment was like about 16 hours of my time. And what used to take 16 hours now takes less than 20 minutes per task. And we're building towards a fully automated RL environment factory where the bottleneck shifts from engineering to collecting high quality tasks. And an interesting kind of point here, the natural endpoint of all this is, what if we actually built RL environments, and this is like a question for everyone in the audience, is what if we built RL environments to test how well agents can actually make RL environments, kind of like a meta benchmark? What would hill climbing on that look like? And you can kind of start imagining that as models get really, really good at making their own RL environments to train on based on real world user data, you kind of complete that loop. Something to think about. So, okay, this next part is the truth nuke, also known as Truc. An unspoken fact is that we're not alone at Cline building this kind of system. Every major agent lab captures this data. They all do some version of this behind the scenes, but no one really talks about it. And I don't even need to name them. If you know, you know, and realistically, you all know. These same companies cite internal benchmarks to justify legacy systems that they spent months maintaining, but curiously, you'll never be able to study or inspect them because they don't publish them openly. And this data is so valuable, yet no one shares it. It's the only thing that actually moves the needle. And here's the heart of my argument, is by standing between real-world engineers working on real-world tasks and the models, agent labs have a unique role in history. We can build better prompts, we can build better tools, but none of that improves the underlying models. We possess the single richest data set of real engineering work anywhere in the world. Models don't improve without this data, and keeping them closed is slowing down frontier research. So today we're announcing Cline Bench. This is our attempt to finally create a benchmark that isn't cosplay engineering. It's not write me a server that generates Fibonacci sequences. This is real software development captured and packaged into standardized RL and eval environments. And this is the benchmark that we always wanted someone else to build. No one did, so we're doing it. And anyone can participate. So here's how it works. The whole thing is open source. There's no secret sauce, no locked away data sets. You can openly run it yourself and inspect it to see how it works. Anyone can use these environments for SFT, RL, evals, whatever. The point is to just give the entire ecosystem a real substrate to measure and improve models on, not just leak code puzzles. And this only works if the community contributes. And the good news is you don't actually need to do anything special. Just work on your open source project with the client provider turned on and opt into the Cline Bench initiative. If a frontier model gets stuck and you step in to fix it, that's actually an ideal task to be a candidate for a benchmark. And that's it. Just use the client provider, see where the model struggles, and we'll pick it up and introduce it into this open source benchmark. So Cline Bench will always remain free, fully open source, and freely accessible. Thank you all. If you want to contribute, thank you.
If benchmark scores for AI coding agents are so high, what explains the problems developers and teams face when working with them? Here to provide us with a few explanations is meta researcher Joel Becker.
Hey guys, thank you so much for having me. My name is Joel Becker. I work as a researcher or member of technical staff at METR, which stands for Model Evaluation and Threat Research. As we'll see in a second, I'm going to be talking about AI capabilities. How do we know how performant AIs are today, how performant they might be in the near future from these two different sources of evidence that seem to give somewhat conflicting answers. You know what, I could have done this whole talk without reference to METR papers in particular, but we'll look at two papers I've been involved with as examples of benchmark-style evidence and then more economic-style evidence. On the benchmark side, measuring AI ability to complete long tasks. This is the paper that comes with the charts that many of you would have seen on Twitter and so on, that METR is well known for. And then the second, this RCT, measuring how allowing AI affects developer productivity. And then we'll be talking about how to reconcile the gap that's implied between these two different kinds of measurements. As I mentioned, METR stands for Model Evaluation and Threat Research. We are an independent research nonprofit that seeks to inform the public, policymakers, labs, about the degree to which AIs might pose catastrophic risks to society. The model evaluation part means that we seek to understand AI capabilities and propensities, and the threat research part means we try to connect those capabilities and propensities to potential catastrophic risks. Okay, the first paper we're going to talk about, associated with this chart that many of you, I think, might have seen. Taking a step back first before we dive into the paper, how usually do we think about measuring AI capabilities using benchmarks on a Swyx bench or a GPQA, so on and so forth? There's some notion of 0% performance or random performance. So for GPQA, that's 25%, which corresponds to this floor, the worst you can possibly do. Perhaps there's a human baseline that's below 100% for GPQA. I think this is something like 75% that represents maybe expert human performance. And then, of course, you can go all the way up to 100% potentially on these kinds of benchmarks. But what does it mean? If I'm getting 50% on GPQA, if I'm like half the way from the floor to the expert baseline, what does that really mean about how performant the AIs are? If I meet the human baseline, does that mean that the AIs are now as performant or even more performant than expert humans in a relevant sense that I care about? It's hard to interpret. Another thing that you see from this graph is that benchmarks seem to have less and less time between coming online, sort of giving any signal at all, and being fully saturated. It's harder and harder to create benchmarks that have plenty of signal that might be informative to us about how capable models are for an extended period of time. So we're going to go about this a different way. First, we're going to gather human baseline data for diverse tasks spanning a range of difficulties. You should think of these humans as, experienced experts, but on their first day or first week on the job. These are not people with context on the tasks in particular. It's not exactly the kind of thing that's come up in their work before, but if it's a software engineering task, they're a relevantly skilled general software engineer. Same for the machine learning tasks and the cybersecurity tasks here that we'll talk about. The type of tasks come from these three buckets or task distributions. Hcast, which is a collection of software-based tasks seemingly requiring autonomy, interacting with tools, interacting with the environments, thinking through the problem, not just this kind of Q&A style data set. The SWA suite, which are these atomic problems. These are problems that maybe GPT-2 can do, maybe it can't. Problems like, here are 4 files. One of them is called passwords.txt. Which file contains the passwords? And then on the other end of difficulty, we have RE-bench, which are challenging, novel, open-ended machine learning research engineering challenges, which are very difficult even for top human experts. In addition to gathering the human baseline data, we'll also, under as close to identical conditions as possible, measure AI performance for the AIs that we're interested in on the same set of tasks. And then we're going to convert the time it takes for humans to complete these tasks into an estimate of AI autonomous capabilities, as I'll show you in a second. Here's an illustrative diagram, in this case for Claude 3.7 Sonnet, which was the frontier model at the time that this paper came out. You can see that for the very short tasks, something like 4 minutes or below, Sonnet is getting the answers correct, essentially 100% of the time, or maybe even here, literally 100% of the time. For the very hardest tasks, it's struggling, and then there's some range where we're kind of in the middle, we're somewhere between 10 and 90%. I'll say that this empirical pattern, where models are less performant at tasks that take humans longer, is, it's not a fact of nature, but it's something that we see pretty commonly, pretty robustly across models, at least on this task distribution, and I'd conjecture for other task distributions as well. So we try and fit this dark purple line to something like this data on how long it took humans to complete the relevant tasks that the models are attempting. And then we call the point on the x-axis, this horizontal axis, this human time to complete axis, at which we predict the models will succeed 50% of the time, the time horizon of those models. There's much debate in the 50% number. I can talk later about the reasons why we chose that. And then we'll do the same exercise for the other models. So here I have Claude 3 Opus has a time horizon of something like 4 minutes. That's where we're predicting that it has a success probability on this task distribution of 50%. For O1 Preview, I'm seeing something like 15 minutes, so on and so forth. And then, of course, all these models, they come out over calendar time. So if we plot the time horizon, the x-coordinate on this set of plots against calendar time, we find something like this. It looks, kind of like an exponential trend that's going up at some constant rate. In fact, it doesn't just look like an exponential trend. If we had a perfectly straight line here, it would indicate a perfectly exponential trend. We see something really remarkably steady, actually much more steady than we were anticipating when we went about doing this research project. And that's continued to be the case. So many of you will have seen updates that we've made of this graph on Twitter. This is going all the way up to GPT 5.1 Codex Max, so extremely recent. The predictions from this shockingly straight line have held up very well, I think. Taking a quick step back, what are benchmarks telling us, or here kind of benchmark-like evidence? Well, one thing is that AIs can succeed at what for humans would be exceedingly difficult tasks. The tasks in RE-bench are really far beyond my capabilities personally, and the AIs are having a good crack at them some decent percentage of the time. And the second, kind of obvious, is that progress is rapid. On the other hand, how much stock should we put in the evidence suggested by benchmarks? What limitations might they have? Lots, but here are 3 that I'll note. One is, as I mentioned, these are humans who are, expert in some relevant sense, but they're low context. It's something like their first week on the job. They haven't seen tasks exactly like this previously. They just have some relevant experience. Presumably people who were more sort of, not just having the relevant experience, but also highly familiar with with the set of tasks would perform the tasks even sooner, and then we think relative to those people, the AIs were more performant. The second is that benchmarks can be low ceiling. Even, GPQA, I'll use that example again, we're beginning to get to the point where that benchmark is totally saturated, not providing additional information for marginal models, whereas time horizon is providing this nice way to sort of chain benchmarks together in some sense over time. But nonetheless, it's still very hard to create these ever harder tasks when the time horizon of models is doubling every something like 6 to 7 months. So even time horizon might be saturated in not too long, or the benchmark's underlying time horizon. And the next one is, not a concern that's limited to the METR task, to the task behind time horizon. It's also true for Swybench. It's also true for many of your favorite agentic benchmarks. The problems aren't very messy in some sense. They don't require a ton of coordination with humans. They're often in relatively small, contained environments where not much can go wrong. Not these sort of massive open source code bases or other ways in which the problems can involve more interaction with the real world or be messy in some sense. So we did this project, and then early this year we were trying to think about how can we attack some of these limitations? What's a different source of evidence that might have its own pros and cons, but importantly be more externally valid in the scientific jargon? Perhaps field experiments are the answer, some more economic style evidence. So here we might be interested in very high context developers who are expert on the kind of tasks they're already doing. Speed up, or some notion of productivity boost, it seems to have more signal through even some superhuman, according to benchmarks, range. Perhaps GPQA is fully saturated, and you're getting a 1.5x, 2x speed up, something like that. But you can still achieve a 3x, 4x, 5x speed up. Even after that, we maintain more signal. And the last is that the tasks are messier. They are tasks that are coming up in people's real work. They're not synthetic. They're not small and contained. This is a real deployment scenario. Here's what we're going to do. For this paper, we're going to gather 16 experienced developers on large, mature open source projects that we'll go through in a second. Each of these developers will, on average, complete about 16 tasks from their real work. These are issues on the relevant GitHub repositories, the kind of thing that they might otherwise have completed, with the caveat that the very longest issues we're not going to include. The tasks will be randomly assigned to AI disallowed or AI allowed. AI disallowed, it means what you think it means. It means software development in 2019. It means no AI-powered tab autocomplete. It means no cursor agentic coding tools. It means no LLMs via the web UI. Or they can be randomly assigned to AI allowed, in which case everything's on the table. Any of the AI tools I just mentioned, or not using the AI tools. If you're in the AI allowed condition, you're not compelled to use AI. You just have the option. And we buy these developers Cursor Pro. So for the most part, that's the tool that they're using, with typically 3.6 or 3.7s on it at the time, which was the frontier model when we conducted this work. And then we're going to record the time it takes for the developers to complete each task and see the degree to which they might save time when AI is allowed versus when it's not. These are some of the repositories. Many of you will be familiar with them. We've got the Haskell compiler represented. We have scikit-learn. We have Hugging Face transformers. These are, on average, 1 million lines of code plus. They've been around for 10 plus years. The developers who are going to be working on these repositories as part of this study are, on average, the third top contributor out of hundreds or even in some cases thousands of contributors to these repositories. They personally have been contributing to the repository for something like 5 years on average. These are top experts. Some of you might have seen this graph too, and so the punchline's been spoiled. For the rest of you, we asked economics experts, machine learning experts, these are people at major AI companies and labs, top academics, some graduate students, so on and so forth, how much they expect developers to save time when they're using AI. They say something like 40% or a little bit less. We asked the developers themselves, the study participants, how much they expect to be sped up ahead of time, and they say something like 24, 25%. Then we asked the developers, after the study has been completed, how much they think they were sped up in the past by AI being allowed on the issues they completed as part of this study. And they say that it will have sped them up by something like 20%. And the punchline is that we find that developers are slowed down by 19%. They take 19% more time when AI is allowed relative to when AI is not allowed. You know, when I first saw the data coming in, saw sort of early versions of this plot, I thought presumably the same thing that many of you might be thinking right now, that we've messed something up, that you know, something's gone wrong, there's some issue in how we've set up the experiments. How could it possibly be the case? You know, at least these developers have access to the 0 points because they cannot use AI at any time. So we poured over many hours of screen recordings from these developers working on issues as part of the study. We looked to dive into a bunch of hypotheses that might explain what's going on and try to categorize the things that we think are going on versus not. Many of this is listed in the paper. I'll just quickly go through some of the things that we think are contributing. First, over-optimism about AI usefulness. That seems like an obvious one. You know, the developers, even after the study is completed, they think that that AI is going to be helpful to their work. It makes sense they might overuse AI on that basis. Two more, implicit repository context and high developer familiarity. You know, these developers are coming to these problems already knowing the solution to the problem. They're so expert in this work. You know, I imagine them as not trying to spend a bunch of time thinking through the solution that the AI can work through. Instead, they're just limited by how fast they can type, which means that using AIs, instructing AIs to do it, comes with some significant time cost versus how they might otherwise have spent their time. I think many of us have the sense that AIs might be less performant on large and complex repositories, which is a difference from this benchmark style evidence or from some previous work. And then low AI reliability. You know, maybe the AIs are very performant on these kinds of tasks, but they're only performant 50% of the time, or 80% of the time, 20% of the time. And so, at the very least, you need to check their work afterwards, and perhaps even you need to spend time correcting their work afterwards, which is something we see quite a lot on these issues. One thing from the factors with an unclear effect that I'll mention briefly, I'm happy to talk to people about later, is below average use of AI tools, which came up in the public discussion. This is in the unclear column because it's sort of evidence for and against. That's true for many of the things here. We don't have anything so conclusive to say. We're still working on this line of work. Here are some caveats, all important. First, obviously, we do not provide evidence for all software developers or tasks. These are extremely experienced developers working on extremely complex, long-lived, open-source repositories. I, in my own work, am not as expert in the relevant sense as these people are. I'm working on much smaller repositories. I feel more comfortable saying that even at this time, I was sped up by AI tools, even if the developers weren't. This setting is weird. It's weird for the same reasons that it's interesting, this unusual developer population. Second, the experiment is concentrated in March 2025. As I mentioned, we know that AI progress is rapid. Perhaps this result will have already changed by the time I'm giving you this talk. So this kind of puzzle suggested, right? The benchmark style evidence is giving a very impressive sense of what AI capabilities look like today, whereas the more economic style, I include labor market impacts working here too, in addition to our field experiment, looks somewhat more bearish or unimpressive. Why is the former not translating to the latter? At least naively, there seems to be a clash. How might we go about resolving this puzzle? So one possibility is that, in fact, we messed something up. This is still live and on the table. Maybe the developers really are not very capable at using AI, and if we continue to run this experiment, as in fact we are, they'll learn more familiarity with the tools and so get productivity benefits that they weren't getting at the time. I'm a little skeptical of that story, but that's one possibility. Another that economists like to bring up is that we're not incentivizing these developers to finish quickly. We're paying them per the hour, which we do for external validity reasons. Looking through their videos, I really do not think they're developing differently in accordance with these incentives, but that certainly is one possibility that's on the table. Another more statistical in nature possibility is, this is a small study. You shouldn't over-update so much. From small studies, we are doing bigger things that I'm excited to release at some point. Okay, but let's assume we haven't messed something up. And this is a result that we think does hold up. How could we resolve the puzzle? So one possibility, as I alluded to briefly, is that reliability needs to be very high to save time. That you need to be getting the answers to these problems that developers are putting in correct, something like 95, 99% of the time, in order for developers to tab through and not spend lots of time verifying the AI's work, which of course is pretty costly from a time perspective. Another possibility is Swybench-like or algorithmic costless scoring at the margin versus mergeability-like scoring. Swybench scores are not trying to account for whether the code is build onable by other people in future, or whether it's matching quality considerations that aren't considered by the unit tests. Perhaps AIs really are performant according to Swybench-like scoring, but not performance according to this kind of more holistic scoring that we might care about. Low versus high context baseliners, I mentioned previously, these are just much more skilled humans. Relative to those humans, perhaps the AIs are less capable. Task distribution, maybe these are just different kinds of tasks, in particular less messy than the benchmark style task. Maybe that's explaining what's going on here. Suboptimal capability elicitation, a huge amount of work has gone in at METR to making the agents as performant as possible, given the underlying models on all kinds of tasks. And that involves churning through a load of AI tokens. Perhaps that's less the case for Cursor in particular at the time when we completed the study. And then interdependence across tasks. Maybe it's the case that if humans can complete task A and task B, AIs can only complete task A, but not task B, and of course can do task A faster, then it still makes sense for humans to do task A and task B, not delegate task A, because they need to know the outputs, they need to know how task A was completed in order to reliably complete task B. I think that's part of what's going on. You need to maintain context as you're working through these subtasks. Lastly, I will say that we are hiring, not just for this kind of work that you've seen being extended, ever longer tasks, ever more ambitious RCTs, even more sources of evidence from which we can triangulate the truth about AI capabilities, but also for much more besides. You can find this at meter.org/careers. In particular, I'm excited about research engineers, research scientists who might be hiding in the current audience. We're excited not just for research types with academic experience, but very much for scrappy startup people as well. And we're also hiring for a director of operations. And with that, thank you very much for listening.
Our final presenter is here to speak about Google's first agentic development platform, Anti-Gravity. Please join me in welcoming to the stage engineer at Google DeepMind, Kevin Howe.
Woo! All right, hello. Last one of the day. Can we get a little energy boost? Who's ready? Who's ready? All right, happy Friday. I hope everyone has had a good week, a good conference. And let me tell you, it's been a really bad week if you are Gravity. Wicked 2 is coming out tonight. And then, of course, Anti-Gravity came out earlier this week alongside Gemini 3 Pro on Tuesday. Google Anti-Gravity is a brand new IDE out of Google DeepMind. It's the first one from a foundational lab, and it is coming right off the press. In fact, I probably should be working on the product right now, but I wanted to spend some time to share what we've built here today. Anti-Gravity is unapologetically agent first. And today I'm going to tell you a little bit about what that means and how it manifests in the product. But perhaps maybe a little bit more interestingly, we're going to talk a little bit about how we got here. Product principles, direction of the industry, these sorts of things. So my name is Kevin Howe. I lead our product engineering team at Google Anti-Gravity. And let's start with the basics. And first, just to get a sense of the room, who has used Anti-Gravity? All right, there you go. Power of Google. Love it. Who's used the agent manager? Cool, nice, good, good. All right, so basics of anti-gravity. Anti-gravity, notably anti-gravity, not anti-gravity, anti-gravity, it's an AI developer platform with 3 surfaces. The first one is an editor. The second one is a browser. And the third one is the agent manager. So we'll dive into what this means, what each looks like. So a paradigm shift here is that agents are now living outside of your IDE. And they can interact across many different surfaces that your agent, or that you as a software developer might spend time in. And let's start with the agent manager. So that's the thing up top. This is your central hub. It's an agent-first view, and it pulls you one level higher than just looking at your code. So instead of looking at diffs, you'll be kind of a little bit further back. And at any given time, there is one agent manager window. Now, you have an AI editor. This is probably what you've grown to love and expect. Has all the bells and whistles that you would expect. Lightning fast autocomplete. This is the part where you can make your memes about, yes, we forked VS Code. And it has an agent sidebar. And this is the sort of thing, it's mirrored with the agent manager. And this is when you need to dive into your editor to accomplish maybe your 80% to 100% of your task. And at any point, we made it very, very easy, because we recognize not everything can be done purely with an agent, for you to Command E or Control E and hop instantly from the editor into the agent manager and vice versa. And this takes under 100 milliseconds, it's zippy. And then finally, something that I love, an agent-controlled browser. This is really, really cool. And hopefully for the folks in the room that have tried anti-gravity, you've noticed some of the magic that we've put in behind here. So we have an agent-controlled Chrome browser. And this gives the agent access to the richness of the web. And I mean that in two ways. The first one, context retrieval. Right? It has the same authentication that you would in your normal Chrome. You can give it access to your Google Docs. You can give it access to your GitHub dashboards and things like that, and interact with a browser like you would as an engineer. But also, what you're seeing on the screen is that it lets the agent take control of your browser, click and scroll and run JavaScript and do all the things that you would do to test your apps. So here, I put together this random artwork generator. All you do is refresh, and you get a new picture of like a piece of Thomas Cole artwork. And now we added in a new feature, which is this little modal card. And the agent actually went out and said, OK, I made all the code. But instead of showing you a diff of what I did, let's instead show you a recording of Chrome. So this is a recording of Chrome where the blue circle is the mouse. It's moving around the screen. And in this way, you get verifiable results. So this is what we're very excited about our Chrome browser. And then the agent manager can serve as your control panel. The editor and the browser are tools for your agent. And we want you to spend time in the agent manager. And as models get better and better, I bet you're going to be spending more and more time inside of this agent manager. And it has an inbox. And I'll talk a little bit about this and sort of why we did this. But it lets you manage many agents at once. So you can have things that require your attention. For example, running terminal commands. We don't want it to just kind of go off and just run every terminal command. There are probably some commands that you want to make sure you hit OK on. So things like this will get surfaced inside of this inbox. One click, you can manage many different things happening at once. And it has a wonderful OS-level notification. So if there is something that you need, it will sort of let you know. And this kind of solves that problem of multi-threading across many tasks at once. And so our team is thrilled to launch this brand new product. It's a brand new product paradigm, and we did so in conjunction with Gemini 3, which was a very exciting week for the team. But alas, we ran out of capacity. This has been tormenting me the last couple of days. And so I apologize. On behalf of the anti-gravity team, I'd like to apologize for our global chip shortage. We're working around the clock to try and make this work for you. Hopefully we'll have a few less of these sorts of errors. But what's been really exciting is people who have used the product have seen what the magic of combining these three surfaces can do for your workflows, for your software development. So let's talk about it. Why did we build the product? How did we arrive at this sort of conclusion? You might say, oh, adding in a new window, it's pretty random, right? It's this one-to-many relationship between the agent manager and many other surfaces. And it's important to remember, I've been at this conference a couple of times, and every single time there is this theme. The product is only ever as good as the models that power it. And this is very important for us as builders, right? Every year there is this sort of new step function. There was a year when it was autocomplete, right? Copilot. And this sort of thing was only enabled because models suddenly got good at doing this short form autocomplete. And then we had chat. We had chat with RLHF. Then we had agents. So you can see how every single one of these product paradigms is sort of motivated by some change that happens with model capabilities. And it's a blessing that our team is able to work and be embedded inside of Deepmind. We had access to Gemini for a couple of months earlier, and we were able to work with the research team to basically figure out, what are the strengths that we want to show off in our product? What are the things that we can exploit? And then also, what are the gaps, right? This desired experience. where are the gaps in the model, and how can we fix that, right? And so this was a very, very powerful part of why anti-gravity came to be. And there are 4 main categories of improvements, powered by a little Nano Banana artwork. The first one is intelligence and reasoning. You all are probably familiar with this. You used Gemini 3, and you probably thought it was a smarter model. This is good. It's better at instruction following. It's better at using tools. There's more nuance in the tool use. You can afford things like, there's a browser now. There's a million things that you could do in a browser. It can literally even execute JavaScript. How do you get an agent to understand the nuance of all these tools? It can do longer running tasks. These things now take a bit longer, right? And so you can afford to run these things in the background. It thinks for longer. Just time has gotten stretched out. And then multimodal. I really love this property of what Google has been up to. The multimodal functionality of Gemini 3 is off the charts, and you start combining it with all these other models like Nano Banana Pro, and you really get something magical. So we have these roughly 4 different categories where things have gotten much better. And if you think about these properties, the question becomes, what do we do about these differences? And from a product perspective, it's like, how do you construct a product that can take advantage of this new wave? And hopefully, and in my opinion, this is the next step function. Autocomplete, chat, agents, and then I probably got to come up with something more interesting than whatever this thing is called. So step 1 is we want to raise the ceiling of capability. We want to aim higher, have higher ambition. And so a lot of the teams at Deepmind were working on all sorts of cutting-edge research, right? Google is a big company. And one of my learnings going from a startup to one of these bigger companies is that there is a team of people that is attacking a very, very hard technical problem. And as a nerd, this is super exciting, right? And then as a product person, it's like, wow, we can start using computer use. So browser use has been one of these huge unlocks. And this is twofold, right? I mentioned the sort of retrieval aspect of things. I guess for software engineers, there is much more that happens that is beyond the code, right? You can roughly think about it as there's what to build, there's how to build it, and then you actually have to build it. I would say building it has become more or less, it's reasonable for the model to now, given context, it can generate the code that hopefully functionally works. And then you've got the what to build. This is the part that is up to you, kind of human imagination. And then there's the how to build it, right? And there's this richness in context, the richness in institutional knowledge, and these are the sorts of things that having access to a browser, having access to your bug dashboards, having access to your experiments, all these sorts of things that now gives the agent this additional level of context. And maybe I should have clicked before, but if you saw on the screen, let's see, how do I do this? So this is now the other side of things, browser as verification. So you might have seen this video. This is a tutorial video that we put together on just how to use it. But this is the agent. The blue border indicates that it's being in control by the agent. And so this is a flight tracker. You put in a flight ID, and then it'll give you sort of the start and end of that flight. And this is being done entirely by a Gemini computer use variant. So it can click, it can scroll, it can retrieve the DOM, it can do all the things. And then what's really cool is you end up with not just a diff, you end up with a screen recording of what it did. So it's changed the game, and the model can take this, and because it has the ability to understand images, it can take this and iterate from there. So that was the first category, browser use, just an insane, insane magical experience. Now the second place that we wanted to spend time is on image generation. And we noticed this theme when I first started at Google, we noticed, okay, Gemini is spending a lot of time on multimodal. And this is really great for consumer use cases, right? Nano Banana 2 was mind-boggling. But also for devs. Devs are inherently, this is a multimodal experience. You're not just looking at text. You're looking at the output of websites. You're looking at architecture diagrams. There's so much more to coding than just text. And so there's image understanding. This is verifying screenshots, verifying recordings, all these sorts of things. And then the beautiful part about Google is that you have this synergistic nature. This product takes into account not just Gemini 3 Pro, but also takes into account the image side of things. And so here I want to give you a quick demo of mockups. So I have a hunch, and you all probably believe this too. Design is going to change, right? You're going to spend maybe some time iterating with an agent to arrive at a mockup. But for something like, oh, let's build this website, we can start in image space. And what's really cool about image space is it lets you do really cool things like this. We can add comments. And so you end up commenting and leaving a bunch of queued up responses. And it's kind of like GitHub. You'll just say, all right, now update the design. And then it'll put it in here. The agent is smart enough to know when and how to apply those comments. And now we're iterating with the agent in image space. So really, really cool new capability. And what was awesome is that we had Nano Banana Pro, we pulled an all-nighter for the Gemini launch, because that was our first launch. Then they said, do it again, do it on Thursday. So we made Gemini Pro, I'm getting all these model names confused. The image gen one, the Nano Banana one, we made that available on day one. I'm running on very little sleep. On day one inside of the anti-gravity editor. And our hope is that the anti-gravity editor is this place where any sort of new capability can be represented inside of our product. And so step 2 was, all right, we have this new capability. We've pushed the ceiling higher. Agents can do longer running tasks. They can do more complicated things. They can interact on other surfaces. And so this necessitates a new interaction pattern. And we're calling this artifacts. This is a new way to work with an agent. And this is one of my favorite parts about the product. And at its core is this agent manager. So let's start by defining an artifact. An artifact is a dynamic representation of something that the agent generates. Sorry, an artifact is something that the agent generates that is a dynamic representation of information for you and your use case. And the key here is that it's dynamic. Artifacts are used to keep the agent organized. They can be used for kind of like self-reflection and self-organization. It can be used to communicate with the user, to maybe give you a screenshot, to maybe give you a screen recording like we described. And it can also be used across agents, whether this be with our browser sub-agent, or with other conversations, or as memory. And this is what you see on the right side of this agent manager. We've dedicated sort of half the screen and your sidebar to this concept of artifacts. And so we've all tried to follow along chain of thought. And I would say this, we did some fanciness here inside of the agent manager to make sure conversations are broken up into like chunks. So in theory, you could follow along a little bit better in the conversation view. But ultimately, you're looking at a lot of strings, a lot of tokens. This is like very hard to follow. And then this is actually like, there's like 10 of these, right? So you just scroll and scroll and scroll, and you're like, what the heck did this agent do? And this has been traditionally the way that people review and sort of supervise agents. You're kind of just looking at the thought patterns. But isn't it much easier to understand what is going on inside of this visual representation? And that is what an artifact is. The whole point, and the reason why I'm not just standing up here and giving you this long stream of consciousness, is because I have a PowerPoint. The PowerPoint is my artifact. And so Gemini 3 is really, really strong with this sort of visual representation. It's really strong with multimodal. And so instead of showing this, which of course we always let you show, we will always show you this, but we want to focus on this. And I think this is the game-changing part about anti-gravity. And the theme is this dynamicism. The model can decide if it wants to generate an artifact. And let's remember, there are some tasks. We're changing a title. We're changing something small. It doesn't really need to produce an artifact for this. So it will decide if it needs an artifact. And then second, what type of artifact? And this is where it's really cool. There are many potentially infinite ways that it can represent information. And so the common ones are Markdown in the concept of a plan and a walkthrough. So this is probably what you've used most often. When you start a task, it will do some research. It will put together a plan. This is very similar to like a PRD. It will even list out open questions. So you can see in this feedback section, it'll surface, hey, you should probably answer these 3 questions before I get going. And what's really awesome, and we're betting on the models here, what's really awesome is that the model will decide whether or not it can auto-continue. If it has no questions, why should it wait? It should just go off. But more often than not, there are probably areas where you may be underspecified. Or maybe it did something during research, right? Everyone has gone through and started a big refactor, then realized they actually don't have all the information ahead of them. They got to go back to the drawing board, maybe talk to some people. Same idea. So it'll surface open questions for you. And so you'll start with that implementation plan, and then you'll say, all right, LGTM, let's send it. You'll go all the way down. It might produce other artifacts. We've got a task list here. This is the way that you can monitor the progress of the agent instead of looking at the conversation. It might put together some architecture diagrams, and then you'll get a walkthrough at the end. And this walkthrough, you kind of saw a glimpse of this before, but it is, hey, how do I prove to you, agent to human, that I did the correct thing and I did it well? And then this is the part that you'll end with. It's kind of like a PR description. And then there's a whole host of other types, right? Images, screen recordings, these mermaid diagrams. And really what's quite cool is that because it's dynamic, the agent will decide this over time. So suddenly there's maybe a new type of artifact that maybe we missed, right? And then it'll figure that out. It'll just become part of the experience. So it's very scalable. But this artifact primitive is something that's very, very powerful that I'm pretty excited about. And then I guess another question is, why is it needed? So we'll always explain to the user what the purpose of this artifact is. And then, interestingly, like who should see it? So should the sub-agent see it? Should the other agents see it? Should other conversations see this? Should this be stored in my memory bank, right? If this is something that I derived, one of the cool examples that I like is like if you give it a piece of documentation and give it your API key, it'll like go off and run curl requests to basically figure out the exact schema of like what the types of APIs you're using. And it'll do this like deep research for quite a while. And then it'll give you a report and basically like deeply understand this sort of API. You wouldn't want to just throw that away and have to rederive it the second time you did this. So it'll store it in your memory. And then all of a sudden, that's just a part of your knowledge base. So, and then there's also this idea of like notifications, right? So if there's an open question, you want the agent to be proactive with you. And that's another very cool property of this artifact system. We want to be able to provide feedback along this cycle. So from task start to task end, we want to be able to provide feedback and inform the agent on what to change. And the artifact system lets you iterate with the model more fluidly during this process of execution. And so, not to sound like a complete Google shill, but I love Google Docs, right? Google Docs is a great pattern. It's awesome. The comments are great. And this is how you might interact with a colleague, right? You're collaborating on a document, then all of a sudden you want to leave a text-based comment. So we took inspiration from that. We took inspiration from GitHub. But you leave comments. You highlight text. You say, hey, maybe this part needs to get ironed out a bit more. Maybe there's a part that you missed, or actually don't use Tailwind, use vanilla CSS. So these are the sorts of comments that you would lead. You'd batch them up, and then you'd go off and send. And then in image space, this is very cool. We now have this like Figma style, drag and drop, like, or not drag, highlight to select. And now you're leaving comments in a completely different modality, right? And we've done this and instrumented the agent to naturally take your comments into consideration without interrupting that task execution loop. So at any point during your conversation, you could just say, oh, actually, mid-browser actuation, I actually really don't like the way that turned out. Let me just highlight that, tell you, send it off, and then I'll just get notified when you're done taking into consideration those comments. And so it's a whole new way of working. And this is really at the center of what we're trying to build with anti-gravity. It's pulling you out into this higher level view. And the agent manager really is built to optimize the UI of artifacts. So we have a beautiful, beautiful artifact review system. We're very proud of this. And it can also handle sort of the property that is like parallelism and orchestration. So whether this be many different projects, whether this be the same project and you just want to execute maybe a design mock-up iteration at the same time you're doing research on an API, at the same time you're iterating and actually building out your app, you can do all these things in parallel. And the artifacts are the way that you provide that feedback. The notifications are the way that you know that something requires your attention. It's a completely different pattern. And what's really nice is that you can take a step back. And of course, you can always go into the editor. I'm not going to lie to you. There are tasks that you maybe don't trust the agent yet. You don't trust the models yet. And so you can Command E. And you can Command E, and it'll open inside the editor within a split second with the exact files, the exact artifacts, and that exact conversation open, ready for you to autocomplete away, to continue chatting synchronously, to get you from 80% to 100%. So we always want to give devs that escape hatch. But in the future world, we're building for the future. You'll spend a lot of time in this agent manager working with parallel sub-agents. Right? It's a very, very exciting concept. OK, so now that you've seen we've got new capabilities, multitude of new capabilities, we've got a new form factor. Now the question is, like, what is going on under the hood at Deepmind? And the secret here is a lesson that I guess we've just learned over the past, I don't know, we've spent like, or I've personally spent like 3 years in CodeGen. It's just to be your biggest user, right? And that creates this research and product flywheel. And so I will tell you, anti-gravity will be the most advanced product on the market because we are building it for ourselves. We are our own users. And so in the day-to-day, we were able to give Google engineers, Deepmind researchers, we were able to give them an early access and now an official access to anti-gravity internally. And so now all of a sudden, the actual experience of the models that people are improving, the actual experience of using the agent manager and touching artifacts is letting them see at a very, very real level, what are the gaps in the model? And whether it be computer use, whether it be image generation, whether it be instruction following, right? Every single one of these teams, and there are many teams at Google, has some hand inside of this very, very full stack product. And so you might notice as an infrastructure engineer, you might say, oh, this is a bit slow. Well, build it for yourself. Make it faster. Image gen. All of a sudden, computer use isn't going well. It can't click this button. It's really bad at scrolling, really bad at finding text on the page. Well, go off and make that better, right? So it gives you this level of insight that evals just simply can't give you. And I think that's what's really cool about being a DeepMind. You are able to integrate product and research in a way that creates this flywheel and pushes that frontier. And I guarantee you that whatever that frontier provides, we will provide in anti-gravity for the rest of the world. These are the same product. And so I'll give you 2 examples of how this has worked. The first one was that computer use example, right? In collaboration with the computer use team, which we sit a couple tens of feet away from, we identified gaps on both sides, right? So we're not just using an API. We are interacting across teams to basically say, oh, like the capability is kind of off here. Can we go off and figure out what's going on here? Maybe there's a mismatch in data distribution. And then on the other side, it's like, yo, your like agent harness is like pretty screwed up. You got to fix your tools, right? And so then we'll go off and we'll fix our side. But it's this harmony. It's both sides talking to each other that really makes this type of thing possible. Similarly, you come up with a new product paradigm, artifacts. Artifacts were not good on the initial versions, right? What part of data distribution includes this like weird concept of reviews? And so it took a little bit of plumbing, a little bit of work with the research team to figure out, all right, let's steadily improve this ability. Let's give you a hill to climb. And then now we were able to launch Gemini 3 Pro with a very good ability to handle these sorts of artifacts. And so it's this cyclic nature that I'm really, really betting on. And this is really how anti-gravity will defy gravity. We've got pushing the ceiling. We're going to have an agent with very, very high level of ambition. We're going to try and do as much as we can. And this includes vibe coding, though I will say there are some excellent products out there by Google. AI Studio is an excellent product. We are in the business of increasing the ceiling. Second, we built this agent-first experience, artifacts, agent manager. And then finally, we have this research product flywheel. And this is the magic, and this is the 3-step process that we used in building anti-gravity. So it's been a blast. I mean, I've been back at AI Engineer Summit. Thank you again, Swyx and Ben, for having me. It's been awesome to come back every year. And so on behalf of the anti-gravity team, I just want to thank you for your time, for your patience as you use the product, and your support. And of course, you too can adopt a TPU and help us turn off PagerDuty a bit more. And then of course, you could also yell at me on Twitter. That's another way of doing it. Maybe do it in DMs instead. But we've got a lot of exciting things. And I'm really, really excited to bring anti-gravity to market. The team is thrilled that this is now out in the wild. So we welcome your feedback. And thank you again for listening. Enjoy the rest of the conference.
Ladies and gentlemen, please welcome back to the stage, Jed Borovik.
Thank you, Kevin. Let's hear it for Kevin and all of our speakers today. All right, what a great way to end our sessions. How are we doing? I know it's been a big day. Yeah, we're still somewhat alive. Okay, before we wrap up, a few logistics. Thing 1, there's an official after party tonight. If you've registered, there'll be a follow-up email in about 30 minutes. The second thing is tomorrow is a full day of workshops. Importantly, they are not here. There's 2 different buildings. There's the Datadog building that's right around the corner. There's also the AWS building, JFK 27 on 39th Street. But when in doubt, the schedule is on the website. My last act as MC is to invite the event's co-founders up to stage for a special closing word. Please join me in welcoming AI Engineer co-founders Benjamin Dunphy and Swyx.
All right. And let's keep it going for Jed, everyone. Let's keep it going for Jed. And Alex yesterday, our lovely MCs who really glued this place together. So we really had such a great time. Did you all have a good time? So glad to see that. Hopefully the program went smoothly. Me and the team here, the lovely team at the Time Center, Argus HD, Max Video Productions, everyone here supporting the production, that's us. And the content curation, let's give it up for this guy.
Oh, thank you. I hope you enjoyed it.
You have no idea how hard he works on this. And for me as a conference producer who used to do both the content curation and the production, it's just a godsend to partner with someone who is on the forefront of thought leadership like this. And you have no idea how hard he works. And he's actually recently so invested in this that he's actually recently stepped up as CEO. So just kind of announced that.
That wasn't
I was going to do that. It wasn't in the show notes.
Expecting, yes.
But yes, Sean is now the new CEO of the company, and I wouldn't have it any other way. If there's one person I want to follow, like in this world, it's this man. And if there's one person I'm happy to be working for, it's this man.
So. Yeah, likewise. The production quality and the creative design and all the music that you hear online is all Ben. So you got to give it up for him as well.
Thank you. So I think we're on, let's go to the other notes. Let's go to this. So we wanted to talk just a little bit. I mean, you saw this slide earlier from Sean. It's basically just showing the growth that we had. Like when I started conference production, I always approached events from the point of view for myself and with clients that from your first event, you want to start small and worst case scenario, you sell out. You don't want to start big and you have an empty venue, you blow the budget, you go bankrupt. So we did that intentionally. We kept the first one very small when we announced it, with the rise of the AI engineer back in 2023. And we sold out that. And then we sold out every single event since then, and we're also growing online. So all of you watching on the live stream, thank you so much for being part of this community remotely. If you can make it to one of our events, we are growing. We have some announcements for you. In just a few moments, we'll be coming to you a little bit closer around the world. And for this event in particular, we had 2,463 applicants, and 815 of you came. So if we ask an LLM, that might tell us that's maybe 2% admission rate, I think, something like that. It's actually 33%. But that's just showing like the exclusivity of this event in particular. Summit is designed to be a little more exclusive because we want this to be our Solvay conference. If you know the Solvay conference, some of you might, that's essentially where Albert Einstein, Marie Curie, all of the physicists from around the world came in advanced physics over the course of a couple weeks, I think. Basically decades, right? And basically to the point where we are today, because string theory, where is that taking us? Come on. Hopefully we can solve that with the rise of AI. In any case, that's what we have for Summit. And where are we at? I put this together in the last 30 minutes, so pardon me. So there's clearly demand for this community. There's clearly growth here. There's a lot of excitement here, and there's a lot of great content, and there's a lot of questions to be answered. There are no clear answers here. This is potentially, as people argue, a new consciousness, right? It's a new form of consciousness, right? We're all discovering this together. So as we push forward into the dark, into the future, in this wonderful, beautiful moment in this temporal existence, we will figure it out together. And that's why we're excited to announce, roll tape. World's Fair is coming back to San Francisco 2026 on June 29th, typo, to July 2nd. So we're going to do 4 days. So we're going to do 1 workshop day and 3 days of sessions. So tickets are on sale now. These are going to be the cheapest they will be. Did we decide on a discount code or just like the price is cheap?
No, the super early bird is the discount.
It's the super early bird. Yeah. Okay. Well, there's 2 choices, right? The ticket is this price, and we're going to change the price later, or here's the discount code. So that's always a question. We're running the event. This is, side stuff. This is future events. So these, so we're really happy and very excited to announce that. This year, we are at Moscone West. That is the baby brother of the Moscone Center, so we're not quite there yet. But we sold out the Marriott Marquis, which is the largest event hotel in San Francisco, at about 3,200 just a few months ago. And so the only place to go from there is to Moscone West, which is about 6,500 capacity. So we're guesstimating, conservative 5,000, but we hope to get to the max capacity of 6,500. So buy your tickets now. They're not going to get any cheaper. Where are we? Oh, the video ended. It's supposed to be quicker than this. Let's go to the next one. We got one more announcement. You want to say something about World's Fair?
Yeah, World's Fair is our is our flagship. We are basically trying to capture all of AI in one event, and for you to basically have kind of an all-you-can-eat pass to go to multiple conferences at once. This year we had 10 simultaneous tracks. That was a lot. So we'll never expand beyond that. But I think we want to really make it count and have you basically just dip into whether it's like generative media or like voice or like robotics or anything else that you want to explore. We are also bringing it to Europe for the first time. So that's the next announcement.
Yes. So this next April 8th to 10th, whether you're from Europe or you want to make the trip to beautiful London, we are right in Westminster at the beautiful Queen Elizabeth II. We can fit about 800 people in there. So buy your ticket soon. We expect that one to sell out as well. It's going to be basically Baby World's Fair. We want to establish World's Fair essentially in Europe. There's no better place than London. We love Paris, and we love what the Koyab team did with AI Engineer Paris. But we feel London is the right call for this event. The venues there are beautiful. The city's beautiful. I'm biased. I really love Paris, but London ain't bad too. I lived there for a little bit, so I do enjoy it.
I really care about direct flight from SF to London. So.
That's it. That's it. Very nice.
Yeah.
Okay, so tickets are also on sale here. Again, super early bird pricing, the cheapest they're going to get. So AI.engineer/Europe. I don't know when those are going to expire, but I'm sure we'll communicate that to you guys later. And then I think this is a video, so let's go to the next one. Okay, so with all of this growth, little old Sean and me, we can't do this ourselves. So we needed to bring someone on to really help grow the company. We needed to get procedures. A lot of organizing conferences it's a lot of grunt work, right? It's a lot of human connection. It's a lot of reminders. It's a lot of sales, but it's also running the business and then just coming up with processes. So a lot of times you're kind of figuring it out as you're going, and you get these processes, but then things change. And then some things are not perfect. So you're always behind, and deadlines are always coming. And these budgets are insane, like you have no idea, and you don't want to see a budget for one of these events. And there's just a lot of complexity to that. So when we first started the event, we, back in 2023, we brought on Leah McBride, who who used to be the director of events at Twitter, and she helped us out. And within 2 months, basically, she was helping us to run Engineer Summit to the point where it was a lot smoother than when I was just running events on my own. With, you get the Hollywood crew that comes as professionals to help you run the actual event, but the whole production is a lot of difficulty. So we're very, very pleased to announce that Leah McBride is joining us as our new general manager to help us grow into a proper corporation. So please join me in welcoming to the stage Leah McBride, everyone.
Yeah.
Thank you, Ben and Swyx. Hi, everyone. As Ben has just told you, I'm very excited to join the company as general manager. I've been working in event marketing, tech event marketing for almost 20 years. I was lucky enough to join one of the biggest London agencies. I am Scottish, so I'm from the UK, quite a few years ago. And Google was my main client for quite a long time. So I kind of grew up through that Google excellence and how we operationally produce excellent events. I was then lucky enough to go on and be the director of events for the developer platform at Twitter for a number of years, where I led multiple global tours.
Just a go.
I led multiple global tours, and I also led our flagpole event in San Francisco, which was Flight, if anyone ever went to that. And following that, I moved, that was in San Francisco, then I moved back to London, and I started a company called Improbable, which is a gaming platform. So I worked mainly with gaming developers there and grew the marketing team from 3 up to 38. And following that, I was lucky enough to meet Ben and Swyx. So yes, I've been with them since the first event, and we have just got a super exciting year coming up. So to add to our program of Europe and Moscone, San Francisco, if anyone was there, I don't know, was anyone in Paris with us? Yeah. Excellent.
Show of hands. We got like 5, 6 people.
So you'll be able to contest that the Paris event was absolutely phenomenal. So our partners, Coab, came to us and asked if we were going to do Paris. We weren't really ready for that, and they suggested that we partner with them. This was a great idea. They did an absolutely incredible job of producing the Paris event. It was a sold-out sponsorship, sold-out event. We had so much incredible feedback that we have actually decided to turn that into a program. So we are launching in 2026 our partner program. We have already signed up, so we are hoping, again, to be doing Paris, October 2026. We have also recently signed up with a Miami team. So we're going to be doing an AI Engineer Miami, April 20 to 21st. And then also, we're very excited to be going to Melbourne also with a partner. So we'll be doing Melbourne, June 3rd to 4th, 2026. This program is obviously just starting, so there's going to be more opportunity as we grow to be part of this program. So if there is anyone in this room who wants to know more about that, please just email us at sponsorships@ai.engineer, and we can talk about what that looks like for your city. So thank you. I'm very excited for 26.
Thank you so much, Leah. You can take that. All right, so that's basically all the announcements we had. We hope to see you at one of those events, whether you come to San Francisco or London. We'll probably be back for New York. So should we come back to New York? Yeah. All right. By the show of woos, how do you say that? By woos, how many of you are from New York?
Wow. Yeah.
San Francisco? Ooh. That was close. Let's do it again. New York. San Francisco. Oh, man. I
Scotland.
Think it's like 70-30.
San Francisco changed pitch.
All right.
San Francisco went higher this time. I don't know.
I met Cape Town the other day. So is Cape Town here? Cape Town has left the building.
Yeah.
We had New Zealand, right? So people are coming all over the world for these events. So obviously New York is one of the great cities of the world. And of course, those 70% of you will say the greatest. We love coming here. We love giving people an excuse to come here. So we hope to be back soon. And we love this venue. Despite being in Times Square, we put up with it because the crew here is just so fantastic. Obviously, look how gorgeous this place is. So we hope to potentially be back here next year. And then the rest of our crew that we cannot do this without. Everyone from Argus HT, who's running all of the AV. Can we give a round of applause for them? And they put up with us because we're getting them assets super, super late. So namaste. I think that's what I'm supposed to say. And I always forget people at this moment. Who else am I forgetting? Florimon Catering. Our caterers are super fantastic. Photographer Randall Gee, Max Video Productions. Doing our B-roll. We're going to have some of those end-of-day clips.
Marina, Kyle.
Yes, of course. Our rest of our team members. Oh my God.
Flo.
Why did I add those as our slides? We got those in the end credits. I at least thought enough to. I was doing this like 30 minutes away. Anyways, yeah, Marina, our senior event producer. Wendy, who recently just joined. Kyle, our program production manager, just joined like 2 weeks ago, and it's been just hit the ground running. Trish, our production assistant, supervisor, and just so many of our partners in programs. So we want to thank all of them. But that's about it for that. Apologies if I forgot you. But we now have until 6:30 in the venue. So we have a little bit of time to kind of chill, make your final evening plans. We do have an official evening after party brought to you by Cerebrus, along with some friends, BCV, McKinsey, Warp, Exa, Modal, am I pronouncing that right? And Metronome. So that is the official offsite after party. We're not giving you the location right now because we're on the live stream right now, but I believe it's on the signs outside, and we'll also send an email in just a few moments, and it's also on your attendee guide. So do go ahead and check that out. They are asking for RSVP for headcount, but you don't need it. You can just show up with a badge and you can get it. But don't forget your badge. So let's give it up for Cerebrus.
Thank you, Cerebrus.
Also, last people to thank is our sponsors and speakers. Our speakers, they work so hard for this, and due to Sean's no vendor talks policy, which is it's a great boon for the community, but they have very little incentive to do that other than thought leadership. So that is a lot of work, and they do a great job with that. And then our sponsors. Did we enjoy the sponsor expo?
Yeah. It's really well done by Art and Display too.
Should we try for the photo?
Sorry?
Should we try for the photo?
Sure. Yeah.
Let's do
is
it.
that the plan? Okay. Cool. Yeah.
So we did this last year, and it was really great. This is our Solvay conference photo. If you want to come up here and do a photo, we can do that together. Randall Gear, our lovely photographer, is going to take a photo. He will direct us. We can actually get him the mic, and then he can yell at us to go left and right. So come on stage. Just one caveat. These things here, they look like you can step on them. You can't. They will break, and we'll get charged a lot of money, so just be careful of those. But otherwise, come on down if you want to.
Yeah, we did this. We've done this every conference.
Totally fine.
It's a little memorabilia.
But please come on, and please keep my mic on for a little bit.
Hi, thanks for coming.
Yeah.
Hope you enjoyed it.
I'm going to everyone now.
Hey.
Thank you so much.
Yeah.
This is amazing. Before, so
Absolutely.
I'm in Minneapolis,
Pleasure.
so we just started like a meetup there, and that's awesome.
Yeah, we do AIE meetups too.
My pleasure. Yeah.
I'm like on a hot mic.
Code Summit, World's Fair. Yeah. So the AI Engineer Series of events. Yeah.
Okay, don't be shy. Take up 2 steps to the front of the stage, and we'll have different rows. And if you're on the left side of the podium, I won't get you, so get on this side of the podium. And don't squat yet, but we'll do kind of like a little squat in the front, but not yet, okay? And if you can, don't be shy. Squish in. There's a lot of space in the middle, so don't be shy. Squish in towards the middle. This is the middle. Thank you very much. Oh, we'll just do a super wide. Okay, this will work. Okay, cool. Oh, wait, where's Swyx? Swyx. Where is he? You want to go get burritos? Actually, since we have some time, can we get like half of this group to come to this side? It's like way left-handed. Can you just, the gentleman in the rain jacket right here? Yeah. They've been busy running around outside. Okay, so now we're going to have the front squat just a little bit. If you're in the middle, squat medium. And then if you're in the back row, tippy toe a little bit, yeah? Okay, on 3. Here we go. On 3, looking at me. 1, 2, 3. 1, 2, 3. Wait for it. Wait. Make sure it's good. Okay, now give me some